Good morning, everyone.
Good morning, sir.
Good morning,
Yeah,
sir.
I
Good morning,
think
sir.
Good morning, sir. Good morning.
Good morning, sir.
yeah,
Good
good
morning.
morning. So,
Good morning. Good morning,
just a
sir.
second. I have some small problem again with my laptop, so it may take a minute or two. Before that, so good morning to all the participants, and I just want a brief, very quickly, a minute or two, if people can just say what is their experience over the last 3 years and last 3 days. If a couple of people can just speak, I think that will be great as I just start my PPT. Is it relevant, irrelevant? Is this meaningful? Or what is it that you expect? Because as I say, I have been intermittently, when I get in between, I have mentioned that, see, we are trying to showcase that there is a huge range of emerging opportunities which actually can be done in our own labs, working with our colleagues in other departments, even if we had not done earlier. If we can just open up our mind and do simple experiments which could lead to cutting edge outcomes. So, I mean, most of our presentation is, towards showcasing this activity. So I hope, you are able to appreciate it, or I don't mind if we can have some inputs from you as to what do you feel about it. So as I get started, because for looks like I had some battery
Yes,
problem
sir.
with my laptop. So
Yes, sir.
I'm just rebooting the other laptop. Yeah, please.
Yes, sir. Yes.
Okay, anyone can, maybe you can just give a couple of inputs if you feel it's meaningful.
Hello, sir.
Haven't had breakfast or very tired.
Hello,
Yes,
sir.
sir. Yes, sir. Audible. Audible. Yes, sir.
Thank
No,
you,
no.
sir.
So maybe we wouldn't mind having inputs from you. Just a minute, 1 or 2 minutes of saying what is it that you feel over the last 3 days.
Yes, sir.
I mean, I don't think, can we still try to make some small changes if necessary to make it interesting is something we want to know. Yeah.
Yes, sir. I think Vishal sir is saying. Yes, sir. Please continue.
Yeah.
Thank you, sir. I am from mechanical background, and
Yeah, please.
and it is my interest to know about this industry 4.0 and
Yeah.
what are the utility to learn. That's why I
Yeah.
have joined this course, and
Great.
it is found useful when yesterday's hands-on sessions help
Uh-huh.
me to know about that Arduino, Raspberry Pi, and
Yeah.
their connectivity on computers, and
Yeah.
what various mechanical application can be operated with the help of Internet of Things
Yeah.
and these electronics components. So I
Yeah.
found that is quite easy by that hands-on. Otherwise, I'm
Okay.
just listening several webinars that only talking about the technology. So by that,
Yeah.
I am not getting the anything about this how to implement as a mechanical engineer.
Okay.
Our college has started to implement these things,
Uh-huh.
industry 4.0. So
Okay.
I wanted to know much more about this so I can introduce into that field.
Great.
Yes, sir. Thank
So
you.
Yeah.
maybe in coming 2 days, I'm much more familiar with these things.
Yeah, I mean, as you rightly mentioned, the idea is that how do we link everything and so that people can make some sense or go back and relate to their colleagues and say, this is what we are looking for, and that it becomes more meaningful. So I hope we are able to give some flavor towards that. And so today, again, when we will be trying to talk about some of these materials and device. We have seen in the very beginning, the title says material and devices. So we want to talk something about them and say what all can be done even there. And then, of course, as I mentioned earlier, showcase some of the labs and infrastructure that we have created over the years, and how that many things actually we can do in our labs, or what is available even in indigenously, what has been done are some of the things we want to showcase in the presentation. And I think partly as this highlight or bring the confidence that actually we can work on new product process technologies which could lead to, meaningful development. And so that is the essence of what we want to say. And I hope, if it can give everybody this confidence that say we can work together and make things happen, I believe we have done our job for the activity.
Yes,
And so let me get started in brief without much ado.
yes, sir. Let me
Anybody
just-
else, any inputs, please? Any other input? Okay, I think we will sort of get started now.
Yes, sir. Let me give you a brief idea about the today's talk. Good morning, all participants. Good morning, respected speaker for today's morning session. Our Vice Chancellor of C.V. Raman Global University, Odisha, Professor B.S. Satyanarayana. He will deliver a talk on IEEE IRDS roadmap for sensors and IoT, the feasibility of state-of-art R&D in large area flexibility, flexible wearable devices and sensors for IoT in the academic institutions. I request sir to kindly.
Yeah. Okay. So thanks, and let us get started with today's interaction. So as I mentioned, see, the topic covers a few aspects, namely emerging material science, devices, IoT sensors and systems, and then Industry 4.0. We have already said many things about some things about Industry 4.0, some more things about IoT and its simple implementation within our environment. And then we have also spoken, a few things about sensors. So today I want to talk about two key aspects. If you can just remember that there is something called an international roadmap for devices and systems. So I think that would be something I want you to remember, because the whole of the semiconductor technology, as we have said in some of our previous meetings also, is what is driving, lot of this development in every domain. And these semiconductor technologies are such that so many new materials are coming up which are more environment friendly, easy to do without any safety requirements, or safe to work even for students, yet do cutting edge material and devices. And the process for this is essentially using amorphous or nanomaterials, either grow them on surfaces by bringing atom by atom and creating a material, or make a solution, use screen printing, inkjet printing, and then create devices and systems. And these can be again made in very, very large area. So, I think the whole of the international roadmap for semiconductor devices and systems essentially talks about this emerging area, which I'm sorry to say we don't even mention in our professor in IIT writes a book in India in 2020. He does not even mention large area flexible electronics in the syllabus. In electronics, in material science, in physics, semiconductor device physics, or instrumentation and sensors. Whereas this has been, anybody who, can you name some devices or systems which could be linked to something called large area flexible? We also said something in the first introductory talk also, or some others mentioned. Anyone who can say something about it? Any thought? Do you follow what is large area or flexible electronics or large area microelectronics? Any heard of it, used, or any material used for such device? Any faculty? how many of you use photocopiers, scanners, printers, mobile phones, LCD displays, touch screens? I presume some of you use it, or every one of you use it.
Yes, sir, using.
So everyone, I'm sure, is using it for the last 20 plus years. Mobile phone maybe last 10 years plus, but photocopier, LCD display, or even a plasma display and all that you might have seen over last 15 to 20 years. And many of you might have used calculators even 25 years back, which would work even in room light under tube light. Any idea? Anybody who remembers having calculators which used to be charged by solar panel in them in room light, even when you have tube light? Conventional crystalline silicon don't do that. Any reason? Anybody? Physics, electronics, material science, or anybody? Any thought?
Yes, sir, that calculator FX 991, that having a solar panel.
Yeah. And it used to work even in white light, if you remember. In the tube light. If you have if you can recall.
Yes, sir.
Yeah. And so, but suppose if you take a conventional current day solar cell, which is typically deployed, and you take it in the room light under LCD, a tube light, will it work?
Not that much recognized, but maybe they are not going to charge. That is only taking the light that having high intensity.
Yeah. So if anybody from physics or material science or electronics, any thoughts? Can I also share my screen, please? Am I allowed?
Yes, sir. Yes, sir. You are allowed, sir. You are now co-host.
All right. Okay. Thank you. Yeah. So anybody, from electronics, who could just confirm? Or physics, material science?
Sir, I
you see,
light is important.
I can't hear if somebody is speaking. Can they speak a bit loudly?
Yes. Sir, work function of the light is, I think, material of that it is important. So that.
Yeah. I think, you see, any optoelectronic device, its working depends on its band gap. Work function is more linked to the carrier coming out of the material. So if I have some other application, like say a vacuum nanoelectronic device, I will have to look at work function. So if I have to have any photonic response, I need to know something about the band gap of the material. So I'm sure whether you are mechanical, civil, chemical, you would have studied that. The band gap of silicon is about 1.1. E volt. Okay, 1.1 electron volt, and that this 1.1 electron volt also, it is something called, it's a indirect band gap material. So if you even make a device, the band gap for the voltage that you can get out of it, depending on the best device, might be something like 0.5, 0.6 or 0.7. Okay, the VOC would be very small. And also, because the band gap is like the window will allow the light into the device, and that light is absorbed to create electron hole pairs to make, either use it as a photonic sensor or use it as a solar cell in an alternate quadrant where it converts electron hole pairs if in the fourth quadrant of the IV characteristics, so that it can be now drawn out and charged. So that crystalline silicon can only work up to predominantly red or orange. Its response in blue and green is very poor. So it will not work in room light, especially something like tube light. Whereas if you go to conventional, new emerging materials, you can design the band gap up to 2 or 2 more than double the band gap, that it will actually work in room light. So the point I was trying to make was, a huge amount of new materials, devices, and systems have happened over the last 30 years. We are using it every day. It is already a $200 to $300 billion industry, going to be $500 billion to $1 trillion opportunity in the age of IoT. And the best advantage of this new material is that These materials can be grown at lower temperature. They can be grown on any surface. And therefore, IoT on wearable electronics, IoT on any surface, IoT on glass, paper, plastic, textile, ceramics, tiles, everything becomes possible. Sensors and their control electronics. So we just want to just showcase some of this. I am sure in 1 hour, we will not be able to cover right from material to what is the difference in the material to the type of devices and systems. But then, as I said, every thing that is going to happen in future in electronics is predicted by something called the International Roadmap for Devices and Systems. IEEE has a website. Any of you can log into it and become, it doesn't matter which department, which domain, or even if you're not related to academics, you could in principle literally become a member and have access to that information. And that information tells you what, everybody from scientists to engineers to professors to company managers have joined together. They work over years and look at every 2 to 3 years, what is the progress? Based on this progress, what can we do? They predict and create a roadmap. And in that roadmap, a huge amount of future prediction for all of this man-machine interface, wearable electronics, or anything that we want to do with this cyber physical system, network and physical system, whether it is a tree, whether it is a plant, whether it is a human being, whether it is an insect, whether it is a working machine, how can they be connected? IoT essentially, the other way you have to look at, that's why you want to call it a cyber physical system, is actually through these electronics and devices which are connected and enabled. And more importantly, I am sure, Professor Rajesh yesterday mentioned that typically these IoT devices are expected to be working for 10 years with their own power. You can never try to connect a battery. So even have systems integrated where it will be self-power generating. So you want to call that as energy harvesting or scavenging. It will literally take energy from environment. Maybe it is light, maybe it is wind, maybe it is the force, or maybe it is a differential temperature. Power the batteries within the system again, which are again on glass, paper, plastic, thin film devices. And that battery will then power the circuits to measure the signals, say once in whatever time, because we don't want to necessarily in this IoT device want to be measuring in picosecond and femtosecond. Maybe it can simply measure a data once in 5 minutes, or in some cases once in 15 minutes, or once in an hour, or just maybe even once in a day send a signal that this tree exists. So for that, it can throughout the day generate its own energy, store it in its battery, and all this can be grown with additive manufacturing, one upon another, layer by layer. Additive manufacturing does not mean only, a 3D printing with some material flow, but multiple things. Conventional thin film itself is the first fundamental additive manufacturing technology. So many exciting things are happening. So in the next 1 hour or so, or 1 hour, 10-15 minutes, I want to sort of showcase all of this and that what ITRS says, what all will happen, or international roadmap, and how new materials are emerging, and then say something about, as I said, large area flexible electronics, or maybe even one more area maybe called vacuum nanoelectronics, and say how material devices application are happening in that domain, so that you have an introduction. And again, the key point I want to convey, whether I am working on image processing, signal processing, whether I am working on embedded system, microprocessor, microcontroller, or whether I'm working with materials devices, whether I'm in chemical engineering, mechanical, all of us have a huge role to play in developing some of this. If you go to a mechanical engineering department, say in US or European university, they would be working, all their work will be on flexible electronics. That is to see that how does a substrate retain this material, how much can it bend and no circuit failure will happen, reliability will happen. So, and all that. So they look at material and the mechanical property. The same thing a chemical engineer will look at, how do we cause a flow process. So whether I want to deliver a tablet or some on a device, or whether I want to deliver an electronic circuit, or whether I want to do a drug delivery plastic patch, how can I work? How do I do through sol gel process, create some of this technology on it just by flowing liquids on surfaces, on micro channels, and making them to solidify, or just by using screen printing, inkjet printing. So these, only in India we segregate everything. Maybe, sorry to use the word, like sometimes our old I mean, caste system or people are segregated. Again, that was a wrong interpretation given in later stage. Earlier, there was no such division. Everything was one and the same. And today, once again, everything is hybrid. So also, all domains combined, multidisciplinary, and that is an exciting opportunity where the whole world is trying to discover, identify, find affordable processes, affordable technology. So we can even now start and get onto this bandwagon of large area flexible electronics, from material to processes to devices to systems and integrated circuit development. And integrated circuit does not mean, I mean, a nano dimensional device. The device, as I said, can be hundreds of micron to hundreds of millimeter, and still create our own new, I mean, electronic circuits to run them again on glass, paper, plastic, ceramic, textiles, using amorphous and nano material. The material dimension is in angstroms, but the device dimensions are in microns and millimeter. And therefore you say you can work on, I mean, nano, micro, I mean, meso, electro devices, I mean, large area devices, and work on them. So that is what we want to showcase. And just as an introduction, right from, as I said, what is IRDS roadmap say, what is large area flexible electronics type of applications that are happening, and how does it come? If I have to come from, because finally it has to start from materials, and this I can literally do from beaker and or a syringe, or I mean simply a simple plasma device which I can create for a few lakhs in our own lab, and do the coating on surfaces which could parallelly be a tribological application, parallelly be a sensor, touch screen sensor, and equally be an electronic transparent conductor. So those are the type of possibilities these materials offer, from medical to aerospace, agriculture to electronics, I mean, all sorts of application. So let us have a quick bird's eye view of this area of large area flexible electronics and how IRDS talks about it. Is my screen visible? Hello?
Yes, yes.
Yes, sir. Yes, sir. Yes, sir. It is visible.
Fine. Okay. So as I said, from time immemorial, I mean, the transformation of people has been through material, evolution of material, from Stone Age to bronze or steel or aluminium, copper, and from steel to, I mean, silicon age, because now, I mean, from late, say, 70s, 80s to now, it is silicon is literally transforming everything. Soon, everything will be polymers and plastics and carbon in general, whether it's a polymer, whether it is diamond, whether it is a graphite. These are the new material, and these stay, I mean, the carbon with various, I mean, elements together would be the polymer, hydrogen and other compounds. Carbon per se is diamond, or carbon in one form, I mean, tetrahedral. Carbon in hexagonal form is going to be graphite. And this is emerging as a material which is environment friendly, safe, and very viable if you can do it accordingly, and also reusable. So we have moved. This age of materials is also causing the age of technology transformation. And like earlier, it took thousands of years for steel, or hundreds and thousands of years to emerge from Stone Age to aluminium or bronze or steel. And then if maybe steel took about 100 years to 120, semiconductor 50 years, huge transformation. Now carbon, as I said, though we knew carbon, I mean, understanding it, whether it is fullerene or graphene or all the, I mean, or carbon nanotubes started in mid 80s. And today it has already evolved into a billions of dollars of technology. And the future of sustainable materials, again, carbon offers exciting process opportunities, and also other metal oxides, organic materials, nanomaterials, but predominantly environment friendly, safe materials. And today we can design and engineer materials to do anything, linking computers, using artificial intelligence, machine learning, high performance computing. Because now we know that, I mean, see, if there was a semiconducting material, what was its structure? If there was a superconducting material, what was its structure and bonding? Similarly, if there was a polymer, what is its structure? So how in that polymer, which was supposed to be an insulator, if I can add some metal dopants, suddenly it becomes a conductor. At what level can it become a conductor and at the same time be transparent? But that is by just adding oxygen and metal. So all this understanding is creating an exciting age of tailoring materials. And the tailoring materials allows us to also tailor devices and systems. And that linked with the communication technology. See, from the first radio to the broadcasting television, that is where IoT comes in. I mean, to direct television, to digital phones in 94, to high definition television in 87 to 97. See, we have come a long way in 2020, where there is a convergence of all sorts of devices and systems. And so 5G, and now we are moving into 6G, an exciting time. And as I maybe also mentioned on the other day, I mean, on Monday, so whether it is services, whether it is technology, in many emerging areas, multiple people have given multiple prediction. Here you see one graph which says Asia, Western Europe, US. It says how the world was led by Asia, essentially India and China, for over thousands of years. Then we came down around 1930, 40. And once again, you see, slowly it started going up by 2000. And so by 2050 or 2055, once again, India, when people say Asian world, it should be India and China. And there's a huge probability India will be the leader, both because of its people and possibly in a younger people and technology. So knowledge driven economy. But for that to happen, we academics have to truly come of age, make use of this opportunity. And you see, what are the areas? It doesn't say chemistry, mechanical, physics, medical. The emerging areas where there are opportunities. On one side, here you see some green color graph. That is a graph which says what will happen in next 10, 15 years in service industry. And that service industry is supposed to be close to 70 to 80 trillion opportunity. And about 20 trillion odd, where 10 trillion is India and China put together. So India has an opportunity to at least do 5 trillion in service, 5 to 10 trillion in service. Similarly, you go into disruptive technology, whether it is mobile, automation, artificial intelligence, machine learning, Internet of Things, cloud computing, robotics, autonomous vehicles, genomics, energy storage, advanced materials, whether it is 3D printing or whether it is again oil and exploration, renewable energy. Most of the disruptive technologies are going to come from developing countries. If you see, one part it says developed, one part it says developing country. So we have a huge opportunity that between the two, if somebody says India will need another 10 years to be 5 or 10 trillion, these predictions says India could be a 20 trillion economy in next 10 to 15 years. So we are 2.5 so 2.5 to 20 trillion is an 8-fold increase in 10, 15 years, is a mind-blowing opportunity. But this can only happen if we academics understand that the opportunity is with us. We need to work together. If we can work from physics, chemistry to economics, management to, mechanical and biotechnology together, we will be in a position to take this opportunity and truly, say leapfrog. And as I said on the other day, can anybody who remembers, I showed this first image on the left hand top corner. What is this? Anybody? You remember seeing this page on my Monday? Is the mic system on or nobody is listening? Can somebody say yes or no if you saw this image on Monday?
Yes, sir.
Yeah. So do you see, it's a black and white picture here. Some wires and some blob and all that.
Yes, sir.
Yes, sir.
This was the first transistor, which was invented in 1947 when India got freedom. And in 1947, India had more advanced knowledge of electronics and semiconducting, even before all this wireless technologies evolved, and even before an electron was evolved, Bose showcased the possibility of wireless and microwave communication. Raman spoke about Raman phenomena. Today, every non-destructive testing to advanced sensors are based on Raman. Yesterday, he spoke about the Raman scattering for use in communication and sensors. So we actually were ahead of the curve, but somewhere our education misled us or made us into glorified by-hearting parrots who don't think. And the below this black color picture is the first transist integrated circuit that was fabricated by Fairchild by around another 5-10 years from then. And just imagine from there, today we have gone to 1 nanometer technology, another black and white and brown and white film that you see in the bottom right hand corner. And so Intel today has already started working on 1 nanometer technology, and it doesn't call it as 1 nanometer, just it says 20 Angstrom technology, rather, just to be safe. But it is working on 1 nanometer technology today. So transformation has happened so much. We were leaders even in 45, 50, and people like Krishnan were setting up National Physical Laboratory and many experiments, and C.V. Raman was still setting up the Raman Research Institute coming out of IISc. But he passed away in 70, but somewhere, as we said, we foolishly left all our competence. Some of these best people went away from India. They were then later heading AT&T, now called Bell Labs, and from there it has become Lucent Technology and all sorts of things. Anyway, so what is this IRDS roadmap? You see here, I mean, you see a small map here which says something called more than more, diversification, more, beyond more, SOC, SIP. Do you see this on the image? So this prediction says we will do many things beyond CMOS. And these many things will be analog and RF, passive, high power devices, sensors, actuators, biochips. They are all more than more, beyond CMOS, non-digital content in system in package. So they will all have to be integrated into a semiconductor circuit. On one side, you would have memory and switches, and then you would have some of these devices, and again devices working at various speed. One of the devices will be working at femtosecond, and some other device will be working in milliseconds and seconds. All of them packaged together in a system in package. So, and that system in package will enable wide range of IoT, I mean, personal monitoring, health, I mean, driving, smart energy, smart water, smart power, hybrid electronics, hybrid electrical devices, smart metering, smart sensor, wireless, wideband, all of these activities, you see, I mean, this black and sky blue, all the IoT activities. But then something in the more than more, you see, is including this flex system. It could be metal oxides, quantum dots, nanomaterial, silver, silicon, gold, zinc, zinc oxide, nanotubes, nanowire, graphene. And there you can actually design them, form structures on any type of cement surface. And switch off the other mics, Am I the only host, or is somebody, some other host who can stop? Neeraj Kumar Gupta, can you please? Okay. So, therefore, I think wide range of opportunities with large area and flexible systems exist, and that can be, as we said, for healthcare, for computation, displays, energy storage and generation, textiles, e-textile, human interactivity, I mean, again, robotics, haptics, all sorts of things can happen. So this is an opportunity where with new materials and new devices, the whole world is, I mean, at par, a level playing field. It doesn't matter whether I have had a 100-year experience or whether I'm starting today. And the devices can be, again, nano, meso, micro. I mean, they can be nano, microfluidics, biomaterials, nanophotonics, neurophonics. I mean, nano organic materials, inorganic materials, magnetic materials, spintronics, molecular electronics. All these opportunities are a level playing field. And that is what all these activity, we want to call them as large area and flexible electronics. Sorry, just a minute. Why it's not moving? So I know, I mean, today in the age of Internet of Things, things are happening very fast. This is just to give, I'm sure you're all aware, so I will not go into all of this. All this has more than doubled in the last 2 years. And we already said yesterday how broadband and mobile connectivity in the wireless networks have all got interlinked and converged, and also wide range of IoT enabled process and systems, as we again discussed on Monday. I mean, opportunities in every domain. And so whether it is enterprise, home, I mean, cities, I mean, even aircraft carriers and defense activity, everything are sort of interlinked with ubiquitous and pervasive computing. And so in a modified way, in the age of 5G and IoT, the way with this new material and devices, what all can happen with this emerging semiconductor technology and opportunity in every area, from application benchmarking, architecture, connectivity issues, I mean, cryogenic electronics to quantum information systems, or even packaging, factory integration, every area of aspect from safety and health issues. And there are huge opportunities. And that is what IRDS 2020, I mean, it's the 6th version, is calling it. And therefore we are saying, can we now look at some of these opportunities and become leaders of whatever we had lost? So it is sort of the expected smart century, this 21st century or smart community age, when everything is connected. The cyber physical systems all are connected, and where you work on the IoT and the edge computing, and especially everything working with very low power, because again, with these billions of devices, if we were to work like the way we powered systems even 10 years back, we will never get power. So there you will have to literally have systems which use no power or use energy harvesting and scavenging technologies. So this is what, and a key enabler for these type of activities is large area and flexible electronics. It's going to be a few billion, 500 billion to $1 trillion opportunity. And we can actually start working, and all we have to study is about new materials and make devices like materials, study its electrical, optical, mechanical, piezoelectric, some of these properties, or make a diode or a transistor, or use the material strip as a resistor or a conductor, and or make it as an inductor by patterning a continuous conducting strip, and we could make devices and systems. So it's an exciting opportunity with simple school physics and semiconductor electronics, and understanding all physical phenomena and the application linked, as I said, whether it's agricultural, aerospace, medical, mechatronics, no matter what your telecommunication or terahertz device. All that with new material and new devices. And therefore today we will, as I said, be speaking something about large area flexible electronics, where we could literally be at par with anybody in the world. This is just to say that how the semiconductor roadmap has said how, I mean, technology has evolved, and how many, I mean, say semiconductor systems, how many billions and trillions are being connected every year. And so, and the number is expanding exponentially. And what is the semiconductor market, which is over 400 billion. And this is just to say that how dimensions are going down every day. So we will not go into all of this, but as we said already, 4 nanometer, 5 nanometer, 7 nanometer technology products are in the market. And Intel today, I mean, though 2021, these products are in the market, and in next 5 to 10 years, they're expecting to go up to 1 nanometer. I mean, so that is the level of technology acceleration. That's what the technology roadmap gives all this information, and how people expect to go to this. So even if I don't know what I am doing, I could simply get down, download this free reports, whether I am working on reliability, whether I am working on memory, whether I am working on sensors, whether I am working on edge computing, cloud computing. I can download this report and start working from fundamentals and see where I can contribute based on my passion, so that I am working on cutting edge technology rather than something which billion people have already worked. So please make use of this opportunity. From any domain, you could be, as I said, mechanical, physics, chemistry, maths, doesn't matter. So this is just to say how things are expected to show up, and how things are moving, and newer tunnel field effect transistors are coming up, and what is the way, I mean, memory is going to go. And so for sheer lack of time, we will not go into all of this, but I am sure if you go to IRDS roadmap, you will get all this data. And also if you're working with new materials, also, it shows how we could even actually do processors with some of this new material. It shows the prediction. So not just that only silicon based processor will be there, but some of this new material also could lead to processors in the near future. And what will happen in quantum world or high performance storage, how small devices to big systems can be connected by 2023, 25. This the data gives you some input, but as I said, for the sheer lack of time, we will not talk about it, but how already trillions of billions of computers, it's a mobile phone. India alone in the last 15 years has moved from just say about 5 lakh mobile phones to close to a billion mobile phones, 1.2 billion mobile phones. Internet connectivity is already 500 million people. So it's exponentially growing every day. And therefore, this age of IoT is assuring that we can connect systems, and the connection is no more on the lateral surface, just along the flat surface, but newer technologies, newer devices are being connected vertically in 3D modeling, even in the electronic devices. So you have, three geometrical scaling, equivalent scaling, and now we are moving into the age of 3D power scaling. So we are to optimize power and give more capability. Devices are built vertically. So thus expanding the scope of work and systems that we can do with semiconductor technology and with new materials, new devices. And as we said, it will be now analog to device, digital to analog, and all of them in a combined way. So exciting opportunity for us to look at what all can be done with sensing, and then sensing combined with human interfaces. And they are saying that, say you would usually be looking at, huge amount of, data storage capability in a single small die. So which is sort of 7 into 10 to the power 28 by 2040, if we go to the higher limits. And so that are mind-blowing numbers. And of course, the associated electronic architecture is also evolving. And we already said wide range of materials and devices. We spoke about this emerging material and device, and this shared the same PPT even on Monday. So you could choose any of these device which you can work on, for which you have facility, either simulation or fabrication. But I would hope you can do both. And many of these softwares are free. Best of the world universities and companies, associations are working on this emerging material and device have open source software. If you can understand, you can even build functional blocks into them. So that is an exciting prospect in this system. So I think we need to now grab, and these opportunities, what it does is again helps us to work with materials which are environment friendly, sustainable, which is again something we should remember. And so now the whole of this evolution of large area flexible electronics or domains like vacuum nanoelectronics started off with our first interest to miniaturize the electronic valves in the 50s and 60s. And from there, to grow it on large area started with our passion first to look for alternate to bulky television. That led to, as I said, solar cells on glass, paper, plastic, which is roll to roll. And then, of course, displays today, which are becoming roll to roll. And now electronic sensors and circuits and systems can be rolled up and carried in your pocket. Are the type of things that are happening. So it's a mind-blowing transition that has happened. And we just want, so what is the difference between large area and flexible electronics and conventional electronics? Here, we are no more constrained by the size of the substrate. Anybody, can you tell us what is the largest size of silicon wafer in which companies can make integrated circuits? Any thought? See, today, very few companies can do it over, 20 inches, 18 inch or 400 millimeter. Again, a handful of companies work on slightly smaller size, which is 12 inches or 300 millimeter. Most others work even smaller at 8 inches, or in India, our highest capability is maybe literally 6 inches, and maybe one SEL Chandigarh may have 8-inch capability. So maximum size of a silicon wafer is no more than I think 18 inches or 400 millimeter. And in that, they will, because the IC die in which you have hundreds or millions of devices can be anything from a few hundred micrometer by 100 micrometer to 1 centimeter by 1 centimeter, depending on what is being made. And so they would make thousands of them in one 18-inch wafer. That is why it is very expensive. And to set up a fab with, say, even 15 or 20 nanometer today, I think we would need tens of billions of technology. And India does not have the best technology. India has is only 185 nanometer. But these large area flexible, you could actually, based on your engineering capability, do it from tens of micron to meters together, roll to roll. And you can engineer the system depending on what material, what device you're doing, with using our conventional electrical, mechanical, and other design and capability and engineering capability and understanding of physics and chemistry. And because we do them on flat surfaces, we use 1 by 1000 to 1 by 10,000 less material. And because they can roll up and be spaced, they have less space requirement, less weight requirement, lower cost, saving on material. And we can also choose the material which we use, which are environment friendly. So it becomes very, very convenient to work on such material. And therefore, we can, plus therefore, if you are going to do some electronic development with this material in your lab, you don't have to worry about environment, health and safety. If I'm working on carbon, if I'm working on zinc oxide, or if I'm working on titanium dioxide, or even silver nano powder or gold nano powder, these nanomaterials are by defect even antifungal, antibacterial by nature. So even if it is somewhere on my body, it is actually antifungal, antibacterial, unlike working on a zinc sulfide, zinc telluride, or even a sodium, which would literally burn or cause some problem, or working with hydrogen peroxide or something which would corrode my bones, some inorganic solution, or so acids which would cause dangerous problems. Here are volatile organic VOC, organic chemicals, which could again cause problem to me. These materials are far more safe and benign. You can work with them. Everywhere you have silicon, ceramics. So sand is also silicon. So if you're working with amorphous silicon and some of these new organic metal oxide molecules or metal oxides and various forms of carbon, they are environment friendly. So it's a very, and plus, as I already mentioned, so many day-to-day products we are using are based on them, but unfortunately, we don't even know that they are made of it. And so anybody, what is the device that runs our LCD display? Am I audible? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
So, you see, amorphous silicon, and now in some of the newer systems, some have zinc oxide or zinc and tin oxide based thin film transistors driving our displays. And of course, there are again organic thin film transistors also coming up, and some lighting system are essentially which drives our LCD display are CCFL lamps, which are 2 and 3 millimeter, and some of them have organic LED or semiconductor LED. So, which are not from the conventional process, but these large area flexible electronics and say RFID. Many people say you don't even have to go and touch anything. If you have an RFID with an NFC, near field communication capability, without even touching, from depending on the range of the NFC, active and passive, just passing by it, it will be counted. So all this technology has become possible because of this emergence of large area and flexible electronics. As you see, it covers every domain from construction to infra, aerospace, defense, transport, home, governance, business, agriculture, banking. So you think of it. So it started with, some of the first calculators had some of these displays, and then some touch screens. So from small size, these displays have now become so huge. They are made with on plastic, roll to roll, whether it is solar cell or whether it is a display. Lighting systems which are roll to roll are available. You can therefore hereafter just connect lighting strip wherever you want and power it with a solar panel and make it run electroluminescent devices. Of course, in our country, in the market, we don't have, but actually we can do some of them with very low technology within our labs. But we don't even teach any of this technology. but it is doable. That is the beauty. So we should be introducing this subject, teaching this subject. And I said large area flexible electronics on textile electronics, circuits to battery storage to driver electronics on paper. And as I said, flexible lighting, roll to roll. You just cut and paste them and then connect a wire. You will have lighting. Flexible displays. All sorts of things are happening in this large area and flexible electronics, wide range of medical sensors and instrumentation. So sky is the limit. But then, as we said, we are not talking, and we are talking of IoT and sensor. You just see here, it shows how, 3.8 billion is just the wearable sensor market. I'm not even talking of all types of sensor. Just the wearable sensor market is 3.8 billion. And so it has been a transition at each stage. And we have now sort of by, say 2021, we have reached, something like, in terms of various stages of technology, we are moving very fast into from the first wave technology is already spreading and even going to wane, saturating. The second and the third wave wearable technologies are happening. But on all of them, there is scope for innovation and scope for, manufacturing, scope for, secure, functionality defining. So any of us can work in this area, and it's a huge opportunity, but are we willing to take it up and work on them? And this is just to say, again, we have said so many types of sensors. This is just to give an idea, the type of sensing phenomena that we can work with large area and flexible. Whatever sensing phenomena you have seen anywhere in the last 2-3 days of presentation, you can also do with large area and flexible electronics with new materials, safer material, lesser material. Suppose today I want a thermo EMF material. India, we don't make thermo EMF systems. If I want piezoelectric sensors, we don't make them. Everything is imported. But if I could start working with polymer and organic or metal oxide materials and make, some of my own colleagues are working on some of them, from ceramics to organic. We could actually make those material and make the devices here in our lab, and also mechanical, electronics and computers can integrate do energy harvesting, energy scavenging devices. Or the same material with the modification can be, a photovoltaic device or a optoelectronic sensor. So there's a huge amount of opportunity. The red is just to tell you what all physical phenomena can be, just again a representative list of physical phenomena that can happen with large area flexible electronics. The green is just to say the type of sensors application. Base sensor. It could be from many of the combination or standalone. So the opportunity is huge, but are we willing to look at it? As we said, today the market is about 250 billion. Each one, just you see, just a display and billboard. Just imagine if all of our billboards, notice boards, are made of this flexible display with a memory which can also from remote area get update, and it works with the light in the atmosphere or the wind or the breeze temperature, and that powers the display. So how much of distributed standalone power how much you would save on billboards? It will be working standalone. It will work at lesser power than the conventional illuminated huge displays that we are putting up. 1/10 of the power and 1/10 of the cost, but that's a 20 billion opportunity. So it just says the type of opportunity in every area of this material and displays and systems that is happening in the next few years. And can you just imagine, this is way beyond India's total economy. But we are not even talking about it. We are not even teaching about it. So that is why we have said, emphasize large area flexibility and flexible electronics or wearable electronics as an opportunity for us to take on. So wearable electronics, see, this was a slightly dated projection, whereas today's projection says by 2026 itself, we will have 250 billion wearable electronic sensor market. So this is saying that how, just in medical domain alone, what are the type of opportunities? Even see, product medicine will be display, custom designed medicine will be delivered. And if I have to take 4 different medicine, depending on the dosage I want, so that I don't get a wrong medicine, it will be then and there combined, and I get a tablet which could I have, or which can even be stuck as a patch, and it will go into my body. Are the type of things happening with large area flexible electronic capabilities. This is to show how some of this medicine-based technology from inkjet printing, screen printing, and molecular fluid flow technologies are being coming, and they are being encapsulated so that it can be slowly released, even using flexible probes into my body. So these are the type of technology. I mean, are we teaching them? Does mechanical engineer talk about it? Does chemical engineer talk? Or does even electronics or somebody talking about it? Physics, chemistry, no way. I mean, none of this we are discussing, but their products already made and in the market, proof of concept being tested. So why are we not looking at it? I mean, see, it is again, say, touch screen based lighting and systems, pressure sensors with graphene, and so that you can now work on them with some of these new materials, and how they can be manufactured with simple roll-to-roll printing technology. So this is just to say that just on glass alone, so many things can be made. But from vehicle application to human usages to, but are we looking at all these opportunities? So whether for power generation, sensors, controlling power, so and as a large area flexible electronics, a complete collapsible, I mean, power generation source and communication system, all of them can be rolled up and taken on my back, and wherever I want, I spread it, get my information, get my power, charge my mobile, charge my computer, and then roll up again. And whole of aircraft has some of this technology with circuits paired, so that as and when it wants, it can be stealth, it can get information, or it can just block information. And so all this, as we have said from earlier, calls for multidisciplinary approach, bringing in application software, algorithms, architecture, circuits, devices, structure, material, manufacturing processes, I mean, and even ergonomics. So from electrical, mechanical, neuroscience, chemistry, physics, all coming together. But for this multidisciplinary approach, the new education policy gives us an opportunity. I mean, we don't have to have any of this in the syllabus. If I am teaching sensors, if I am teaching material science, if I am teaching semiconductor devices, if I am teaching image processing, signal processing, I could have an integrated assignment for my students with all of this new activity, and we will all learn together. If you make a mistake also, doesn't matter. I mean, the assignment is with the college. I mean, and every time you say repeat the assignment in 2 years and improve it to a product. I mean, so an analog circuit, physical world, instrumentation, communication, power, data conversion, control, everything is coming together in the age of sensors, IoT. So can we do things like that? As we said, we could do things for agriculture, and it could be various medical systems yesterday also, or electronics, as I said, on plastic and skin-like material, and electronic sensors for, say, oral cancer. I mean, small capsules, polymer capsules, which will be able to sense if I have some amount, what is the amount of acetone coming in my mouth, and saying, am I getting diabetes? So, I mean, you could just by looking at a pillow, you can say, what is the way I'm sleeping? Am I all right? Do I have a problem? Am I alert? So all sorts of sensors technology happening on glass, paper, plastic, monitoring kids. So therefore, you call them as structural electronics, whether you are monitoring a car, whether you are monitoring a building, whether you are monitoring an aircraft, printed printed electronics, and for, as we said, from healthcare, for smart patches for monitoring people, to electrical vehicle, energy generation, and integrated structural health monitoring, or an aircraft or a building. I mean, similarly, RFID and packaging systems are all printed electronics. Every one of them, as I said in the beginning, are billions of dollars of opportunity. And it needs all of the technology, wired and wireless technologies, to come together, and a huge amount of market. So whether it is packaging, whether it is RFID, whether it is sensors, but then do we study all of this? Is it there in our system? No. And it doesn't need rocket science. And as I said, you will see that, somebody is holding a whole set of sensors and circuits on foldable paper, and we can actually make them with screen printing, inkjet printing. And today, I mean, to make a inkjet printing or screen printing pattern with a laser-based pattern generation of 10 to 20 micron, you hardly need to spend a few lakhs to get a pattern generator which will do patterns over 200 millimeter by 200 millimeter, 20 centimeter. It means you could build hundreds of sensors and look its reliability. Use it in multiple applications. So you see, screen printing is used in conventional printing technology, inkjet printing, coating, screen printing, in wide range of application. And so this just displays so many types of application that can be made with some of this technology, and it's only growing. Every day, I mean, the technology and the capability that is growing, whether it goes into a mobile phone, whether it goes into solar cell, whether it is going into a display. So huge amount of, and in every one of them, we have opportunity for R&D, innovation, automation. So, but then are we looking at all this changing opportunity? And the best part is, again, this is to say wearable electronics and also from just on the skin, inside the body, all sorts of capabilities are happening. And these studies cannot happen just by electronics, just by physics, just by mechanical, but from biotechnology to medical people have to work together. But then are we willing to look at all of this opportunity? And touch screen sensors just from carbon, because everywhere, whether it's aluminum oxide or carbon. And when we say large area, these electronics coatings can happen on a flat surface, like when they are doing an LCD display. And some 3.3 meter by 2.9 meter or close to 3 meter is what they do in the current 10th generation. This is 7th and 8th generation. Now they're moving to 11th generation fabrication of LCD display, where, I mean, at a point over 3.3 meters to close to 3 meter glass plate is taken up, and then various size of large displays are made. Therefore, every LCD display, whether it is 30 inch, 40 inch or 110 inch, is actually one integrated circuit. Because there are millions of display points all connected together, and all of them have worked together to make sure you get one display. So on one side you have integrated circuits which you cannot see, and they have 10 billion devices in a memory or storage and or switching device. On other side you have a large area device like an LCD display, a touch screen. An LCD display of 100 inch, 10 inch is one integrated circuit. Because even if one dot does not work, I mean, the whole system gets spoiled. Nobody will buy it, and the cost will be a few lakhs. So therefore, how you can again do roll-to-roll, combining amorphous and organic and nanomaterials, and also have conventional semiconductor devices embedded in them and do roll-to-roll electronics and chip fabrication. So the technology is moving very fast. As I said, structural integrated means it could be an integrated structure monitoring an aircraft, a building, a car, or I can even monitor whole of my eye with all its electronics, so that a blind man can literally see. You can embed it into make a blind man see with some of this new technology, and use nanotechnology and nanocarbon to do electronics and connecting dots on plastic sheet. So, or some of the circuits can be drawn, as I said, roll to roll, meter to meter together. You can coat surfaces and cause transformation of material properties and wearable, stretchable electronics, and plus the new materials that are coming up with integrated electronics into it, so that you can do the structural monitoring of a bridge, a barrage, or even develop new materials which are very light, floating on water, or a material stronger than steel, enmeshed and standing on one of the softest flowers. So this is the way material technology is evolving. And so what are the material? Next, we will see quickly in next half an hour and try to complete looking at the type of what goes into this materials, whether it is biofabrication, additive manufacturing, surface engineering, tissue engineering. All of them are going together to create this material and devices. As you see here, health related devices are demonstrated, or whether whether you are doing sensors on car or an aircraft, as we have mentioned multiple times. So on a single plastic layer or a set of plastic layer, you could have a complete hybrid electronics where you could have an energy generation system, an energy storage system, a driving electronics, a display system, and its memory. All of them fab, and this will be about a few thousand devices on one layer or multiple layer structure. So this is where I think we have a unique opportunity when we bring in multidisciplinary curriculum, work in a multidisciplinary way to do affordable R&D, because we cannot invest, in semiconductor technology. Just this year, Intel has announced that they will have 3 fabs in Arizona, in Phoenix, where they're in Chandler. They're adding 2 more fabs so that they can make semiconductor fabrication affordable, because they will not get people. They don't have to invest newly in all the associated clean water, clean energy, uninterrupted power supply, clean environment, and all of that is needed to make them. And so they are investing about $10 billion. And you will just imagine the joke. Karnataka government says we have put 25 crore for semiconductor. What is 25 crore when one company, just to scale up its production, puts $10 billion? Government of India says there is a 1 billion incentive for semiconductor industry for whole of India. And then Karnataka government says we have announced a semiconductor policy. We are giving 25,000 crores. It is not even equivalent to one measurement equipment. So we don't understand what we are doing. And again, all of we professors are teaching semiconductor electronics and all the VLSI embedded system we do. We cannot apply to any project we do, only train coolies to work as coolie for somebody without understanding where the device or the product goes. But if we could move to large area flexible electronics, we could develop our own material, our own devices, our own software, even to do the simulation, because the material is mine. And as you see, the type of application, autonomous car, agriculture, packaging, autonomous robot, mobility, waste management, remote health monitoring, smart buildings, connected cars, smart homes, logistic, heating and lighting, animal tracking, wearable electronics, smart metering, pollution control, predictive monitoring, all sorts of feasibility. And many of them are in pilot stage or some have already been there. And as we said, in the age of IoT, it's a mind-blowing opportunity, so in every area. But are we willing to work on it? But then also there are some issues of security and all that. So therefore, we are better off if we can do all of this ourselves. And this is just to show that way back in 1988, we were involved in developing world's highest current density solar cell with complete indigenous capability in National Physical Laboratory, and even making integrated panels at 1/10 the cost of what the best equivalent cell was made in Japan by Sanyo. But unfortunately, nobody in India was interested to support. So we had to waste all of that was done way back. But again, now this is just to say that various process equipments related to large area flexible electronics, from screen printing, inkjet printing, extrusion machines, 3D printing equipment, microwave plasma CVD, or induction heating for linking, say, ceramics and polymers together under vacuum. All these equipments are made in India with local companies, and all of them can be scaled up for meters together activity. This is just to show that actually we can do things if you are willing. And also these are some antenna that we are involved in developing, process equipment for or nanomaterial, because see, many of the future were nano silk based, and these equipment and testing capabilities we developed in our labs or medical instrumentation. Or for example, this is a telepresence sort of, this is a robo which is standalone, it can walk. The same principle which was used to develop this in 1913-14 was used by the Wipro had set up an innovation lab in our college, then in RB College. Today has used it to develop a remote car, standalone, driverless car. That's all the principles that were used here. And this was made in our labs, and students from electrical, mechanical, computer science, instrumentation, chemical, all work together. And we demonstrated it in 2013-14. It could walk around the whole campus based on somebody sitting in the computer and managing it with a Google map. So now all of these principles went into 2018-19 Wipro's driverless car. And they are trying to move something beyond the point. Therefore, lot of feasibilities and all this can happen with materials, as I said in the beginning. And materials can be made in many ways. Conventionally, we had material processing, means casting, forging, forming, rolling, extrusion, all this conventional process. But then now we have come way beyond these conventional process, and this is how, conventionally, or even for silicon, you had to take a sand, you then, melt it, and then from a seed crystal, you extract silicon ingots, and then cut and dice them as very fine wafers, and from the wafers, you make integrated circuit. So this is for conventional materials melts. But it needs so much of energy, so much of wastage, huge amount of area. But then today you come to, again, aluminium, because we are in Orissa, we have all sorts of ores available here. But if we can understand the materials, if we can understand their bonding, if we understand and see if we can either study from simulation which bond and which electron and atom or molecule join together, and say what type of bonding do they have, and how can I design a material, you could actually start designing materials today using high performance computing. And plus everywhere, again, the key point I want to make here is working with crystalline materials is like saying working with aircrafts and rocket. Everywhere you are not going to go by a rocket. Everywhere you don't have to go by an aircraft, because to take off an aircraft has to literally run 1 kilometer. But I need to do most of the things in my next door in 200 meter, 300 meter, 500 meter, or I need to do something in another, say, 2 kilometers. But if I take off after 1.5 kilometer in a aircraft, to land again, I have to go a few kilometers and come back and again land 1.5 kilometers. So if I want to do a 2 kilometer job, do I need an aircraft? No. I'll go by car, I will go by cycle, depending on my pace, depending on the amount of luggage I want to carry or my affordability. I'll go by two-wheeler, I'll go by an auto or a Ace, Bajaj Ace. So it means you can do so many things of transport in different way, depending on the load, depending on the requirement, depending on the speed, depending on affordability. And the same thing today, all electronic devices don't have to work in nano and femtoseconds like, high storage device or a high-end processor. They can work in, all I need is milliseconds to watch a screen on TV. My sensor has to respond only in seconds to tell me what is the temperature, what is the, or it can even tell me some signal even in 1 minute and I'm happy. So that is where ability to engineer materials, bring atoms and molecule, whether they are amorphous, whether they are some sort of nano clusters, some of these amorphous materials joined together, or whether they are some more nano clusters joined together forming a specific structure, nanocrystalline, or if you add some more atoms, a few tens of thousands and become polycrystalline with repeated structure of few hundred microns to a millimeter, or is it a few millimeters to centimeters or more crystalline material? Each one has different requirement, even making the material, the type of energy, the type of process, the type of cleanliness varies. So, but our ability to now understand this material, ability to monitor the process and just make sure we only get amorphous or only get nanocluster or only get nanocrystalline or only get microcrystalline or polycrystalline, all of this engineering capability and using process helps us today to design a wide range of materials based on our application requirements. And that is where it becomes possible that I could set up a lab in my own department and do material with reasonable control to do repeatable device and actions depending on what I want to do. And it could be, as I said, elemental semiconductors, it could be compound semiconductors, it could be metal oxides, it could be organic material. Any of them can be combined and you could be working on nanoelectronics, precision engineering, working on medical related activity or communication related or sensors or huge rockets. All of these are today possible with the new materials, as I mentioned earlier, with their structure. What is the atom and molecular chain? Are they just a few set of 5 to 10 and 100 atoms amorphous, or a few thousand atoms nanocluster or nanocrystalline? Maybe a few more thousands and to 10,000 microcrystalline, or are they in lakhs and more in polycrystalline, depending on the atom? Because at bond length, bond angle, you can create materials. And the created material based on their bond length, bond angle, and total length, and the structure of the bonding, you can define its physical properties, whether it is the quantum behavior, the electronic transport, the magnetic behavior, the optical behavior. All of this can be defined by engineering these repeated structures, by controlling the bond length, the bond angle, and the length of chain of atoms, whether it's amorphous, nanoclusters, nanocrystalline, microcrystalline, polycrystalline, and based on that, material properties can vary. And the best part is, earlier for different property, we used to use different material. Today, you see the same carbon can be superconducting, same carbon can be highest insulator diamond, or the same carbon can be conducting as graphite. So you understand, you had 1 or 2 allotropes. Today, you can engineer any material with any property, and in a very clean environment based on your requirement. So that is why emerging materials are very important. And as the number of atoms, molecule combining and their surface area vary, their properties vary. When they are in smaller clusters, their ability to react or work with the environment, the surface volume ratio is huge. So they have more reactive or they are more dynamic. We can engineer more things as they become larger bulker cluster, you just see as you move from 13 atoms to 1400 atoms, the surface to volume ratio already has gone down from 92 to 35. By the time you come to 10,000, you see that it's very small, or that's why bulk material, whatever piece, the property is same. Whereas when you're working with nanomaterials and thin films, I mean, you can have each layer can change the property of the material, and that's what you use to design materials and then use them for various application based on their length and capability. So this just shows how you can engineer, I mean, metals, metal oxide, ceramics for various application. And the way we do it, again, with these nanomaterials or thin films or this metals, semiconductors, metal oxide, is broadly we would call them as two things when we are using them as small, fine layers. Either call them as thick film or thin film. If I make nano powders, I mix it with some binder, I make a paste or a solution, and I spread it on a surface, and depending whatever thickness I spread, if the property is going to be the same, I am dealing with thick film. A pre-formulated solution giving repeatable property of a material, but the thickness can be as small as 1 micron or even 800 nanometer. Or it can be 10 micron or 100 micron. Property would be roughly same. Then we are dealing with thick film-based materials and device development. But if I bring atom and molecule to a surface, glass, plastic, paper, ceramic, textile, whatever it is, and on that surface, I grow this atom and molecule, allow them to join together and form layer by layer addition and a structure of a material, again amorphous, depending on how they form clusters, amorphous, nanocluster, nanocrystalline, microcrystalline, polycrystalline, or crystalline. Then I am dealing with thin films. Ab initio, I am creating, I'm like a god on a surface of material. I am dealing with thin films. So you have now various process technologies to do that. So for the sheer lack of time, we'll not go into all of that, but essentially say that to make such things, again, you need vacuum because the environment has to be clean. You are bringing atoms and molecule at very small, one atom at a time or one molecule at a time, making them interact at a particular pressure, temperature, environment to create material. So you need typically clean vacuum, and then so therefore this clean vacuum is used to grow some of the material. Even the characterization equipments like SEM, TEM, AFM are used to study them. And the clean vacuum, again, vacuum can be broadly, for sheer lack of time, I'll not go into all of this. You can say from atmospheric pressure, then you have low vacuum, medium vacuum, high vacuum, very high vacuum, and ultra high vacuum. That is about 10 to the power minus torr, or it is actually 10 to the power 12 times less number of atoms than atmospheric pressure when you go to ultra high vacuum. So you can go to various stages, and based on this vacuum stage, again, have various ways of growing materials with different process technology. And the growth process also depends on how the atoms and the molecules flow. Whether it is turbulent flow, because atoms and molecule in huge number, like near atmospheric pressure, or slightly lower than atmospheric pressure, they are going in huge numbers, then you have a turbulent flow, and that reaction leads to some possibilities. If it is a bit more uniform laminar flow, you have another kind of possibility. Crystalline material growths are typically done with laminar flow, but then you also use molecular flow for atomic layer epitaxy. Then if you want to grow in a very controlled way, atom by atom, you could also go into molecular flow, where the molecule or the atom will not interact with any other atom because the mean free path between them is about 10 to the power minus 6 meters. So it will only interact with the vessel or the container or the substrate. So you control this flow with vacuum, and for the, as I said, the mean, well, not as I said, talk about all of this for the sheer lack of time, mean free path, and then you can grow various ways of material growth are available. Like it, it could be say called vacuum evaporation. You take a metal into vacuum and heat it. So aluminium, which normally would melt at, let us say, 1000 degrees in the environment, would literally melt under vacuum for say 500, 600 degrees. And if you heat it further, it completely melts and evaporates, and atoms and molecules come out that can be deposited on a surface. It's a simple physical vapor deposition. Or you can use a plasma to etch out an atom and molecule and get it deposited on a surface under vacuum condition. So you are calling it a sputtering. Or you could use ion assisted deposition. So various ways of deposition exist, or you could use a laser to fall on a pure material, and the intense laser light with its high energy will make a small micro spot and make it melt, and atoms and molecules can come. You could again get a deposition of these ionized atoms, so you could get even purer material. So I mean, therefore, there are many ways of this, and plus, as we said, screen printing, inkjet printing, rotography, offset printing, all of these technologies today are used for growing materials and 3D printed materials today. I mean, nano imprint lithography, actually you can do integrated circuit in nano dimension. And that is what Professor Bhattacharya was mentioning, that Jadavpur, IISCT, Shibpur, has this facility. So if you can do a design, they can help you fabricate or help you create a mask, so that you can use the mask, and on polymers you can do imprint lithography, and nano dimensions of devices and layers can be brought together, structures to make devices in polymers or other sol gel based processes. So all sorts of technologies are available. And as we said, for the sheer lack of time, we will not go into all of them, but typically, as I mentioned, we control the vacuum or the environment, and based on the environment, atom and molecular flow will decide what type of material under what temperature will be grown. And you can bring atoms and molecule on a surface and create a material. Then you are leading with thin film. If you have mold a pre-formulated solution, and that is used to grow material and devices, semiconductor or insulating layer or resistor, capacitor, whatever, you are dealing with thick film. And suppose you are doing thin film, I mean, there is broadly, as I mentioned, if it is simple physical vapor deposition, you have something called a phase transition. We have a solid, the solid on heating becomes liquid, and further phase transition, and the heated liquid becomes vapors. The vapors are carried on to a surface where it condenses, and atoms and molecules join together. Initially, there are one or two atoms, and later, as you go further, the atoms combine and the nuclei agglomerate to form smaller islands. The islands form together complete film. So thin films can be formed, say, for, as I said, for lack of time, we are not going into greater detail, except to say that this is we can today create any material. And there are multiple ways of doing it, from sol gel, solution-based process, or phase transition, solid to liquid to gas, or liquid to gases, or just gas and gas interaction and condensation, materials can be grown. And so carbon nanotube was identified, as I mentioned, they set a roadmap and they were able to go beyond. And now it uses all this process, sol gel processes, exfoliation, solid to gas, I mean, gas to condensed material, all sorts of forms are used today for whether even in carbon nanotube. So if you just take one material, carbon, as I mentioned, you could have a diamond, a graphite, a fullerene, a graphene. I mean, today all possibilities are there and they do wonders. I mean, you can also have nanocluster, nanohorns, nanopolol, corylene, so many new, by just changing the sp2, sp3 bonding nature. So whether it is only sp2 hexagonal, whether it is sp3 tetragonal, or sp2, sp3 combination, and is there, so all of this change can create new materials, and with this material you can do anything. For example, the carbon alone, you can use it in VLSI, you can use it in tribology, you can use it in touch screens. So wide range of, I mean, right from, I mean, say surgical knives. Suppose you don't have to have any more a metal knife. If you can make a 10 micron edge, a thermoset plastic, and on that you coat a diamond-like carbon coating, it is sharp enough to cut anything. So a surgery can be done and use and throw without metal. So you engineer literally materials, because today so many possibilities. So that is the exciting capability with materials. And you can grow anything from amorphous to nano. This is, for example, an equipment that I was involved in developing to grow nearly up to a meter. We could easily grow carbon films from amorphous to nanoclusters and nanostructured material. Or these are all materials, equipment made in India, where we can engineer a material or multi-layered material and a combination of anything in this for research. I could bring in a gas called silane, a gas called germane, or a gas called methane. So it means carbon, germanium, silicon. I can then create carbon-based material, silicon-based material, germanium-based material. I can bring in dopants and then cause doping. Or I could bring silicon nitride, ammonia, and or oxygen and create oxides. And so it's a huge opportunity to create. And similarly, we had provision to do multi-target sputtering. So we had used this to create a tube which could absorb and create 600-degree thermal heating from solar heating. See, create 600-degree solutions of molten metals. So by coating metal systems. So but then it can be used to engineer any material today. I mean, because we had RF sputtering, plasma CVD, and provision to change any metal or metal oxide target, and also, as we said, have silicon or carbon or germanium based coatings and dopants and all of them. So, or this is again an equipment where you could now condense, say, mix a ceramic and a metal and heat them with induction heating and create a rod. The rod could be further extruded, or you could create, say, these are ferrite magnets created by combining materials. We could even say at lower temperature combine ceramics and polymer and then extrude them to be piezoelectric thermo EMF. And all this equipment were developed locally. And this is an equipment for extrusion. So you could add solutions, carbon nanotube and all that, and you could extrude a wire or extrude a sheet with appropriate properties. You could heat it with RF and all that. And as I said, a complete equipment to yeah. So I mean, I'm not sure if you can see at the bottom a set of 4 instruments. These are essentially probe station for measuring materials, devices. Again, 3 probe, 4 lead, 3 lead, everything can be measured. And earlier, only IITs and defense lab used to have this equipment because it used to be 40 lakhs, 50 lakhs. We worked with Ambala and developed a basic 4 probe material with microscope, and we could see up to 10-20 micron precision. And this we did it for 2 lakhs. And then we also added a heating stage so that you can heat and do measurements. And later we could have also linked it to vacuum and all that. So now IIT, IAC, everybody buys from that Ambala equipment company where we developed. But what stopped them to do it for the last 40 years and then restrict everybody? So everybody could work. I mean, you could simply make a solution, dip a substrate into it with a patterned electrode and covering electrode on one side. So the electrode gap will define a device and you could measure them. And you could use such a simple 2 lakh probe station to do measurement up to -10 current, because we used a 5.5-digit multimeter. So with an inbuilt source meter. So I mean, it's a question of can we create, so whatever they say, for example, IAC has created in 100 crores, we were able to create the whole facility in 10 crores. But in 2 to 3 or 5 lakhs, I could create nanomaterial and a measuring facility and sol gel based process. We could be working on nanomaterial devices and sensors. And here you see one more equipment to measure terahertz sources, vacuum nanoelectronic devices. And this equipment, for us, it costed about 50 lakhs. But one of the only major company in the world which gives precision equipment for microwave measurements for terahertz or X-ray source and all that costs about 15 crores from Japan, called Tokyo Cathode. So we made the whole equipment in just 50 lakhs locally. So this is just to say that if we are willing, depending on our budget, depending on our capability, we could, and in this lab, from a simulation to material to device to even packaging and electrode fixing can be done. This was all created just in 2 years in, say, BML Munjal University between 2016 to 2018. Sorry, for some reason it's not moving. 1 second. So, and then we can create atomic smooth films. I'm not sure if you can see this. It says 100 nanometer. And this is near atomic smooth film at 100 nanometer. And this is a diamond-like carbon coating, which is exceptionally hard. This was the type of coating which used to be used on, say, storage, I mean, our data storage, memories in our computers earlier, so that when it rotates at 30,000 RPM, even accidentally, if some dust comes because there was a DLC coating, if the dust particle would go away from the surface at 30,000, it was like a missile going out of it, or I mean, some car going on a surface of a sheet. But then because there was a DLC coating, nowadays storage could be done literally, you could keep your storage anywhere and it would work, because they had a DLC protective coating. But this is also a coating for low K dielectric in VLSI. It is, you can also use it as protective coatings, a transparent anti-reflection coating on optoelectronic devices to allow more light to pass into the device. So all sorts of things can be done, or we made clusters, fibers. This is just to say that we made patterned devices with nanosphere lithography, where we could easily make 100 by 200 nanometer patterns. So this is some of those process equipments. As I mentioned, say this is our own designed and fabricated, locally made cluster tool. And for example, we developed carbon-based material. We could control every property. I will not bore you, but just to say that 12 order, we can change the conductivity of the material. All semiconductor devices from insulator to conductor, 12 order is good enough. And this material does not need any dopant. It only works with carbon. A very environment pure material. By changing nitrogen, helium, and maybe some hydrogen content, we could make material over 12 order change. You could make electronic circuits. This is just to say how with that material, we even developed simple thin film transistors in an inverted gate structure. It means, first of all, we make as 2 electrodes, gate and source. Then on that, drain and source. And on that, we grow a semiconductor. And on the top of it, we make a gate electrode. This is called an inverted gate configuration. And this is a general coplanar TFT, thin film transistor. So you could now, this is inverted. Gate at the bottom, semiconductor, drain source at the top. So, and this is the turn on, turn off property of the transistor. We can switch it on and switch it off. Off current is about -12. On current is -8, -7, depending on, and we could go up to -6. So 7, 8 order turning on, turning off was a wonderful capability made with. So then suppose if we can make this device in a repeatable way, we could make electronic circuit at room temperature within our lab. Integrated circuits can be made. So this is how to do that simulation. I'm sure tomorrow you will also work with Silvaco software. You already saw yesterday one of the other software for organic semiconductors. So you could do some of this simulation in your own labs, and there are even initially freeware on which you can work, simulate these devices. And then, as I said, whether it's a solar cell of amorphous silicon or TFT, and plus in India, world's largest solar cell factory was established by Moser Bayer. And so you could actually do about 3.5 meter wide continuous glass panel for solar cell fabrication on glass. And this was that whole factory layout of when we established here a PECVD tool and all that. And so this is just to say that whether it is a solar diode or a transistor, whether you want to use it as a solar cell, whether you want to use it as a turning on, turning off switch, or combining them and also with the same material making resistor, capacitor and circuits, we can do in our own labs with amorphous, organic, metal oxide materials. Depending on our capability, we can choose processes and equipment, and right from a few lakhs to maybe a few crores. But this is nowhere compared to the billions of dollars internationally people use to make systems. So, and we could actually create ecosystem in large area of flexible electronics. I'll just take under 5 to 7 minutes and finish off with this. Vacuum nanoelectronics is another interesting area where you could do next generation technology of terahertz sources, or sensors which can do precision measurements of nanoampere and picoampere, or sensors which could identify atoms and molecule for pollution control, or sensor which could be used for medical application, or a handheld X-ray source which can work with a battery. Or you could even create a whole low energy X-ray box for food processing, for extended life of agriculture, all sorts of possibility with low energy and safe technology called vacuum nanoelectronics. I'll just take to, this is again, you can do it over large area. Conventionally, I mean, all this communication systems, X-ray sources, or even the old CRT used vacuum electronics. That is, a filament would get heated, The heated filament would give an electron. The electron will come to a cathode. Or the moving to the cathode will be controlled by a set of additional electrodes. So you would have triode, tetrode, pentode to control the flow of electrons to the cathode from anode. And these were all, because of thermionic emission, huge. Even if you want to cause propulsion in rockets, you heat and ionize gases by, applying electric field, the heat, it was very difficult. So now these technology can even be today used to make electrical propulsion for a nano or a pico satellite by using just a Teflon layer as a fuel. This field emission would create electrons, strike a Teflon layer, bring out atoms and molecules from Teflon. They now come into gaseous piece. These gaseous molecules can be ionized or neutralized with another set of electron emitters, depending on what you want to do. And you could literally cause a propulsion for, a pico or a nano satellite. These are the type of exciting possibilities that come up with vacuum nanoelectronics. So vacuum nanoelectronics is nothing but emission of electron in the presence of a field from a material into free space, rather than the conventional process where you had to heat a metal and then have an electron come out of it. And because you do this with nanostructured material and at low, and the nanostructured material, you simply apply 1 volt, the field will be 10 to the power 5 if the dimension is very small in nanometer and height is about a few hundred nanometers. So what happens is very intense field at the tip. And so the vacuum nanoelectronics, therefore, is a combination of conventional valve electronics to solid state technology, microscopy, molecular engineering, all of them coming together and then causing, electrons. As I said, conventionally, if you have any circular or semicircular surface, all electrons would spread uniformly, or charges will spread uniformly. The moment you have a sharp tip, I am sure most of you sometimes would have experienced, the corner of your chair giving you a shock because it's a very dry day. Charges have accumulated and you touch it, and because you're wearing a rubber slipper or something, or you're grounded, and the chair has a insulation which prevents it from grounding, all the charges from the corner of the table or the chair, you get a shock. Or similarly, when you touch a key and a car. So this phenomena is used in a sharp point. Large amount of electrons are brought together, nano point. The field is so high that there is a probability some electron will escape out of the material into free space without even heating, because of the intense field. This is called field assisted electron emission. So just for the lack of time, we'll not go into various variations, but you can now create light sources, electron sources and ion source. So from terahertz laser, devices to free electron lasers to, lighting systems, all sorts of products and technology are possible, and they can be made over large areas. And we were also involved in developing some of this in the startup companies that I was involved in Japan. And so the products could be gas sensors, propulsion, lighting systems, which are more energy efficient than LED and can be built in a conventional bulb factory. An X-ray source which can go from a catheter directly into the body and at the desired point deliver, X-ray, biosensors or ionization sensors, which would you have an array of sensor, you turn them on at different potential, and you know that for each molecule or atom, there is a specific ionization potential. So only that specific atom or molecule will be ionized at that potential. So depending on the array and turning on potential and corresponding ionization, you can identify, a mass spectrum analyzer, which could be in the size of a stamp, and could with MEMS technology be in your hand rather than a huge equipment and vacuum that you want elsewhere, along with appropriate guttering technology and all that. So mind-blowing opportunity. Like this is that example of a mass spectrum analyzer with an array of electrodes and a gate insulator, and so a triode configuration. You could do whole of them in a stamp size material and with appropriate microfluidics and guttering. And so that by allowing a flow, you identify atoms and molecules, specifically each atom molecule in a very simple way. Or, direct electron beam lithography, X-ray sources. So as I said, for these were one of the first displays that were made. And so these displays initially started working with, started it with working with diamond, then we worked with nanocarbon, nano diamond, and we developed many room temperature materials to do such displays. And this is just to show that we can do all sorts of characterization were done. Or to create nano pattern, we have used this nanosphere lithography process. So without any mask, we could easily create nano patterns, and the nano pattern were used to generate again electron sources for X-ray emission and wide range of product. And we have patents on some of the structure. As I said, for lack of time, I will not go into detail, but it is just to say all this literally can be done here in our own environment if you are willing to work on it, develop new, and even on that material. So just by varying the surface, you see some black spots and use some yellow spot. The black spots are the spots where you have graphite-like material. The yellow spots are predominantly diamond-like material. And so what happens is when electrons come and accumulate near these black spots, there is more charging of electrons. And so when the field increases, electron escapes from the, so without even patterning or doing sharp structures, by just depositing layers of material of nanocluster carbon and nano diamond, we were able to create electron emitters. And this is a room temperature nano carbon grown lighting system. Of course, it is sketchy, but then it works with less than a milliwatt of power, and it already gave a few hundred lumens of light. And if with further optimization, I'm absolutely sure these lighting could have been, and this can be made in, as I said, our own bulb factories. So a lot of exciting and these are again better quality bulbs made from field emission, again using just milliwatt power compared to the watts of power used by LED. And they are very bright and they can last 10 years without any problem. And again, these are a similar experiment activity measured in our labs in India. And we had also worked on developing X-ray generators. So I think this is just to say all sorts of applications are feasible. And we have already gone through all of this. And yesterday, Dr. Dikshit mentioned the same process can be used to actually grow diamond with further extension. So these are the nano diamonds grown in Delhi from a microwave plasma CVD. So you see, and if you could grow them in thinner layers, you could grow ultrasound, UV sensors. Instead of growing a diamond, you stop them at few hundreds of nanometer or few tens of nanometer, or even, so you could literally grow UV sensors with the same material rather than making a diamond. So exciting possibilities with new material, or as I said, again, student activity led to, I don't mind repeating them, like satellites, solar car, UAVs, which won award from NASA. So it's up to us to make these things happen. A driverless car philosophy and all of this, we hardly spend a few lakhs from assignments and projects, made some progress, spoke to companies invested. The institute hardly even 3 years, if it had instituted 20 to 30 lakhs, it was a 3 crore project with companies putting in money as we showed progress. So whether it is a satellite, whether it is a solar car, which ran 3,000 kilometer rally, we can do things with students. Since an agricultural equipment, again, we did due diligence for a startup and development activity that it saved 25% of fertilizer, 30% of water, and 20% excess yield in any agricultural field. By using a handheld machine for sowing, you could ensure all of this process. And I have already shown these things. So for, accidentally, or these are piezoelectric materials. Again, we have made this for some company, and also we have made electrodes for ECG, EEG, or you could use it for brain computing study, and electrodes made on polyamide and PDMS sheets. So therefore, if we can link all of this activity into student assignments and projects, I think the way we can do things is mind-blowing. Product process development can happen. For example, everything about the automotive can be seen here. Student can work on everything and even understand it with the software and video display on as to what is this functionality. Then they could design alternate material, alternate sensors, alternate actuators, alternate circuits. And then every drilling, milling, as I mentioned in the first class also, linked with tachometer, energy dynamometers, and flow controllers, we could automate whole mechanical process. So I think, and many of the sensors can be made with these new emerging materials. The student activities led to, as I said, race cars and various sensors. So can we now open up our mind and looking at new opportunity? And just see, whatever I showed facility in BMU, students who worked on that on the electrical car and from the battery reassembling, they developed a battery company. And these are the batteries that they have made. This second life battery is 1/3 the cost of conventional electrical battery, a lithium ion battery, and can do even more efficient high power delivery, peak power delivery. And they have also used the waste material, and from our facility created a complete capability. And today a recycling facility is being set up so that we can recycle the material and use it again to create new batteries. And so the large area, flexible electronics, IoT, industrial automation are all unique opportunities for us to work among ourselves and our colleagues and create mind-blowing opportunities. As we said, if you might have listened to what Dr. Samir mentioned, he gave hundreds of examples of what you could do as automation and industrial IoT enabling for a local MSME. I mean, if you had listened to Dr. Renuka Prasad, he gave a whole gamut of capability of starting use and throw products and small product technology, and also understanding how complete end-to-end system within a small capability if we work together. And now hope we have shown how large area flexible electronics, vacuum nanoelectronics again give you an opportunity to do new materials, sensors based on them, or their associated energy generation and harvesting devices, or even whole circuits can be fabricated based on this device. So I again repeat, it's a huge opportunity for innovation and transformation. So I want to call this innovation transformation process as a device. I mean, it is, can I include the desirability, inclusivity? I mean, whenever I want to do a product or a process, I just need to think from the beginning, is there a desire to work on it? Is there a desire for such a project? So if any way I look at it, in inclusivity, can I work as a team? And also can I look at saying that I will also enable large number of people? Then is there viability? I mean, economically, is it viable to do it? And then, of course, whatever we do, we want to be sure it is sustainable. It does not cause any damage. And above all, we start off with effective feasibility. Will it even work? That is the first step. But so you combine them, you say you can cause a transformation through this device for sustainable innovation. And we could, with a multidisciplinary approach, we can truly solve any problem. And later in the afternoon, some of my colleagues will be showcasing how by design, the university has created about 20 odd centers. Either you want to train somebody into skilling and then link it to fundamental first and second year subjects and start using them for small projects, or you want to actually design big products for industry or subsystems for industry and manufacture, you can use all of these 20 odd labs in our campus to do product development, give student a skilling opportunity, or even faculty can come here and do train the trainer opportunity. Faculty or technical staff from other colleges can come here because our trainers are trained and certified. They can make use of it, get themselves trained, and depending on their capability, as you saw automation, where Dr. Samir showed that you could do a whole automation lab with a 35,000 kit and understand any automation. Or you, if your institute has money, it might put 20 lakh, 50 lakh, 1 crore, whatever, depending on the money, set up a Bosch Rexroth or Festo lab or Siemens lab or whatever. So, but then we can help either for training and skilling or for joint collaborative product process development. And I am happy to say by design, all this has been created, and across the globe, I can assure you that, homogeneous team, people from the same domain, initially they may look like they are working very well, but then the moment they come to certain level, they will saturate. Whereas when a diverse team come together, initially they may be a bit more confusion, but multiple times it has been repeatedly shown that a diverse multidisciplinary team with different points of view, when they come together and work, they're always more effective if they're well managed in delivering product, process, and solution. So this whole domain gives us a unique opportunity for us to leverage national education policy and the changed experiential learning and project-based learning to leverage the same and work on a process or system to develop new product process solution. And sky is the limit if we are willing to open up our mind. And large area flexible electronics or vacuum nano electronics is again part of that, again an emerging area where it is a level playing field for us to be at par with the best in the world if we can put some effort over 1 or 1.5 years and start developing product, process, solution, integrated circuits, functional blocks, sensors. Anything can happen. And thanks for your patience listening. If at all there is a question, I'm happy to answer, but generally maybe lunchtime and I see general people are taking in information and maybe they will think it over and later come back. But thank you. I'll stop here and I'm happy to take any questions, if any. And also, as we said, we are willing to work with anybody to setting up labs or setting up facility or even discussing on enabling things. Any of our colleagues will be happy to work, or if you have expertise and we don't have, we are willing to learn and also work with all of you if we can jointly send project proposals or anything. So thank you.
Thank you, sir. It was a very nice presentation. We were, as always, very encouraged. So with your enlightened talk. Now I'd like to request participants if they have any question.
Okay, I think we are also next talk is there soon. So if they want a few minutes break before they come back. So I think, thank you once again.
Okay, thank you, sir. Now we will be proceeding towards our next session. The topic is ultraviolet optoelectronic devices and will be presented by Professor Anirban Bhattacharya from Calcutta University. Professor Bhattacharya, are you present here?
Yeah, he should be here in a few minutes, I presume.
Yes.
Yes.
I think he's yes, sir. Welcome, sir, on this session. So before going into the talk, I'd like to give the introduction of Professor Bhattacharya. Professor Bhattacharya completed his BSc in physics from University of Calcutta. Then he completed MSc in electronic science from University of Calcutta. Then he did his MTech in material science from Indian Institute of Technology, Kanpur. And then he completed his doctoral degree in electrical engineering from Boston University, United States, in the domain of electro-optics. Now he is working as the assistant professor in Institute of Radiophysics and Electronics, University of Calcutta. And his current research interest is in the domain of growth of semiconductor epitaxial films and nanostructure and development of optoelectronic devices based on them. So now I would like to request Professor Bhattacharya to initiate his talk. Over to you, sir.
Hello, can you hear me?
Yes, sir. Yes, sir.
Good. So let me try to share my screen. Could you allow share screen?
Yes, yes. Yes, sir. Now you can share, sir.
Okay. No, it doesn't allow me again. See, I am in two places. Can you see me?
Yes.
Here, and then I am also in another place, which is going to be the place where I'm going to share. Can you see me? Anirban?
Yes, yes, yes. Yes, sir. Can you check, sir? I have made you co-host.
Yes, it's allowed. Good. Good. Can you see my screen?
Yes.
Good. Thank you. So I will start. Is everybody ready?
Yes.
Good. So today's talk, which I have prepared, is on ultraviolet optoelectronic devices. Now, if you will excuse me for spending a few minutes or a few seconds on the slide. The opening slide is a picture of our university, the University of Calcutta, and you can see the name, University of Calcutta, also in Bengali. It's called Kolikata Vishwavidyalaya. And I'm from the Institute of Radio Physics and
Sir,
Electronics.
voice is not audible, sir.
Hello, can you hear me now?
Yes, sir. Now,
Okay.
okay, sir.
So I just have to pick up the microphone apparently. That's good. Whenever you have a problem, please let me know because I cannot hear myself. So I am from the University of Calcutta, which picture you can see like an old colonial building. But my department is the Institute of Radio Physics and Electronics. So that is where I teach and we do research. So the first slide I have is who am I? Because unless you know me and what we do, it is difficult for me to try to explain what we are working on and about optoelectronic devices. So I am from the Institute of Radio Physics and Electronics, University of Calcutta. Also, I am associated with, we are from the Center for Research in Nanoscience and Nanotechnology. The Institute of Radio Physics and Electronics is the oldest institute that teaches electronics in India. It started in the 50s. And the Center for Research in Nanoscience and Nanotechnology is very new. It's about 10 years old. It hosts all our fabrication facilities and our growth facilities and characterization facilities. So that is where we do the work. So our research interests are, there's a whole lot of things. And you can see the first point is 3-nitride optical and electronic devices. So that is exactly what we are going to talk about. So the topic for today is the first bullet in my research interest. So 3-nitrides are nothing but, as we will talk about, materials which are semiconductors. They are alloys of gallium nitride, aluminum nitride, and indium nitride. And we will talk about that. And also, if you look at the second bullet, it talks about molecular beam epitaxy. Now, that is something interesting, and we will try to explain. This is a fabrication technology that is used in the optoelectronic fabrications. And then we talk about some physics and things like that. And current focus, if you look at the current focus, the first bullet there. Yes, can you hear me now?
Sir, your voice is very low. Please.
Is it? I am shouting as much as I can, unfortunately.
Due to some problem in audio, sir. That's why I think.
Okay. Some problem in audio. Let me check. Hold on. Just a second. So can you hear me better now?
Yes, little bit better, sir.
Okay, good. So I will try to shout louder. Hold on just a second. Let me try to do something. So can you tell me one thing? Is it echoing or is it just low?
Just
No,
low,
sir.
sir.
It's okay now.
Now it's
Somebody,
okay, sir.
It's
now it's
okay,
good.
sir.
Okay,
Now
so we
it's
will
okay,
continue.
sir.
Good. So we will continue. So what I was saying is, if you look at the current focus, now the first bullet of the current focus is UV LED for white lighting and water purifications. Now that is what we are going to talk about today, mostly. So the two topics that are going to be covered today are 3-nitride optical and optoelectronic devices, and then the molecular beam epitaxy of 3-nitrides, and UV LEDs for white lighting and water purifications. Now, there's also going to be a little bit of talk on, if you will go to the third bullet from the current focus, it says solar blind photo detectors. Now, that is also another optoelectronic device we are going to talk about. Okay. So based on that, let's me go to the next slide. And yeah, so my primary expertise is in this humongous, giant, complex equipment. Now, what it is, we will talk about later, but right now, as you can realize, and I would like to stop for a few seconds to describe it, it's shiny and complex. And yeah, complex is one word for it. So this is what we use for our work, and it is hosted, as I said, at the Center for Research in Nanoscience and Nanotechnology, University of Calcutta. And we will talk more and more about this as the work progresses. I just want to show you that sometimes when we do, talks to a general audience, we try to simplify things, and diagrams we use diagrams, we use basic equations, and sometimes the impression we give is that things are simple. The answer is no, things are not. Things are complex and things are technologically pretty heavy. So that is why instead of doing that, I usually start with this picture, trying to show people that yes, I am trying to make it as simple as possible for explanation purposes, but things itself can be quite challenging. Anyway, so we will start. How the talk is arranged? The talk is arranged in. So we will first start with light emitting diodes, just LEDs, and see how they are, how they started, their history. And the reason I talk about history in an FDP program mostly is because, we lose track of history. We lose track of people. When we do research, we read in books, we talk about devices, we talk about transistors, we talk about detectors, we talk about the internet, we talk about IoT, we talk about many things. But what we lack sometimes is the history, and that each of these are the work of, hundreds of years of slow progress. And there has been a very large number of very, very important people, very smart people. And we are essentially sitting on their shoulders, so to speak. So it is important to give them the due respect when we discuss such subjects. So that is the introduction part. And then we will talk about ultraviolet emitters and why are they useful and what is the current state of research. And then we will talk about some of the technologies that are necessary to make them. And then we'll do the same for photodetectors. So it's a similar kind of a talk for everybody, for both the topics. We will talk about why they are useful, and then we'll talk about how to make them. And when we say how to make them, I do not talk in global context. I talk about how to make them within our so-called research ecology. That's the story. Okay, so here we go. Let's start with the introduction. And as usual, we start with something very, very fundamental. So civilization started with the building of the fire, that we know. So that is how human beings started, and that was 420 million years ago. And the fire gave us warmth in the winter and light. And yes, we stopped fearing the night. We could sit around the fire and we could discuss, and thought processes started. Because the daytime, I'm assuming, was spent in fighting and hunting and doing all the practical things. And the nighttime, we spent, I'm assuming, envisioning, I can think back, probably discussing. And no civilization can progress without discussion. And so that is how things went. And that happened till about 200 years ago. And then Humphrey Davy in 1808 created the first incandescent light. So we can attribute to him, the honor of saying that he started the revolution that leads to UV LEDs today. So incandescent light by passing electricity through a platinum wire. So this is what it looked like, at least in portraits, 1808. It was neither bright nor useful. We were not talking about lumens at that point of time. But it was the first light artificially created. And Humphrey Davy, among other things, also did other things, like he discovered calcium, magnesium, strontium, and barium. So, yeah, I mean, these people did a whole lot of things, and we could not. Now, this is another topic that I keep talking about whenever I talk about FDPs, that you cannot pigeonhole science or research or teaching into electronics engineering or physics or chemical technology, or the way we pigeonhole subjects. And in reality, it is an expanded universe where you do many things. And this guy, he discovered calcium, also made the first light. So was he a chemist? Was he a physicist? We cannot pigeonhole things. And another 70 years went by. And then Thomas Edison, he patented first in 1779 and a year later in 1880, and began commercializing his incandescent light bulb. So it lasted 14 and a half hours, which was huge for its time. And that is the patent. And even today, these things are useful, even though we are slowly phasing out incandescent light. And so Joseph Spawn, he's patented his light bulb in England. And together they formed General Electric Company, GE, which still exists today. And here you go. Edison, of course, is very interesting. Just a little bit of history. He was born in 1847 in Ohio, Milan. Very interesting. He received little formal education. And he left school in 1859 to begin working on the railroad. So, a person with little formal education. And by the time he died, he had amassed 1,093 patents, 389 for electric power and light, 195 for the phonograph, 150 for the telegraph, 141 for storage batteries, and 34 for the telephone. Again, he received little formal education. So the question is, the question is pretty obvious. So how did he do it? Apparently, he had a laboratory, and a newspaper article printed in 1887 stated that in his lab, he housed 8,000 different kinds of chemicals, every kinds of screws, every kind of needle, cord, wire, and he had hair of humans, horses, hogs, cows, rabbits, goats, camels, silks, shark's teeth, whatever you needed, he had it in his lab. So that is quite interesting, because apparently you do not need formal education. You need a whole lot of brains and a whole lot of work and a whole lot of stuff to get 1,093 US patents. I hold one US patent in my name, and I was very proud of it. And I was wondering, where can I get my other 1,092 patent? And I realized that, unfortunately, unlike him, I had many years of formal education. So probably that leaves me out of the race. So the first point, light from a semiconductor. We're down to LEDs now. Light from a semiconductor. Light from a semiconductor started in 1907 from English experimenter H.J. Round. He was working in the Mercury labs, and he had a crystal of silicon carbide and a cat's whisker detector. Now, that is a picture of his discovery. Now, if you look at a cat's whisker detector, it's simply like a spring touching the crystal, and there are adjustments. And he wrote a paper, and I have to put the paper there. It's just a few paragraphs, and that is the start and the end of the paper. So if you go through it, it just says, during investigation of this, this, and this, I applied a voltage to a crystal of carborundum, which is silicon carbide, and the crystal gave a yellowish light. That's it. I mean, that's about it. He didn't know why or how, but he says there seems to be some connection between the effect and the EMF produced by the junction of carborundum and another conductor. So he says, okay, it's probably some kind of a junction effect. That's all we can say. So that is the starting of the semiconductor diode, and we move from there now. But before we move, I just wanted to put in one slide, very interesting slide. We have a cat's whisker detector, right? Can you see that? Like a spring and a touch and a crystal. And so who holds the patent for the cat's whisker detector? Apparently, this patent is from somebody we know. So Jagadish Chandra Bose in 1901 patented the cat's whisker detector. Of course, he was not doing LEDs, he was doing detectors and radio waves. But yeah, we have our name attached to it as well, which is something that I'm very proud of. Yeah. So the detector was to galena, which was lead sulfide, and that was used to detect microwaves. Now, coming to LEDs, the first person, and I will drop history in a few minutes, so bear with me. But it's important to note that the first person who really worked in the light emitting diodes was a person called Oleg Vladimirovich Lozev. He was a technician in several laboratories in the Soviet Union. And again, like somebody we talked about already, he did not receive any formal education. And he published about 43 papers and was granted what was equivalent to patents, because in Russia they didn't call them that, they called them something else, but 16 patents. And in the 1920s and the 30s, he correctly linked the emission of light from point contact silicon carbide to the formation of a diode. So he actually did the research and moved the thing forward to what we call the light emitting diode. The diode part came into the picture now. And he linked it to a quantum mechanical phenomena and called it the inverse photoelectric effect, which is what he called it. But he also did something very interesting. He filed a patent called light relay. And in 1927, he proposed the invention that the phenomena of luminescence of a carborundum detector consists of the use of a detector in an optical relay for the purpose of fast telegraphic and telephone communication, transmission of images and other applications when a light luminescence point contact is used as the light source connected directly to a circuit of modulated current. In other words, he talked about optical communications in 1927. So, yeah, in 1927, he predicted and he talked about optical communications. Unfortunately, and this is unfortunate, he died of starvation in 1942 at the age of 38, among others, during the siege of Leningrad by the Germans during the World War. Nobody knows where he was buried. So that with him was buried the research on LEDs in early part of the century or the last century. Until there was a huge revolution and we know all about it. And see, today we are saying that only LED street lights in Bangalore by 2021. So there has been a huge change. And how did that happen? It happened over time, but what I'm trying to say is we should not forget the initial pioneers who lived and died for progress of research and science. So enough of history, and let's move on to a little bit of basic sciences before we move on to technology. Just in case somebody is listening, can you hear me now? Am my voice audible?
Yes, sir. Yes, sir.
Yes.
Good,
Yeah.
good, good. Thank you. Thank you. So a little bit of history is done, and now we are going to move into a little bit of science. So story starts with semiconductors, something which is very boring, but something which everybody knows. Unfortunately, this is how it starts: the conduction band, the valence band, and the band gap. And we have here at zero temperature, the valence band is empty, the valence is filled, conduction band is empty, and then at room temperature, there are some holes and electrons because of thermal generation. This is all basic. And then you have under non-equilibrium condition, if there are excess electrons and holes, they combine and generate light. And of course, the light depends on the band gap. Now, that is the only story that we need to talk about, is the band gap. Now, these are semiconductors. What are the important semiconductors for light emission? And there are whole list. The binaries are the gallium arsenide, zinc selenide, gallium nitride, gallium antimonides, and then there are ternary semiconductors, which are alloys of the two. And there's AlGaAs, there's InGaN, and then there are quaternary semiconductors. So we are looking at the periodic table of elements at these: boron, carbon, oxygen, aluminum, silicon, phosphorus. So these are the major players when it comes to the optoelectronic devices. And if I am about to say something which is interesting, is that all of them are major players when it comes to optoelectronic devices. And why is that? Because it depends on what band gap you want. So if you look at these materials, they cover the entire range from infrared to ultraviolet. And since we are going to talk about ultraviolet LEDs today, now let us look at the various semiconductors that are useful for that purpose. So we can see zinc sulfide, magnesium sulfide, magnesium selenide. Yes. And if you look at it, you have the other ones, the gallium nitride and aluminum nitride. And what we are going to talk about today are alloys of gallium nitride and aluminum nitride, which are the three nitride materials. But of course, you are more familiar with the gallium nitride and indium nitride, which is also a three nitride material, but that is for the visible light. If you can see the graph, I have highlighted where the visible part is. And the visible part goes through the alloys of gallium nitride and indium nitride. Now, these class of materials, aluminum nitride, gallium nitride, and indium nitride, they cover the range from infrared, the communications wavelength, the visible, the shallow or the near UV, and the deep UV. And they have been with us for 25, 30 years now. And they have been studied to death, so to speak, for the last 30 years. And yet, these materials can still fit into something which we will call novel materials. Why? Because we hardly know them, despite so many years of research. They're useful and yet unknown. Why? We are going to talk about a little later. But this is the most important point of these class of materials. They have the combination of being very, very useful. They have a whole lot of potential. They have been studied for 30 years, and yet we hardly know them. We know their physics very little, so to speak. So I will show you why during this talk. And so we start with the optoelectronic device part. So before we go anywhere, let's look at a white LED. That's something that you see everywhere. It's also an optoelectronic device, and I will show you why. And we will go from something which we know to something that we do not know. That's always the case. So I thought, okay, people know about white LEDs. They know exactly what it looks like. And so we will start with that. So this is the white LED. If you look inside, see, it's a transparent shell and there's some sort of a metallic structure inside. So we look inside and we find there's a dome, which is made of epoxy. And dome is, of course, to collect the light. And then there's something called a lead frame or lead frame. The lead frame is the frame onto which the leads are connected, the cathode and anode are connected. And onto one of them, of course, the chip is placed and then bonded with wire. Now, let's look at how you get white light. The white light, of course, the easiest way and the most simple way is to use a blue LED. And if you use a blue LED and then coat it with some sort of a yellow phosphor, then the phosphor, it converts some of the blue light into yellow light. And then they recombine, they additively combine the two colors, and what you get is white, but not a very good white. The quality of white is very, very poor. So if you take a cheap white LED and shine it on the wall, you probably can make out that some of these LEDs, the white, has different kind of colors. Some of them look a little yellowish, some of them look a little bluish. It's simply because the original part was a blue LED, blue light emitting diode, and some of it was converted to yellow and not very efficiently, not very effective. So for the cheap ones, you have a problem of something called the color rendering index. The quality of the white is very poor. Now, there is, of course, another way to do this. You could start, instead of a blue LED, you could start with an UV LED and convert the UV light using a phosphor to white light. At that point, of course, the quality of the phosphor is well understood and is well known. Why is it that? Because we have always been using it. See, the compact fluorescents, the tube lights, so to speak, they are exactly that. They are a UV generator and a white phosphor, which converts the UV to white light. We could do the same using LEDs, but for that you need efficient UV LEDs, and that is where we are still lacking, as we will talk about. So, if you look inside the chip, of course, can have various configurations, and that is the most basic. As I said, it's a diode, so you have a light emitting part and then two contacts, as you can see. It can also be more complicated structures. The connectors can look very complex or even more complex. And why is it that we have so many different geometries? And the reason for that, even though the basic is the same, you have two p-type, two contacts, one on the p-type, one on the n-type. The geometry are used to distribute the currents evenly, to reduce the device heating, and to maximize the light output. Which is why, can you see that the electrodes on top are long and thin? Long because you want to distribute the current evenly to all over the chip. Thin because you do not want to block the light from coming out. So, long and thin electrodes on the surface, we'll talk about it again, as I keep saying, a little bit later again. So that is what it looks like from the top, the chip. Now, if you look at it from the side, it is a basic PN junction, fundamentally well understood. Electrons holes are injected, they recombine in active layer. But as I said, It's not as simple as that. Why? Now, let us look at the cross section of the diode. So, this is the cross section of the diode. Now, we have, as I said, made these materials using the group 3 nitride semiconductors. Now, the group 3 nitride semiconductors have gallium nitride, aluminum nitride, indium nitride, and all of them are in use here. They are deposited onto a substrate called sapphire. Why sapphire? Sapphire is transparent. That is the one at the bottom. And then you have the gallium nitride, which is the red, connected on top. So first layer is of the N gallium nitride, and the last layer is P gallium nitride. So okay, it's a PN junction, perfect. But there are a whole lot of layers underneath, in between. And why is that? The light output comes from the purple. So if you look at the purple, you see that there are InGaN, so alloys of indium nitride and gallium nitride, and there are two layers of that. The N type is indium 0.5 and gallium 95%. And then there is a purple one, which is I, which is indium 43%, gallium 57%. And then the P starts. But again, see that the P is not gallium nitride. P is an AlGaN layer. So the alloys of gallium nitride and aluminum nitride. So why do we have so many layers? So these are called so-called current blocking layers. So let us assume I am an electron and I am traveling from the N type to the P type. So I would go upwards, and there is a hole traveling from the P type to the N type, traveling downwards, and we should meet and we should recombine. But what if we do not meet? We overshoot. So in order to stop the electrons from overshooting, you have the P AlGaN, and in order to stop the holes from overshooting, you have the InGaN. So these are the electron and the hole blocking layers so that they can recombine exactly in the middle. So all I'm saying is these are complex layers. So even the basic semiconductor LED has many, many layers. So even the basic semiconductor LED has many, many layers, and these layers are deposited on top of each other. Next question is, how do you get so many layers? How do you control their composition? How do you know it's 43% only? How do you know it's 10% or 5%? So the control of composition is very, very important. Could you hold on just a second? Hello?
Yes, sir. You are audible, sir.
Good. And I can move my hand also. Okay, good. So the question is, you have various layers. Each of them have a very specific composition, and you have very specific thicknesses as well. So the question is, technologically, how do you make them? How do you make them of a particular composition and of a particular thickness? Now that is the question that we are going to talk about in the next section, which we will talk about the technology. But first, I would like to point out that even the basic LED that you see on your cell phone, or you think is simple has many layers, and each of these layers have very specific composition and very specific thickness, which must be met. Without meeting, you will not be able to get the light. Okay, so with that background, let's move on to what we are going to talk about, the ultraviolet part. So here finally we are back to where we are wanted to go to, the ultraviolet optoelectronics. Now before we move on to ultraviolet, so the spectrum that you see covers the visible, the infrared, and the ultraviolet, and the UV part is broken into UVA, UVB, and UVC, and each of them have various applications. So as I said, the first part would be the applications. So UVA is usually taken to be from 315 to 400 nanometers. Now that is used for curing of polymers, adhesives, coatings, and detection of fraudulent currency, identification. So if you go to a bank, you sometimes see that there is a little bit of a UV lamp, and people would place currency notes or other certificates under it to see it glow, to see fluorescence. So that UV light is the UVA. And then there's UVB, which is from 280 to 315 nanometers. And that is for medical light therapy, forensics. And then the UVC. The UVC is shorter, and this is used for water purification and sterilization. So if you are like me, most people in India living in urban places have something called a water purifier in their kitchens, and they are more often than not powered by UV lamps. And you connect your water supply to there, you turn it on, and there's a jingle, there's a sound or music, and then you wait a few seconds, and then the water starts pouring. Now, what is interesting is for that, the purifying agent is a lamp, mercury lamp. Now, mercury lamp obviously is fragile. It has mercury in it, and mostly it has to be powered by plugging it to the wall. So what if you had a power cut? And power failures are not uncommon. So you will not get potable water in that case. Also, it has to be connected to the wall. It is immobile. It cannot be taken with you, things like that. So that is a problem. And we are trying to solve that problem by making something called ultraviolet light emitting diodes. So for UV LED, the market size now, obviously, are there takers for it? So you have now some sort of a projection that was made by some company, and the y-axis is in millions of dollars. And the important point is they are projecting that UV LEDs are going to have a huge burst of applications. Some of it is UV curing, as I said, but also there is UV purification, disinfection. And then there is something called new applications. Now, what are the new applications? We will see what new applications are there. And a funny part is, one of the new application that wasn't envisioned before was surface decontamination for the COVID problems. Now, as you know, in order to decontaminate surfaces, you can use UV light. But then UV light has a problem. You cannot shine it on your hand without, running the risk of cancer. But recent discoveries have shown that if the wavelength of light is short, around say 240, 230 nanometers, then the penetration of the light into the human skin is very, very short. It does not really penetrate past the dead layer of the skin. So you can safely shine it onto your hand and disinfect your hand. using that. Of course, the downside is there are no commercially available LEDs or even lab-based LEDs that have the particular wavelength of emission. So that is like a mad rush. People are trying to make these devices work. And so the so-called new applications that they projected in 2015 has now really gone up much higher. And there's a huge amount of push to get UV LEDs working. But, problems are there. And the problem, of course, we will come back to this story again, that the problems are mostly the fact that we really do not know the gallium nitride, aluminum nitride material system very well. Unfortunately, that is what it is. But we are learning every day, and there's a whole lot of research going on. And I will slowly now go into what is the current state right now for UV LEDs in the world. And this is still a little older. Now, if you look at the graph, it talks about something called external quantum efficiency. It's basically the ratio of photons to electron hole pairs. So, if you look at the blue near the 400 nanometer mark, the devices are very efficient. They are, 80%, 70% efficient. But as the wavelength gets shorter and shorter, there is a decay in efficiency. At 240, the efficiency is like 0.04%, which is not good enough for applications. So this is where a whole lot of research is going on. When I show this slide to people, I always ask, so why do you think there is a little peak around the 280 nanometer mark? See, the efficiency has gone down from, say, 400 to 320, and then gone up again, and then gone down again. Is there a lot of physics involved? The answer is no. What is involved are dollars. The 280 nanometer is the most efficient wavelength that can be used for purification of water. Why? Because shorter wavelengths than that do not penetrate water, do not go through water very efficiently. And longer wavelengths than that do not disinfect very efficiently. So people have really pushed on that one particular wavelength, 280 nanometers, and you have, as you can see, huge number of players. They are commercials, they are universities. You can see Sandia National Labs, you can see Mitsubishi, LG, Dowa. So everybody is fighting to get into this game. Whoever makes an efficient 280 nanometer light is going to be the king of the hill for the next several decades. So this is the story that we now have, is the current state of affairs. And based on this, we are going to now talk about technology. So, as I said, applications are in water purifications, but also in biomedical applications. Cancer treatment is a big area, and then fluorescence spectroscopy and so on and so forth. We will talk about it, the detectors part, when we come to the detectors. And then there are also applications for modulators and waveguides, because the UV is a very important area of the spectrum for communications purposes. You can pack a whole lot of channels in there. Wavelength is very short. Unfortunately, UV gets absorbed in the atmosphere. So in the communications area, there are two applications for UV communications. One, in which you can have very high data transfer rate, but that is between satellites, satellite to satellite communication. That is above the atmosphere. And the other one is for covert communications. This is when you do not want people to be able to eavesdrop into what you are communicating. So this is for short range communications. It is like you are entering a building and you want to communicate to your colleague who is like 3 feet away, but you cannot speak because people will overhear you. You can use UV light as the communications system, because UV light will decay beyond 10 feet. So whoever is there on the other side will not be able to see what you're talking about. So that is very, very important for many, many strategic applications. Okay, so that is about the communications part. Now, as I said, even the basic LED requires many layers. And each of these layers have to have a very, very specific wavelength, that is, a very, very specific composition, and a very, very specific thickness. So, how is it done? Now comes the technology. So, there are many different methods. There's something called the halide vapor phase epitaxy, and there is a more commercial metal organic chemical vapor deposition, also known as MOCVD. But today I'm going to expand a little bit on the technique that we use, and that is called the molecular beam epitaxy technique. Okay, so we start from there and let us see how the MB works. So, starting point is you take a strong steel chamber, okay, a steel chamber. It looks like this. Let us assume it's made out of steel, it's strong, and you mount one more little chamber inside this strong steel chamber, like that. It's connected to the wall, pointing in one direction, and so it is a chamber within a chamber. And you fill the inner chamber with some material, gallium, aluminum. Remember, algan, algas, or ingan, they are all compounds of gallium and nitrogen, and then alloys of two of those compounds. So alloys of gallium nitride and aluminum nitride is algan, and so on and so forth. So here you go. You fill it with that, and then you wrap it with. Here you go. You connect a vacuum pump to the chamber. Now, what will happen if you connect a vacuum pump to the chamber? You are going to pump out the gas from inside. If you pump out the gas from inside, what will happen? The molecules from inside have reduced to as low as possible. So you have the inner chamber filled with the liquid, outer chamber is mostly vacuum. Then you have reached the vacuum. You put some heater around the smaller chamber. Yes. And you start it. So what will happen if you heat up the gallium? First, it will actually gallium is liquid at room temperature, so it will evaporate and form a vapor. So now the status is you have nearly vacuum on the outside and vapor inside the chamber. Now, if you open a hole in the inner chamber, you will generate something called a molecular beam. So that is the first point of the molecular beam epitaxy process, how to generate a molecular beam. Now, why is it a molecular beam? Why not smoke? Because there are no molecules outside. The gas molecules have been pumped out. So the distance these molecules travel between collision, which is called the mean free path, is so high, it is longer than the dimensions of the chamber. So one gallium vapor molecule will travel the length of the chamber and hit the wall if you let it, before it collides with another molecule, air molecule. So it will travel in a straight line like a bullet, and it will keep traveling until it hits the wall. and the molecular boom is formed. And then obviously you do not want to coat the wall with it, so you put a substrate. If you remember, the substrate we used was something called sapphire aluminum oxide. Or substrate was put it in its path, and the deposition will start. So, but gallium itself will not be able to. So you have a shutter to turn on or off. So this contraption of the chamber, the heaters and the shutter is called a Knudsen cell. That is a effusion cell. That is the heart of the so-called molecular beam epitaxy system. And then you have multiple sources. You have group 3s, group 5s, which in this case is nitrogen. You have dopants, which is silicon for N, magnesium for P. And so you can make various layers. Now that is the basic story of the molecular beam epitaxy system. A steel chamber connected to a pump with diffusion cells inside. This diffusion cell generate molecular beams of gallium, indium, aluminum, nitrogen, silicon, magnesium, and these fall on a substrate. So how do you control composition? You control composition by controlling the arrival rate, the rate at which this gallium, indium, or nitrogen arrives. And how do you control that? You control that by controlling the temperature of the diffusion cell. How do you control the thickness of the various layers that are deposited? Using shutters. If you know the rate at which the materials are arriving, if you know the time you are turning the shutter on and off, you can control the thickness. So that is, in short, the process of the molecular beam epitaxy system. However, let's go back to the picture that we started off. The reality is something a little bit more complicated. This is our facility here at University of Calcutta. We have the so-called FICO Gen 930 system. We have a chamber in which we grow the 3-nitride materials. We have a chamber in which we grow silicon germanium materials. Right now we are focusing on the 3-nitrides because that's where our projects are. All of this requires a whole lot of money to run. And so that's what we have been doing. Now, let's look at a little bit of growth kinetics. As it seems simple. You have a layer and then you deposit another layer and that's it. But it's not. It's not as simple as that. Because if you have 2 layers, you can deposit them in various ways. So for example, you have a substrate and then atoms are coming down and they deposit and they complete one layer and then they complete the next layer and so on. So this is a process which is called the layer by layer deposition technique. Okay. But this is not the only way. And how do you know if it has layer by layer deposition? The way it can be known is, of course, if you look at it after the fact and you see a very smooth surface. This is a scanning electron microscope of a surface. The dot that you see is just a speck of dust. We use it to focus, otherwise you have nothing to focus on. But molecular beam epitaxy allows you to look at the surface during the growth itself using a system called reflection high energy electron diffraction. READ is a short form. If you see lines, as you can see, like white lines, bright lines, if you see lines, then the surface is smooth. Of course, there are other ways. So this is another way of depositing. Atoms are coming down and they deposit. Boom. And as you can see, they deposit in a random fashion, and the surface is very, very rough. So the surface looks like this, and the read pattern becomes, instead of lines, it becomes like spots. So this technique also allows you to uh, look at the surface, so to speak, evaluate the surface as it grows. And there is another way of growing. This is the third one. I will not bore you any further. It's called the step flow growth. And then, of course, the surface looks like steps. This is an atomic force microscope image of the surface, and they are atomically flat steps. And the step height is 1 unit cell of the crystal structure. So one layer. So the point is, there is a whole lot of physics involved in the growth process itself, which is not trivial and something that has to be looked at during the growth process. Now, we are going to talk about a little bit of additional physics as we are going to look at, because it's interesting to do a little bit of physics more. So what we are trying to say is that if you have a substrate and if you have efficient cells, and this is a deposited atom, if the atom is deposited, it can either stick or it can re-evaporate depending on the temperature of the substrate. If the temperature of the substrate is high, it re-evaporates. If it is low, it sticks. So there's one more way in which, if you have a deposited atom and you have a metallic layer that forms on the surface, this metal, of course, is molten. It is not a solid, it's a liquid thin film on the surface. At that point, if you have the same red atom, instead of flying away, it sticks. So we have in our, this is now, we have gone from very fundamental to somewhat general. Now we are talking about something in particular, about what we do in our laboratory. We are growing, we are developing this kind of a growth technique, which are allowing us to make things which are interesting and useful, because we can look at arrival rates and grow films which normally would not be thermally stable. So there are two types of atoms are coming down, and then their evaporating rate. So if you balance the atoms coming down and evaporating, you can control the incorporation right there. So we have published something called the new growth model, which this metallic layer that is on the surface is like gallium and aluminum, and then nitrogen reacts with this metallic layer to form the argon layer. Now, our question is the metallic layer flat? Now, even from fundamental understanding that if you have a metallic layer on a surface, it can either form a flat surface or it can form like spheres, depending on the surface tension, depending on the surface properties. So, for example, water can wet silicon surface, or it can form little spheres of water if the wettability is low. And this change from a flat surface to a small spheres is controllable by various factors. You can use something called surfactants. For example, if you coat a surface with oil, then the nature of the spheres will change from flat to spherical. So similar way, in the atomic level, you can control the surface and the flatness. And if you do that, you can form something called nanodots. So we have moved from the topic from flat surfaces to nanotechnology to something called nanodots or quantum dots, which are useful. So these are images. Now, what are these images? These are images of something called transmission electron microscope images. Now, I want you to look at it. Each layer is essentially an atomic layer. Okay. And the bar is 5 nanometers or 50 angstroms. So you can, using this technique, look at layers of atoms in the cross-sectional mode, and you can count how many layers you have grown, and so on and so forth. So as you can see, in this structure we have grown, the layers are very, very flat. So these are flat structures, and these are called quantum wells. These are used in various electronic and optoelectronic applications. These are quantum wells. Or you can form droplets, and you can see those droplets on the surface. These are called nano dots because they are nanoscale. And I would ask you to look at the surface. And if you can look at the surface, you can see that there is some degree of pattern. It's almost like we can see hexagons. And as if the atoms are sort of like aligned next to each other. Why do you think these atoms are aligned? See, I mean, there is no way we can use a tweezer to control where the atoms land. But why are they aligned? Why do they look as if they have a regular periodic structure? It is because if you remember our slide a few slides back, we talked about something called step flow growth, in which we said the surface can, under certain conditions, look like steps. So here, of course, the surface look like steps, and the dots have moved onto the steps and they have arranged themselves. It's almost like you go to a stadium and people are sitting down on the steps watching a game. So here also we have steps, atomic like, on the surface, and atoms have formed nanostructures, nanodots, onto the edge of the steps. So these are very, very useful for many, many applications, starting from data storage to quantum computing, where the ability to be able to control the formation of nanostructures at specific locations with reasonably similar surface size of the dots. Anyway, moving on. So we have formed nano. If the metallic flat layer is flat, we can form droplets, and the droplets can form nano dots. So that is what we have worked on, and we have used it for light emission and for UV photo detectors and things like that. And we have been very, very successful in controlling these phenomena. I will not go into the physics of it. Let's go back to the device part. So, what happens if these materials, this is the problem of these materials, why do you think the 3 nitrides are very inefficient? Because they have a very, very large number of defects. So let us look at the structure again. You have the conduction band, you have the valence band, you have the electrons and the holes, and you have defects. So what will happen? The carriers will travel by drift or diffusion. They will be trapped in the defects, and there they will recombine in a process which will not emit light, non-radiatively. So that is loss of efficiency, which is why the UV LEDs have much less efficiency than the blue ones, because they have much more defects. So that is a problem, and we have tried to go around this problem by making small fluctuations in the composition of the material. What will happen if there is a small fluctuation? If there's a small fluctuation, the band gap will fluctuate. And if the band gap fluctuates, this is what is going to happen. Can you see the conduction band and the valence band? They are both fluctuating. So what will happen? The electrons and holes will move to the potential minima. They are going to go to the potential minima and recombine from there. And since they cannot move around very much, they cannot go and recombine at the defects. It is the same story as when I talk about this to a live audience, it's easier. It is like trying to have recombination which is efficient. Let us assume the electrons and holes are a thief and a policeman. In order for efficient LEDs, holes and electrons must recombine efficiently. So the policeman should be able to catch the thief and come together. Now think about a road that is very, very smooth and flat and straight. And we know the thief, which is the electron, moves much faster than the policeman, who is probably a little large in size. And so they will never be able to catch the thief. So in this case, the electrons and holes will never recombine, and they will recombine at defects, and there will be a problem. On the other hand, if the road is undulating, there are a whole lot of speed bumps, then the speed of motion of both the electrons and the holes is reduced. And so we can have our inefficient large volume policeman run up to the thief and catch him. In this case, the holes will be able to efficiently recombine with the electron. So that is a way to reduce inefficiency in LEDs, and we are working in this path, and not we, many people are working in this direction to grow semiconductors which are not uniform in the conduction band and the valence band, in the band gap, so to speak. Okay, so from there, we will talk about now. I think we are already in the second hour of the talk, and we will now focus on the device part. And before I move on to device part, again, I will ask whoever is listening, anybody, could you please tell me if I'm audible? Hello?
Yes, sir. Yes, sir.
Good.
You are audible, sir.
Good. Thank you. Now, so that was a whole lot of physics, whole lot of this and that. Now, we are going to talk about how to make the UV LED. So, this is the schematic of the structure that has to be made. Okay, so we will go from the bottom. The substrate is sapphire, and there is something called a nucleation layer. The first layer is aluminum nitride, and then there is a N over there. Earlier we talked about gallium nitride. Now it is algan, which is doped with silicon. That is the P type. On the top, the N type. The N is the algan doped with silicon at the bottom. On the top, you have the P algan, which is doped with holes. And in between, we have multi-quantum wells. And we have the electron blocking layer, EBL, P algan EBL, which is the yellow layer. So multiple quantum wells, they make things more efficient. But of course, also, is a pain because there are so many layers now. You can count 1, 2, 3, 4, 5, 6. There are about 15 layers to be grown efficiently with proper control over thickness and composition and doping levels. So that we take care using our MBE system. And after this is grown, then the fabrication starts. So we will just show offhand that, our LEDs do glow. This is one that was tested using our system, and you can see this light coming out. This is only the visible part that you can see. The UV part, of course, you cannot see, which is much more intense than the little soft light that you can see from the probe. The UV part is much more intense, but obviously you cannot see that in this picture. And these are the spectra. And as you can see, we have grown a whole series of these LEDs. And the UV part, the visible part, is beyond 400. So the little white light that you saw does not come into scale even when it comes to the spectrum, when it comes to the power. So the UV part is a whole lot brighter. So that is the show and tell. But now, how do you make it? So these are the sapphire substrates that we have used. We could use silicon, but then the light cannot come out. It is opaque. Silicon carbide is not rare. It's actually expensive. It's much more expensive than sapphire. And also it is opaque because light does not come out through silicon carbide, which has a much larger, much smaller band gap. So sapphire is chosen as the substrate for LED growth. The third picture is the sapphire. Now it looks hazy because the top surface is smooth, but the bottom surface is deliberately chosen to be rough because it allows better extraction of light. So otherwise it will be like looking like glass. It is very, very transparent to visible and to UV light. So, and then there's a growth, aluminum nitride buffer, 13% lattice mismatch, so the buffer need is needed. N-algan layer, quantum well structures, electron blocking layer, p-algan, p-GAN. So that is the growth using in our MBE system. So we use very, very pure aluminum. So, and gallium for the growth, and we have precision control. We have monolayer growth possible. We can grow by layer mode. And the reason I put this slide is you can see me and my students over there operating the MBE system over there. And it is complicated, and my students have learned how to use it. It took them several years to do so, to get rid of the fear of the system itself. Now we will talk about the problems. So usually, if you have an alloy semiconductor, for example, AlGaN is an alloy semiconductor. The Vegard's law says if you know the band gap of gallium nitride and aluminum nitride, you should be able to find out the band gap of AlGaN using this law, which is just a function of the composition. But unfortunately, that is not the case. So this is our expectation, that AlGaN composition and the band gap should be linear. But unfortunately, it is not. In reality, it is like a bow, and the equation has an additional term called the bowing. So far, it would be fun. But what happened to is, we don't even know what is the bowing. So there is a whole lot of literature. We have summarized it from 83 to 2009, and even afterwards. A lot of people have have measured various number of bowing parameters. So, as I said from the beginning, we know these materials, but we don't know these materials. We don't even know what is the bowing parameter. If you do not know what is the bowing parameter, how can you find out what composition to use for what wavelength? So we had to learn our own bowing parameters, and this is our data, hundreds of samples grown, and we measure the energy, the band gap energy versus the composition, and you create your own calibration curve, so to speak. Now, why is it different? Because the technology of deposition is different. And so every time you have to develop a history of your own samples, and you have to know what you're doing. So that takes years, so to speak. And we have to learn how to dope. So this is some publications about doping. This is some publication. Oh, the student I asked to help with the PowerPoint presentation put in uh, her paper here. So that is some more recent work, 2019. We made quantum wells to emit in the UV region. I will not go into this specific story. But at the end of the day, the device looks like this. You have a P and an N and a quantum wells, and then you have to have the contacts at the top and the bottom. But there's a problem. What is the problem? The problem is sapphire is insulating, electrically insulating. It's optically transparent, but electrically insulating. So there is no way you can make a contact at the bottom. So how do you access the N type? In order to reach the N type, which is buried underneath all the layers, the material has to be etched like that, removed. It's called a mesa etch. Unfortunately, 3-nitrides are very, very difficult to etch. No chemical can etch it directly. So you have to have a plasma etching system, and that too inductively coupled plasma. It's a more complex and a lot more energy involved in removing gallium nitride. So the first step is you etch down to reach the N type, and then you form ohmic contacts. And it's easy to say, but each ohmic contact is many layers of metal and a whole lot of annealing. But we will skip that for the moment. So you have P type and N type contacts, and here you go. So for the N type, you have titanium, aluminum, nickel, and gold layers, one after another, with a very, very specific thickness. And then you anneal it. You have to anneal it at different temperatures to make sure that the ohmicity is there. The contact to the P layer is nickel and gold. Again, it has to be annealed. And the whole process is done using something called optical lithography. I am sure these are undergraduate things. I will not go through it, but we use something called image reversal lift-off process in order to do the lithographies. And so this is the system that we use, is a MS6 from SUSE Microtech. And so this is the image reversal technique. It is a process in which, here you go, lithography is carried out, you image reverse mask. So if you look at it let's not go into in detail. If there are any questions, I will ask. Otherwise, this is too much detail for an FDP program. I will skip this for the matter. All I'm trying to say is, rather than go through this entire slides, I would just like to say, if somebody is willing to set up a lithography lab, which we have, for example, each material, each device has its own unique problems. So there is no unique recipe or even process to do lithographies. For example, if you have a rough surface, if you have a smooth surface, if you have a transparent surface, if you have a surface or a substrate that is insulating, for example, all of this must be taken into consideration for the successful lithography process to happen. So I get a whole lot of questions from students saying that, can you tell me what recipe I can use? And the answer is, I cannot, because every recipe has to be fine-tuned for the particular uh, substrate, for the particular ratio, the smallest feature size, and all of that. So this is quite challenging. I'll give you just one challenge, and then I'll stop. Is the developer solution that is used, standard developer solution, it can have an effect on aluminum gallium nitride. It can etch or it can roughen the surface. So we had to go around all of these problems and develop our own technique. So the take-home message I only have from these slides is, there is no one solution for that. Now, so this is what the device can look like if you look at it in a profile. So you have the sapphire, the aluminum nitride, the contact layers, and you see the P contact layer on the top and N contact layer. Now, if you look at this picture, the problem is that the N-algan is very, very difficult to dope very well. So current spreading is very inefficient in the N-algan. So if you use this structure, what you will see is only the edges of the LED will light up, the center will remain relatively dark. So we have to use other devices which has other kind of geometry. Can you see the E geometry? You can see the so-called spiral geometry. So we have a whole lot of geometries which are used for spreading the current around so that there is no bottleneck for the current. And if there's a bottleneck, unfortunately, the device will heat up. And if the device heats up, then the efficiency goes down, because most of these transitions are so-called excitonic transitions. The electron and hole, they form an exciton to make efficiency more. But at high temperatures, the excitons break. So you cannot afford to have the device heat up. So if you remember the earlier part of the talk, we talked about a whole lot of geometries, and this is the reason. It is there to spread the current and to make sure the heating is uniform. And so it looks more like this, the device geometries. And these are some of the structures we have fabricated, and we already showed you the emission spectrum. And this is our publication, which came out, let's see, 2021. Oh yeah, so few months back. So we have made efficient quantum LEDs, ultraviolet LEDs, using the fluctuation that we talked about. If you remember, we talked about compositional fluctuations or inhomogeneity to make things more efficient, by the policeman and the thief story. So that we have put into practice, and these are the papers that came out of that work. Okay, so why do you need? So this is a dark slide because this is not my work. Just to remind me, this is not my work. This is from the internet. So UV LEDs are useful because you can have water purification at the tap itself rather than on the wall. So if you have a UV LED reactor connected to the pipeline, you can open the tap and you can, you can get pure water right at the trap. And so it can also be used in batteries, in water bottles. So the LED is hidden inside the cap. You have a switch. You press a switch and it turns on and it purifies water. So we are looking forward to the time where we can make LEDs so that you can have it inside every bottle, like one inside the cap. And so you do not really have a fear of recontamination of water. So, and then you can have water, pure water on the go, so to speak. What happens is there are bacterial contamination at almost every water. And if you keep it stagnated for a while, it will multiply and multiply. So you need to have some sort of germicidal effect on the water from time to time. And so, for example, you can have a children's water bottle you can take, who they take to school, and just tell them, before you drink, make sure you turn on that switch and let it blink, and it will stop blinking, and then you can drink the water. And then you have to tell the bottle itself that make sure that you do not let the child open it while the LED is still blinking, because these LEDs are still, harmful for humans as well. So this is the aim. We have, this is again a white because this is our work, and this is our publication from 2020. We have developed water purification systems, not using our LED, a commercial one, but we managed to purify water using a specific geometry, which we called a multipass geometry reactor. And we used a single LED to purify 250 milliliter of water, which is great. And so because that LED could be powered by like rechargeable sources and things like that. So this came out in the Journal of Water and Health last year. So we not only work in the LED to UV LED development, but we are also looking at how to put it to actual use, to actual work. And the whole idea at the end of the day would be to use such systems and, at off-grid locations where people cannot use an AquaGuard or something, etc., etc. And you can get these LED-based systems. You can charge them using a solar-powered system or a hand-cranked system, and you can get pure water that way. So that is all I have for the LED part. and I have about half an hour left. So I will very quickly go through the photodetectors part. Most of the stuff that we wanted to talk has already been talked about. So ultraviolet photodetectors and why we need them. We are back to the flame. Okay, so a flame, of course, emits light. And light emission is given by the blackbody radiation curves, which you see underneath. And if you can sense UV, you can sense high temperature sources. Why? As the temperature of the flame goes up, the spectrum shifts more to the UV part. So ultraviolet sources are typically among the various ultraviolet sources are, are very high temperature flames. Now, so if you have a detector that can detect UV, you can use that to detect flames. But how about the sun? I mean, the sun also generates UV. So how can you say this part of the ultraviolet is coming from the sun, or if it's coming from some flame you have somewhere? And for that, a little bit of upper atmosphere story comes into the picture. So solar radiation absorbs as it passes through the upper atmosphere, and so there is a range 240 nanometer to 280 nanometer, which is given in this red line. If you can see the absorption, it's an absorption versus wavelength. So this gets absorbed in the ozone layer. So that is why we are still surviving, which is, we don't have skin cancer when we go out. Because radiation in this wavelength range do not reach the surface of the earth, even in broad daylight. Unless, of course, you have an ozone hole or something, which, of course, is a different story altogether. So, any light within this range you can detect is coming from an artificial source. Now, if I am pointing my detector to the sky or from a satellite, pointing it down to the surface of the earth, and I see a flash of high intensity UV light, that is not a good thing from the defense point of view. So, without doing too much of explanation, I can just say that these are used in something called the solar blind photodetectors. They are used in sensing of plumes from various incoming bad objects, so to speak. Now, how do you make them? That's the next question. Before you do that, the ultraviolet, illumination, as you can see, is used for water purification, sterilization, food preparation in hospitals. But then you have to know if the UV light is on for effective sterilization. You need the photodetectors that are necessary for quality control and continuous monitoring. The way I am asking you to tell me every now and then if I am audible, it is a quality control and continuous monitoring process. So the same story. I mean, if you have a UV light to do germicidal action, you better have a photodetector that will tell you that yes, it is on. It's not merely switched on, it is on. So detectors go hand in hand with ultraviolet illumination for germicidal action. And current technology use photomultiplier tubes or silicon photodetectors for UV detection. Now, photomultiplier tubes are bulky and fragile. Not recently. Recently, they have some MEMS-based tubes, but generally are bulky and fragile and require high operating voltages, and they are incompatible with imaging. Difficult. I will not say incompatible. It's very difficult to make compatible with imaging. Silicon photodetectors are inefficient in the UV. Of course, because most of the light is absorbed on the top surface, top few layers, and there are a whole lot of defects. So they're inefficient in the solar blind, and they are broadband. So you need a lot of filters to make them wavelength selective. So these are the problems with the current technology that we have, which leads us to the fact, again, to this slide, the ALGAN alloys are the only ones that can cover this 280 nanometer range, which is around 5 electron volts in that picture. Okay, so this is a typical solar blind photodetector. I use the word proposed because that is proposed by us. We will make it at some point. A whole lot of people have done, but we have developed a shortcut around this problem. We will talk about it again a little later. So if you look at it, this is the structure similar to that of a LED, except it is a PIN structure. And if you look at it, it's the same substrate, and then the aluminum nitride buffer layer and the N contact layer. Now, when light is shining from the bottom, what happens is the N-type ALGAN, the 65% aluminum nitride N-type ALGAN, it absorbs shorter wavelength lights. See, when we talk about solar blind, we talk about 240 to 280. So you cannot have light shorter or longer. It has to be sensitive only to that range. So the shorter wavelength light is cut off by having an ALGAN window, the light blue. So the light, see, imagine broad spectrum UV light is coming from the bottom. The shorter wavelength is cut off, and then the rest of the light is absorbed in the undoped region. Longer wavelength is cut off by the band gap of the undoped region. And so this one is only sensitive to a specific wavelength range. Now that is the general way of making a solar blind photodetector. But now we are going to talk about our own work. Before we do that, I just wanted to show you that such a structure has a whole lot of things. It has to have design of epistructure, and then the buffer layer, then the graded layer of ALGANs, and then characterizations, and then lithographies, and whole lot of stories. So the process flow is huge and complicated. Again, I will not go through this entire thing. I just left it there to show that making a device has a very large number of process steps which has to be done and done well in order to get anything done. And what we have done is something a little bit more simple. We have made ultraviolet photodetectors based on quantum well structures. So if you still remember your undergraduate or early days of physics in quantum wells, if you remember that in quantum wells, the transition is between states. So if the transition is between states, then you can make sure that the quantum wells absorb only certain selective wavelengths. The actual process is a little bit more complex. There's a formation of exciton and things like that. But quantum wells can be used to absorb at certain specific wavelengths depending on the thickness and composition of quantum wells. So that is undergraduate physics. And what we have done is we have used such quantum well structures here. And if you can look at it, it's sapphire, aluminum nitride, and ALGAN layer. And then we have made some quantum well structures. What are quantum well structures? These are alternate layers of large bandgap and small bandgap materials with specific control over thicknesses. And then we have made metallic contacts on the top. The two contacts on the top are there without any mesa, without anything, just the two. Okay. So growth by plasma-assisted molecular beam epitaxy. And the quantum wells are made out of ALGAN and fabricated using optical lithography, RIE, and VVD for contact formation, etc. And here we show you some of the TEM pictures of our quantum well structures. As you can see, that TEM shows well-defined wells and barriers. And so we can say, yeah, we have grown what we intended to grow. The contacts are made using lithography. Again, the specifications of the lithography I will not put in because it is very, very dependent on the material and the geometry, but they are like interdigitated structures and they have pads to contact them to. So they are essentially MSM, metal, semiconductor metal structures, except the semiconductor in this case is not a thin film or an epitaxial layer or even a bulk film, but a set of countable structures. And using that, we have managed to get something called wavelength selective photodetectors. Now, if you look at the picture, the blue is the spectrum of the wavelength selective photodetector. As you can see, the peak is at around 300 nanometers, and we have almost exclusively been able to detect light at that wavelength, and we are invisible to all other light up to 700. So this fulfills our purpose. It's nearly a Gaussian peak at around 310. And of course, depending on the thickness and the composition, this peak can be made to shift to any wavelength of our choice. And the mechanism is, again, physics, formation and splitting of excitons. I will not go into that without any questions asked. And even more recently, we have looked at other structures in which we have moved our wavelength of interest down to the 230, 240 nanometer range. Now, why do we need detectors there? Again, I will say, and this is an important area of research. Anybody who is interested, I would ask people to look into it. The only way to really, really save yourself from COVID and other situations is thorough disinfection. And we do that right now using chemicals. It's much easier if you could put your hand inside a box and turn on some light and get disinfection done. Or if you have a car, if you had disinfected light LEDs built inside, so before you move in, you turn on the light, wait X number of seconds or minutes, and make sure it is sterilized. The problem with using that as it is if there is an accident, if you ever are inside that car and you turn on that light by mistake, there's an acute chance of skin cancer. Using the disinfectant technique, we can prevent
Actually, Sir is having some network issue, so he's joining again shortly. So let's wait for a few minutes.
Hello?
Yes, sir. You can share your screen, sir. I have
Good.
made you the.
I was on my last slide, so
Oh, okay.
I'm so happy I managed to do this. Okay, so okay, can you see me? The screen?
Yes, yes, sir. Yes.
Good. So that this is the reason we shifted to the 240 nanometer range, because these are COVID days and we are trying to do what we can. Okay, so so can you see my screen? Is it moving now?
Yes, sir.
Good. So as I said, I'm on my last slide. So that is the work that we have published, and deep UV wavelength selective photodetectors based on lateral transport in alga and aluminum nitride quantum dots. That came out 4th of August, so like several days ago. Okay, so with that, we come to the summary. And we are going to talk about, we have talked about UV LEDs, which are commercial. Excuse me. Yes, which are very efficient, which are very inefficient, but they are useful in water purification, hand sterilization, etc. And UV photodetectors are available, but images are not. And solar blind photodetectors are available for flame sensing. I'm also talking about the fact that we at the University of Calcutta are also in the game, the big game of trying to make stuff work. Okay, so this is the team that we have, and the funding agencies, students. And before I end, I thank all the organizers for letting me talk about our work over the last several years, so to speak. And also the fact that, this picture was taken at around 3 o'clock in the night at the end of a long, hard day working on the machine. So yeah, I'll thank the students for still being able to smile at the camera. And still, so 4 of these people have one of them have graduated, 4 of them submitted their thesis, and others are in the pipeline. We also work with many groups with collaborative research. We do lithographies for them. We make devices. We test their equipment, their devices. We have a whole facility for device testing, photodetectors, LEDs, materials itself, and so on and so forth. Thank you very much. And if there are any questions, please let me know.
Thank you, sir. Now I would like to request participants to ask questions if they have any. Any question from the participants? Okay, so if you have any question, you can also contact Sir through his email. Okay, sir, it was indeed a very encouraging and interesting talk. So thank you for coming and sharing your works and giving such a enlightening speech. Thanks a lot.
Thank you.
Thanks
Thank
a
you
lot.
so much.
And now we will be moving forward for the lunch session. So again, we will be coming back on 3 o'clock. So see you again after the lunch. Thank you.
The equipments present in the lab. Okay, so quickly just browsing through the rest of the centers of excellence. So yes, this is the Kwanzaa Center of Excellence exclusively for the control systems, and this is being catered to the graduates, undergraduates, and the postgraduates for academic and research in electrical engineering, in instrumentation engineering. So these are the exclusive experimental kits which are available in the facility. So you can witness the multi-dimensional several degrees of freedom based equipments here. So, ladies and gentlemen, you can also go through the 360 virtual tours of all these centers in our website, or you can just scan this QR code here for an immediate 360-degree virtual tour should you require for. Okay, so next is the SU Eurodrive Center of Excellence, which imparts short-term modular course programs and training programs on the variable frequency drives and multi-axis servo controlled multi-axis. So next is the very elite Tata Technology Center of Excellence, and exclusively the Center of Excellence caters to the mechanical engineering, the electronics, the instrumentation and electrical engineering undergraduate programs. And they have beautiful programs on the smart factory lab car, the product design and development, and very interestingly, the tear down and the benchmarking. So in association with Tata Technologies, basically, this comes as a part of the package that they have set up the entire car in the lab, and our students, as a training session, they completely tear down the entire car. They break it into bits and pieces, and then starts learning the technology, and they assemble and they completely fabricate and set up the entire motor. So next, quickly browsing through the CVRC CAC Center. So this exclusive center is catering to this computer science and computer science IT major departments in the campus. So basically, the CDAC covers the high performance and supercomputing, the cloud computing, the IoT, the WSN wireless sensor network, the SCADA lab. Apart from that, they also cover, IoT-based wireless communication, mobile computing programs. So next is a very, very high-profile center, which we are very, very proud of. That is the HVAC. That is and the Refrigeration Center of Excellence. Do we have Professor Sachindra, sir? Professor Sachindra, are you there? Okay, so I was expecting Professor Sachindra Rao to be here. He's the ISHRE and the ASHRE certified HVAC trainer. That is ventilation, air conditioning, and refrigeration. So these are the training programs which are exclusively covered under HVAC, that is the refrigeration and air conditioning, the industrial air conditioning, the PLC and wiring stimulation of the refrigerators, and use of the softwares for the psychometric analysis and industrial applications. Most importantly, after setting up this center, our students could witness a surge in the placement, especially in the sectors of refrigeration. So, the Voltas, the Carrier, these sort of global giants started recruiting our students, which was a very big achievement because, normally we witness these placements maybe in the IITs, but not mostly in the private universities. But yes, we were very fortunate that our students were trained and they were certified by ISHRE and ASHRE. And post to that, they were recruited by these refrigeration global giants. Shots during the HVAC classrooms, which has been taught by the experts from the refrigeration industries.
The demand for air conditioning and refrigeration industry has gone manifold with an ongoing global trend. Understanding the need, CVRCE has established the HVAC and Refrigeration Center of Excellence for imparting training for the future engineers.
HVAC Center of Excellence is established 2 years back. This is basically to address the facility for training and research in air conditioning and heating. And this particular Center of Excellence is established in collaboration with Ketang, South Korea. And we have got a lot of equipments from Switzerland, from Germany and from China to address to our requirement.
HVAC industry has actually progressed over time, and earlier it was very theoretical. Over a period of time it's become far more practical, and today organizations and institutes are working to a large extent in providing a lot of practical orientation to giving students on the actual feel of the product, the actual feel of the entire equipment, which makes them far more ready to when they go back to the industry.
The Air Conditioning Refrigeration System and Control Lab at CVRCE has 5 types of equipments imported from South Korea and software on psychometric analysis from USA. The world-class training tools procured by CVRCE for this center includes refrigeration sequence control training kit, standard refrigeration trainer, air conditioning unit automatic control equipment, 4-way reverse valve control heat pump, heating and cooling experiment, and refrigeration PLC control training kit. In a recent expansion, the HVAC and Refrigeration Center has further added some modern tools like air conditioner and refrigerator assembling and FDP central air conditioner trainer, double freezer control circuit trainer, cascade cryogenic box refrigeration electric training system, piston type chiller electric training assessment equipment, variable frequency air conditioner trainer, air conditioning maintenance trainer, semi-enclosed type refrigeration compressor disassembled trainer, open type compressor disassembled trainer, and shield pump disassembled trainer. Both degree and diploma students of mechanical and electrical engineering at CVRCE get exposure to HVAC and refrigeration training center from third semester onwards.
We augment our classroom teaching with the beyond curriculum experiences of the students, which includes hands-on experience in centers of excellence which have been set up by various global industries within the campus. So over there, people have a project-based learning, so they experiment and create their own ideas over there. As a result of that, after they pass out, after they graduate, after 4 years, they are almost industry ready.
The program offered here are basic diploma in HVAC and refrigeration and advanced diploma in HVAC and refrigeration.
For being a professional mechanical engineer, HVAC is a very important and helpful part for us because by doing experiments in these labs, we can have practical knowledge about the real world and I feel to be ready for the real industrial front.
By taking this training, the participants get to understand the real air conditioning and refrigeration system, build confidence for maintaining, troubleshooting, and controlling the air conditioning and refrigeration system.
Technology changes that are happening, with the environment changes that are happening, with the focus on energy, I think there is a tremendous scope in the HVAC industry. There will be far more people looking at this as an elective. If I look at it at a geography basis, look at the Middle East or look at in Europe, global warming coming up, I think there is tremendous scope for a person to take, to really specialize in this field and take this as a career choice.
HVAC and Refrigeration Center of Excellence at CVRCE is a unique destination on HVAC and refrigeration training in India. As of now, there is no such center in the country which provides hands-on training in. Thus, at the time of placement and in future career progression, CVRCE students get an edge over their peers.
We have all the facility for skill training, starting from the basic split and window AC to cold rooms to entire cooling plant and all the other equipment. Those are used in the university today. These students are absolutely trained as per all the requirements of the air conditioning industry today, which the industry is looking for. And to my knowledge, this center is one of the best and unique center in the country.
So dear participants, these are the equipment snapshots we have exclusively taken from the lab. Exclusively in the HVAC, we could attract a couple of industry projects and fundings from the DST and other reputed organizations from the Science and Technology Government of India. Apart from that, also many faculty members, they could achieve the PhD degrees. They could publish couple of very highly reputed journals in association with the HVAC Center. So next, quickly covering the industrial robotics. Yes, ladies and gentlemen, what you are witnessing right now is a 6-axis industrial robot, which has been purchased from Fanuc. I'm sure you have heard about Fanuc being one of the global giant in the robotic systems, and this particular robot is almost like 25 feet tall. It's huge, and basically this is installed exclusively in the welding center, and basically it is completely coordinated and controlled by the robotic programming and the Fanuc robot simulation. So yes, we have already discussed about the Google Center, and next coming up to the Korean VLSI Center of Excellence. Now this VLSI Center of Excellence is exclusively catering to the electronics and telecommunication and the instrumentation students. Excuse me. So here they are basically trained in the digital and the analog and mixed VLSI designing and extraction and embedded system designs.
Welcome to VLSI Center of Excellence in C.V. Raman Global University, Bhubaneswar. The Center of Excellence is a pioneering center imparting advanced skill development on VLSI design and embedded systems. The center is equipped with high-end computers with advanced and state-of-the-art softwares for VLSI designs such as Xilinx, Cadence, Synopsys, as well as other required softwares, and hardware tools such as Spartan FPGA kits. The systems are highly state-of-the-art in nature for advanced skill development. There are enormous opportunity for collaborative research on VLSI design and embedded systems. Thank you.
So this was Professor Arnab Mukhopadhyay, our beloved professor of ETC department. Okay. So Robotics Center is again supervised by Department of ETC, and again this is a multidisciplinary lab which caters to all the engineering disciplines and physical sciences departments inside the campus.
Welcome to C.V. Raman Global University, everyone. CGU Robotics Center of Excellence was set up in the year 2013 with the collaboration of ED Corporation, South Korea. Since then, more than 700 students have been completed training in this center on the subject embedded system and robotics. Cost of this lab is more than 1 crore. In this sector, these are the different robots available which can be used to do research on mobile robotics. ED7255 and ED7378 are the two robots from ED South Korea. These are the two mobile robots based on ATmega 128 microcontroller, and these two robots are equipped with Omni wheels, onboard LCD, and onboard sharp sensor and ultrasonic sensors. And both the robots supports I2C communications. So these two robots can be used to do research in the field of mobile robotics. We have also Forward V robot in our lab. These robots are based on ATmega 2560 microcontroller. This is a very powerful microcontroller, and this robots equipped with onboard LCD, sharp sensor, and number of proximity sensor. There is a Zigbee slot available on the board to establish wireless communication. So this robot can also be used for research in mobile robotics. We have also 6 number of NI Mario based mobile robotics kits in our lab. These robots are controlled by NI Mario controller. In this kit, one will get powerful MD2 motor driver, and this kit consisting of high torque DC encoder motors, omni wheels, and easy to implement mechanical structure. And this control also support Wi-Fi connectivity. And LabVIEW is the platform used to do programming of this robot. We have also 2 number of VMAX Pi based mobile robotics kit. Here VMAX Pi is the controller and Titan Quad is the motor driver, and this kit also having omni wheels, hyper servo driver, easy to implement mechanical structure, and in this kit also one will get Max Pro camera for image processing. Okay, here one can use Java or C++ for programming. This also support LabVIEW. These are the facilities we have in our lab for product development. We have 3D printer, acrylic bender, macro bandsaw. We have 2 3D printers which can be used to develop small parts of different projects. We have one machine to bend acrylic sheet. And we have also one macro bandsaw machine by which one can coat thin metal sheet, acrylic sheet, and plywood also. Thank you.
So very quickly, let me just browse. I know there is a time constraint and we really have to get over with the presentation as soon as possible. So just quickly, let me just walk you through the rest of the centers of excellence. So again, under the supervision of Department of ETC, we have the Printed Circuit Board and Circuit Design Center of Excellence, which is completely aligned to world scale and in association with the Electronic Sector Skill Council. We have collaborated with LPKF Laser and Electronics Private Limited for establishing the Center of Excellence, and this is one of the very recent most set up in our campus. So as you can see, these are the PCB design and the fabrication equipments. So you can, ladies and gentlemen, you can actually visualize this virtual tour more beautifully and more clearly in our website. So I would actually encourage all of you to please visit our website and to please visit the different Center of Excellence, visit our programs and the virtual tours under it. This is the workstation. So these are the individual equipments. So next is the Plumbing Center of Excellence. Again, this Center of Excellence has been set up in association with the Indian Association of Plumbing, India, and IPA. This complete setup has again been designed in consultation with several global giants, plumbing global giants in Germany. And as I was saying, yes, we do have the hands-on training models from Schreiber Didactic Germany. This is exclusive remote sensing, that is RS and GIS information system lab. This is the cyber security lab. This is also recently developed and set up in our campus. You can see the cyber security components. Again, we have the Schneider Electric Center of Excellence, exclusively catering to the electrical engineering and the various skill projects which are currently running in our university campus, starting from the OSDA and the DDU-GKY Grameen Kaushal Yojana projects. So these are the facilities for the assistant electrician. We also float the OSDA and the Hunar Se Rojgar program in association with this Center of Excellence, and we also rigorously practice the Atmanirbharta in association with these centers for fabricating and developing our own equipments. So this is the food testing lab, and we make sure that whatever food is being provided to our hostel students, basically that should not be adulterated, and rather it should be pure. So most, in samples, we keep on testing our canteen food, and also not just canteen food. We definitely outsource the equipment for various other projects as well. So we have the very coveted tool room training center and you can see the production equipments here for the EDM, CNC turning and milling, the conventional machines, and also we have a separate computer labs for AutoCAD, Pro, iCATIA and all. So these are the entire list of research activities which is carried out at the COEs in the last 1 or 2 years. We have another very huge list if we start counting from the starting date or from the date of commencement of the centers. I mean, that is a never-ending list, but very clearly we decided to only show you the developments and the research activities of this year and the last year. So they are the recruiters, and thanks to the setup, thanks to the vision of our Honorable President Shri Sanjeev Kumar Raut to think forward and to think ahead of 10 years than the rest of the world, and to ensure that their students are actually upskilled and they are standing apart in the crowd where the students, they exude basically the entrepreneurship qualities, the skilling qualities, and definitely attracting more placements. And all our students at the end of their career, at the end of their BTech programs, they are loaded with minimum 3 to 4 offers in the campus placement, so be the day 1, day 2 or the other campuses. So thank you, ladies and gentlemen. It has been a pleasure presenting our state-of-art facilities, so be it in a restricted, in a time constrained manner. But for more details, I would request everybody to please visit our
Okay, thank you.
and as we are very hopeful that we are transiting from the pandemic to the endemic, so definitely we can we all would love to welcome you all to our campus. So be it if you ever visit to Bhubaneswar, so please don't forget to meet us at CJU Vidyanagar, Maurajala. So thank you so much.
Thank you, Soumya ma'am, for the wonderful presentation. Thank you. Now let us move to the next presentation on simulation of thin film transistors and pin diodes for sensor development. And the next talk will be delivered by Dr. Purbasa Shamu Nanganatham. The brief biography is Dr. Purbasa has obtained her master's degree in VLSI design from Anna University, Tamil Nadu in the year 2014 and PhD degree in electronics engineering with specialization in nanoelectronics from Vellore Institute of Technology, Tamil Nadu. Currently, she is working as lead application engineer at
Cognitive Design Technology Private Limited, Bangalore, India. Her research interests lie in the development of novel material-based semiconductor devices. She has vast experience in nanoscale transistors, micro and nano electronics. So I welcome Dr. Purvasa to kindly deliver her talk. Ma'am, is it audible?
Yeah. Yes, sir. Yes, sir. Thank you so much. Thank
I've
you for the
already made
introduction.
it over. You can share.
Okay.
Yes, ma'am. Thank you.
Okay. Okay. Thank you. So I hope my screen is visible.
Yes, yes, yes.
Okay, great. So a very good evening to one and all present here. So I'm Dr. Purvasa Shanmugathan, lead application engineer from Cognitive Design Technology in association with Silvaco. So in this presentation, we'll discuss about the simulation of thin film transistors and PIN diodes for sensor development. And the outline is as follows. We'll start with an introduction and then followed with why, what is TCAD and why there is always a need for TCAD, followed with why we prefer physics-based modeling, and a quick overview of Silvaco TCAD to sign-off flow, followed with Silvaco products that is available in order to perform any process or device simulation with respect to any devices that we are working with, and followed with a few applications related to the simulation of thin film transistor that has been carried out using Silvaco tools, along with the PIN diode simulation, and finally the simulation. So without any delay, let us quickly get into the presentation. Introduction. So as we are aware, technological advances in the past few decades have taken at a breakneck pace. So from the new device to new technology like Apple iPad and 3D TV, we have new ideas that are continues to change our daily life, and even the innovation is not showing any sign of slowing down. So these new products are made possible by matching the innovation in semiconductor technology. So from this perspective, the semiconductor industry is found to be one of the key driving forces in today's global economy. As we are quite aware, the architecture of transistor are now switched from the planar to the vertical design. In order to keep the semiconductor industry on its technological growth track, a heavy emphasis is being placed on the technology computer aided design tool, shortly referred as TCAD tool, for achieving a key long-term research results. So with this quick introduction, let us just understand what is TCAD. So TCAD refers to the development and optimization of semiconductor processing technology and devices. So TCAD is basically a software modeling of actual semiconductor fabrication processes, as well as the physics-based simulation of the operation of semiconductor devices. TCAD has the potential to perform a semiconductor device design and then manufacturing process design, circuit design technology. Also, it involves the characterization, manufacturing efficiency optimization, along with the protocol process control due to there are various advantages of solving fundamental, or it could be of any complex partial equations like diffusion and transport equation. So with this physical approach, TCAD provides predictive exactness for a wide range of technologies. So TCAD simulation are generally therefore used in the development and characterization of new systems, that is new device systems, to decrease the expense as well as the time consuming test wafer runs. And yes, TCAD is a branch of EDA, this electronic design automation. So with this quick introduction about TCAD, let us understand why there is a need for TCAD in the semiconductor industry. So I have listed a few points, and the first one is reduced development cost. So TCAD has a significance in order to reduce the development cost, that is to reduce the time and manufacturing cycles that is spent to develop the semiconductor technology. The ITRS roadmap also indicates that TCAD simulation can reduce the cost during the development cycle by approximate of 30%. And the next one is visualization of internal physical processes. So using simulation, we can understand, we can see what is happening inside the device. So when I consider experimental measurements, it will let us know what happens, but it will not let us know why it happens. Whereas TCAD provides us with answer for all the why question. Hence, a visualization of internal physical process is found to be a significance of TCAD. And then next is we have this design technology co-optimization. So TCAD is a part of design technology co-optimization flow, which is shortly called as DTCO flow. So it helps, for improving the design across multiple domains, which include layout, process, device, SPICE simulation, or it also includes the RC extraction. So a full TCAD to SPICE flow in an integrated DTCO environment delivers a clear, actionable results for circuit design optimization. With this, we are having another significant point of TCAD is virtual experimentation. So this is generally categorized into two. So the first category is experiment with cause and effect. For example, if we have a change in the device design, like layout, or there is a change in technology with respect to any semiconductor process steps, or there is any change with respect to device operation condition, for example, biasing, etc. So they can be easily understood and improved or enhanced device performance can be achieved by means of virtual experimentation that can be carried out using TCAD. Another category is experiment with theories in TCAD. That is to have a control of the impact of various physics in the device via a model settings and coefficients. So if a theory is applied to a simulation and if it matches the measured result, then obviously we have found the root cause and we have gained some physical understanding of device performance. So, and the last one is communicate device complexities clearly. So semiconductor device design and processing of semiconductor is a complex task. So engineers, they must be working collaboratively in order to solve problems, explain issues, and opportunities to like a variety of colleagues with a very technical expertise. So utilizing TCAD can clearly communicate the device and the process changes. Also, it can clearly communicate the potential performance improvements with clarity, but also having in mind that that is minimizing the manufacturing cycle time. So all these advantages have attracted the researchers to use the TCAD globally. So with this like brief overview of what is TCAD and why there is a need for TCAD, we'll quickly move on with the next. It is designed for various technology sectors. So physical design plays a crucial role in a variety of technology sectors. So we, in Silvaco, we have categorized the application, into 5. So we have the display, and then we have power, and with respect to radiation reliability and optoelectronic simulation, or if we are working with any advanced process development, with any advanced devices. So everything is possible by means of using Silvaco tools. And when considering display, just a quick example of TFT technology. So Silvaco TCAD and the SPICE tools, they contain a comprehensive set of models that are specifically designed in order to take the consideration of the poor electrical performance of TFT thin film transistor that is generally manufactured on a non-crystalline silicon substrate. So with respect to power devices, like we have GaN-based HEMT devices, or it could be IGBT or any silicon carbide-based devices. So considering that, Silvaco process and device simulation have all the ingredients. That is the state of art from the mesh and solvers. So they do have the essential to accurately simulate any type of 2D and 3D simulations. And considering with respect to radiation and reliability point of view, so Silvaco advanced model for reliability and radiation effects, it allows the device and the circuit performance in order to be optimized for a lifetime and a robustness enhancement. And with respect to optical simulation, so we have the charge coupled device, or the few are mentioned over here. So CMOS image sensor or solar cell photodiode. So anything, any device can be simulated. So Silvaco supports for the optoelectronic device simulation as well. So for example, when I consider like solar cell, so Silvaco tools incorporate the electrical and optical physics that is required to like simulate a wide range of optoelectronic device types and materials. And then finally, we have the advanced process development. So in order to simulate a challenging new technology, Silvaco tools are having a tool mainly for including a 3D process and then stress and device simulation capabilities. So with this, let me quickly move on to the next. So why it is required to use a physics-based modeling, specific mainly for 3 reasons. So first reason is about the predictiveness, and the physical simulation provides us insight that is about the device, and then it captures and visualizes the theoretical knowledge. Like unlike the empirical models of physically based simulation, it provides a very good insight and encapsulates the fundamental phenomena. So it provides the information even which is found to be difficult, or even if it is found to be impossible to measure. So one, obviously that's a challenge, that we need to know in-depth knowledge of the device physics when we are working with physics-based modeling. So with this, a quick, like a few words about Silvaco, the leading EDA provider. Silvaco, it's a leading EDA software and service provider, founded in 1984. And it delivers a full TCAD to sign-off flow for the vertical markets, and including the displays and memory design, advanced CMOS process, and intellectual property development. So for over 30 years, Silvaco has enabled its customer in order to bring the superior products to market in a very shortest time, and also having in mind with providing them with a reduced cost. So semiconductor fabs and design houses from around the globe, they have relied on Silvaco's expertise to help and to develop the technology behind the chip. Silvaco mission is mainly to help the customer accelerate the pace of technological innovation and their time to market, while that is reducing their cost in developing the new generation chips. So with this, so here are the management team, that is who are continuously working in order for the development of the growth of Silvaco. So Silvaco providing capability across all nodes. So like it is approaching even 5 nanometer, below 5 nanometer. Obviously we are included with respect to the atomic level simulation also. Definitely we'll have a cross check. So we are just like penetrating even below 5 nanometer. Silvaco DNA. So the first core is found to be the TCAD, and Silvaco is known as the market leader with respect to TCAD, and it is in the #1 position for the display market as well as the radiation and soft error reliability. The next cell is formed by the EDA, that is for transistor level design. So here the SPICE connects the physical and the electrical world. A full custom design flow for mature nodes, and Silvaco EDA tools for example, it has the best parasitic reduction tool on the market, and it offers a best variation analysis tool for high sigma. And the next cell is formed by the intellectual property, large portfolio of intellectual property. So standard cell library foundation of IP and large automotive IP portfolio. So now let us quickly move on with a overview of Silvaco TCAD to sign-off flow. So as we could see here, the first being the TCAD, and then we have the modeling, and then we have the design and verification tools and simulation and analysis tool. So that is the reason we just gave TCAD to sign-off flow. So everything that is starting from TCAD till the analysis can be carried out by means of using Silvaco tools. So the first case being the process simulator, so where we mimic the fabrication steps and we create the structure, and which is being characterized by means of using the device simulator available in Silvaco TCAD tools. And so every time it is not a single device that we want to work. We want to work for many devices that are tied together. So in that case, we need to move on to the next level. So that is SPICE modeling. So as we could see, Silvaco Smart SPICE is found to be a high performance parallel SPICE simulator. So that delivers industry leading accuracy. It is a proven and a comprehensive solution for applications, so including simulation of a complex high precision analog and mixed signal circuits, along with memory, custom digital design, and characterization of cell libraries of many advanced semiconductor processors. So after this SPICE generation, we have the design and verification tools. There are so many tools with respect to design and verification. We have a gateway, that is when we are focusing towards schematic. So gateway is a schematic editor. And when we are working with design rule check or LVS check, then we have a guardian. And with respect to layout creation, we have the expert, and a tool that is completely dedicated for a parasitic extraction, we have Hypex, and for parasitic reduction, we have Jivaro. And we're coming to simulation and analysis. So, for example, if we need to perform, it provides a block to full chip level analysis. So, considering a CMOS image sensors. So, in that case, InVar is found to be a better tool, best tool, while considering the reliability analysis. And apart from that, we have variation analysis tool that is for high sigma analysis and for providing a fast Monte Carlo analysis, mainly to save simulation points. And also the variation analysis tool that is Varman, which is generally called as. So it provides allows for a statistical corners for quick design iterations. So with this, I've just listed few available resources for Silvaco software users. Silvaco provides an advanced interactive GUI tools, and Silvaco give the user for the beneficial of exploration, that is with respect to design of experiments or with respect to optimization. So it provides a design of experiment and optimizer tools. And then there are a number of worked standard examples with results that are available on both Silvaco website, and if the user is available with the software, then they can directly incorporate from the library. So, and those examples are available with results. That's a major thing. And next is about the simulation standard tools with Archive. So that is whatever the simulation that is standard example available, a brief detailed explanation with respect to the structure formation or with respect to the characteristic what we are analyzing is been presented as a paper format, and that is available as a simulation standard articles, and that is we are having an archive of back to 1992. And then a number of webinars and the recorded archives are available in Silvaco website, and a number of presentation material which includes white papers and so many. Apart from all these, extensive manuals and release notes, that is Silvaco will keep updating their tool every year. So they keep developing every year, and they will be incorporating more and more models so that they make sure that they are in the track with the semiconductor industry. So whenever they update their baseline, they make sure that they update all the details in their user manual, and they release the updated notes as well. So every year it will be performed by Silvaco, and then Silvaco provides an active support, training, and seminars. So with this available resources for Silvaco software users, let us quickly move on about discussing about Silvaco TCAD products, that is process and device simulator, and let us have a quick overview or exposure to various modules available in Silvaco TCAD. Process simulation, 2D and 3D process simulator are used to simulate, develop, analyze and optimize semiconductor process fabrication steps. And this may include a diffusion, ion implantation, oxidation, etching, silicidation, epitaxy, etc. So as I mentioned, whatever we are performing with respect to the fabs, those fabrication steps can be mimicked in using Silvaco TCAD tools. And Silvaco TCAD, they have two completely dedicated tools for performing process simulation. Victory Process is a 3D process simulator, and then we have Athena, which is a 1D, 2D process simulation software. So with this, just overview of what are the architecture of Athena. So what are all the modules that are available in Athena? So there are 2 standalone applications that is available in Athena, and then 3 add-on modules. So quickly, I'll just tell like what are these. So S-Supreme 4 is a 2D core process simulator that is widely used in the semiconductor industry for design, analysis, and optimization of various fabrication technology. So S-Supreme 4 accurately simulates like almost all major process steps using a wide range of advanced physical models for diffusion, implantation, oxidation, epitaxy, etc. And then we have this MC implant, that is nothing but Monte Carlo implantation simulator. And they provide model stopping and ranges in crystalline and amorphous material. So it accurately predicts the implant profiles and damage for all major ion or target combinations. And then we have Elite. Elite is an advanced physical etching and deposition simulator. And it allows for modeling of physical etch, or it allows for modeling of deposition, reflow, everything can be performed by means of using Elite module. And then we have Monte Carlo deposit and etch. So this is for simulating various etch and deposit processes which use a flux of atomic particle based on the Monte Carlo models. And finally, we have Optolith. So Optolith is a non-planar lithography simulator, and it models all aspects of submicron lithography. So it includes the imaging, exposure, photoresist bake, development. So it provides a fast and accurate alternate to experimental evaluation of mask printability and process control. So it simulates both projection imaging and proximity printing with a large mask to resist gap. And then with this, so a few results of process simulation, I have tried to just project it over here. Like if we are going for any flexible structure, yes, in that case, it can be defined by means of using Silvaco TCAD. And then if we want to analyze the strain or stress in a structure, yes, it is possible. And while considering, like for example, if we are working with any GaN-based devices, so when we are concerning about the physics behind the process simulation of GaN device, or when we are concerned about the physics behind the device simulation of GaN, so everything is by default available within the tool. And then this particular tool is easily it can be combined with the other interactive tools for plotting, for viewing, all such. So quickly we'll have a overview of all those interactive tools as well. So the next is about simulation that is for 3D. So which a multi-purpose scalable 3D process simulator platform for it starts from a small complex geometry to a large multi-device structure. It can be created and characterized by means of using Silvaco TCAD tools. Moving forward, device simulation. So device simulation is majorly used to simulate to analyze the electrical, optical, and thermal behavior of semiconductor devices. So device simulators, they solve the physical models and equation in order to perform either it could be a DC analysis, or we want to analyze any AC analysis, or we want to perform any time domain simulation. So there are 2 dedicated tools with respect to Silvaco TCAD that is specifically available for performing the device simulation. So we have Victory Device, which is a general purpose 3D device simulator, which accurately predicts any three-dimensional device simulations. And then we have Atlas and Atlas 3D. Again, it's going to be 2D device simulation software. So with this, let me just quickly introduce with respect to the Atlas framework architecture. There are a number of modules that are available in Silvaco TCAD depending upon the application in which the user is working with. So here we have silicon-based and advanced material-based. So silicon-based devices can be simulated using the SPICES module. Quickly, I'll give what all these modules are. So SPICES is an advanced 2D device simulator that is targeted for silicon-based technology that incorporates both drift diffusion as well as energy balance transport equation. So a large selection of physical models are available. So for example, that may include any bulk mobility model or recombination model or any impact ionization or tunneling model with respect to the device we are working with. And then we have the Blaze module. So Blaze module is meant for simulating any compound semi-based material. For example, if you are working with a binary or if you are working with any ternary or even quaternary material, all these compound materials are supported by Silvaco TCAD by means of using Blaze module. And then we have the Device 3D, which is a device simulator for silicon and other material-based technologies. And we have so many other modules like TFT, specifically designed for simulating thin film transistor. Definitely, we are going to have a deep look into this particular module as well as the simulation that has been carried out by means of using this module. And if we are working with any ferromaterial, then we have a ferro module. And if we are working with VCSEL-based devices or laser, like when we are going for any waveguide simulation, then laser modules are used. And then we have a LED module specifically for simulating the LED devices. And quantum module is a 2D, 3D. It's available both in 2D, 3D. And that is when we are concerned about, or when we are working with any quantum confinement effects and we want to analyze it, then this quantum model is used. And then we have, if we are performing any noise-based simulation, then noise module is completely available. And then if we are working with any optoelectronic device simulation, then we have like a luminous module. And if we are concerned on working with isothermal devices, like electrothermal, I can say, when we are considering about specifying any heat sink, or if we want to understand about the thermal impedance, ambient temperature, all these can be performed using Chica module. And then we have mixed mode simulation. So it is it's a simulation that physics-based devices, like in order to simulate a physics-based devices in combination with compact analytical models in a circuit environment, then we prefer this mixed mode module. And this particular module, like the device is simulated with a SPICE netlist circuit description. So we'll be updating all these. And finally, we have the C interpreter. So apart from all these modules, if a user is coming up with a new model and they want to include it within the device simulator for characterizing, so in that case, Silvaco TCAD allows the user to include the like user-defined models by means of using C interpreted templates that are available within the tool. So with this, yeah, again, so the 2D device simulation, a few results of the same are being projected over here. So with respect to refined segment or understanding the grain boundary simulation of thin film transistors. So all these are being displayed over here. And then a few words about the interactive tools. So in Silvaco TCAD, there are interactive tools are a suite of applications that provide the interactive GUI-based pre and post-processing services to Silvaco TCAD simulators. So they provide an easy-to-use GUI interface, and powerful plotting tools are like available that is targeted to TCAD simulation. And Silvaco interactive tools, they have the runtime environment with automatic optimizer. So these are the interactive tools, that is Deckbolt, it's in a runtime environment, Mask View, for the integrated layout editor, divided it. It's a structure tool, GUI, completely GUI based tool, and it edits the structure and it can edit the meshing as well. And then Tonyplot, 1D, 2D, and 3D are nothing but the visualization tool. That is, if we want to view our structure, or we want to view the plot that we have generated. So in that case, the visualization tool is Tonyplot. Moving on further. So I was discussing about like there is a like complete dedicated tool in order to perform a design of experiments and optimization experiments. So virtual wafer fab is a particular tool which I was mentioning earlier. So the split parameter that can be defined for any of the Silvaco's process or device or parasitic extraction are from the circuit simulator. So they can be optimized by means of using virtual wafer fab. And yeah, it comes with a GUI and that enables a examination of an experimental results. And next tool, this is about the Victory Atomistic. So I was mentioning like Silvaco are targeting even below 5 nanometer, that is even in the atomistic level simulation. So Silvaco and Cordova Research Foundation, they have teamed up to bring the scalable atomistic TCAD solution for the next generation semiconductor and materials. So Victory Atomistic extends the Moore's law through model creation and simulation of transistor and new memory technology that approach the sub-nanometer scale. Victory Atomistic is the first commercial realization of an atomistic nanoelectronics modeling and simulation tool. So it employs a material-based database containing an essential and advanced set of tight binding parameters of usual compounds in microelectronics. So Victory Atomistic allow to build an architecture with atomic resolution and Ignatius, that is considering about the material, domain, region, all these combination based on the pseudo-epitaxy and passivation rules combined with the boundary condition. So Victory Atomistic manages as many as atoms required by the user geometry with an effective limit of the order of 1 million atoms. So with this, yeah, so few simulation results that has been obtained by means of using Victory Atomistic has been projected over here. So this Silvaco has been tied up with Cordova University in order for this Victory Atomistic simulations. Yeah, moving on further. So now let us get into the thin film transistor simulation by means using Silvaco TCAD. So imaging display technology, they uses an array of thin film transistor. So they require the application of thin film layers of semiconductor and insulator material when they manufacture. So these ultra thin layers should make sure that counter to the contour of the underlying material during the wafer fabrication. So the resulting specific shape of those layers, it will impact the parasitic resistance and capacitance of the circuit and its performance. So the ability of the model that the conformal deposition is an essential requirement with respect to a modern thin film transistor technology to capture, to simulate with high precision the parasitic effects to ensure that manufacturing specifications are met. So Silvaco's software suite, they have the field solver technology. They employ the field solver technology for a very accurate extraction that is being required for the usage by the modern thin film transistor technology. So with this, we'll have a deep understanding of the thin film transistor module that is available in Silvaco TCAD, which is preferred, which is used in order to perform any thin film transistor simulation. So TFT, 2D and 3D, it is a advanced device technology simulator equipped with physical models and specialized numerical techniques that are required to simulate amorphous or polysilicon devices. Planar, it supports with the planar and non-planar device modeling is found to be possible by implementing the advanced thin film transistor module models that is focusing on defects and defect states. So when we are simulating the thin film transistor, the most important requirement in setting off is the defects, that is specifying the density of states in the semiconductor band gap. So the thin film 2D and 3D, it can be coupled with the Athena process simulator for the realistic device properties, and then the accurate modeling of these defects and the density of defect states is critical for accurate predictive software. Moving on further, let us quickly understand, like we'll see some application with respect to thin film transistor that has been simulated by means of using Silvaco tools. So we will understand about the amorphous oxide semiconductor, TFTs, and then active matrix liquid crystal display, and then Pentasin organic thin film transistor, and then channel length dependence of IGZO TFT, and we have the temperature properties of amorphous of thin film transistor with a new mobility model. So the first one is about the semi-amorphous oxide semiconductor material. So they have attracted much attention as key components of the thin film transistor for flexible electronics. So the advantages of such materials, they include the flexibility, and they allow for a transparency with which are compatible and with plastic substrates, and even higher mobilities than those of the amorphous silicon and other materials. So the operation of an amorphous oxide semiconductor thin film transistor was analyzed here. It's been provided over here to verify the applicability of the standard drift diffusion model to an amorphous oxide semiconductor material, because this particular oxide semiconductors are used in the thin film transistor mainly due to their high mobility and a wide band gap and low process temperature. So moving on further. So we have non-planar TFT. So this is designed for AM LCD. So, here is a non-planar buried gate advanced 4 micrometer channel is being used in this particular example. So a polysilicon thin film transistor is used in this particular AM LCD circuit. So it is extending with the LDD regions mainly to improve the electrical performance. And then ion implantation and diffuse model is being within Athena, it has been performed. And then density of states within the band gap that is implemented. So if we are using, using C interpreter also, it can be implemented into it. And then when the Go Atlas, that is Atlas, will be performing the electrical characterization of the same. So as I was mentioning, the one particular important factor that need to be designed, included while performing the thin film transistor is about the defect statements. So with this, I'll quickly move on with the next. That is, it's a organic thin film transistor. So recent years, there have been rapid acceleration in the research and development of organic thin film transistor as the key components for the active matrix display, the radio frequency identification tags, and for many other small scale integrated circuits. So there are many advantages of organic thin film transistor. So it also includes with the flexibility of the plastics fabrication substrate, and then the potential cost that is saving to the manufacturers that adopt a solution process and inkjet printing process. So one of the most widely studied organic semiconductor material with respect to organic thin film transistor is about the Pentasin. So results of the structure of a Pentasin organic thin film transistor and the characteristics, that is energy distribution and the density of states, and along with the IDVD characteristic of which is having a constant mobility model, and when it is compared with the experimental curve is being projected over here. So then moving on further, we have the channel length dependence of IGZO thin film transistor with self-heating effect. So a few results of the same is projected over here. So an amorphous, that is indium gallium zinc oxide thin film transistor, which is shortly called as IGZ4 thin film transistor, they show a high mobility and a small subthreshold swing. So like they also provide with a low of current, and they are considered to be one of the most promising thin film transistor while considering the flat panel display, new flat panel display. So the high mobility, it originates from the unique electron transport that is available in this IGZ4. So the transport properties are different from those of the conventional semiconductor, like when I take silicon. So for example, the mobility increases with the increase in the electron concentration or with respect to the temperature. So the new mobility model for IGZ4 is bound to be necessary, and TCAD supports with a new mobility model specifically designed. So here in this case, the pixel size in the flat panel display, like considering that features also the variation of the channel length of the IGZ4 TFETs is becoming shorter. So in this case, we have like provided few results that has been calculated using TCAD for the temperature distribution of the IGZ4 thin film transistor with a channel length of 6 micrometer, and for a gate voltage of 20 volt and a drain voltage of 12 volt. And then here we have this transfer characteristic that is being calculated for the IGZ4 thin film transistor. And then also apart from that, we have this one is the on current plot for the IGZ4 thin film transistor for various channel. So with this, we'll quickly move on to the next. That is temperature properties of amorphous for the indium gallium zinc oxide thin film transistor with a new mobility model. So we have included a new mobility model in order to analyze the temperature property of this particular material, thin film transistor. So amorphous IGZ4 is it's a typical amorphous oxide conductor. So it is considered to be one of the promising channel material of thin film transistor. So as I already mentioned in the previous case, for any flat panel display, mainly due to their high mobility and so low subthreshold swing and with respect to low off current. So when devices with IGZ4 thin film transistor are developed, it is necessary to consider the operation of thin film transistor under various bias and temperature conditions. So in many cases, it has been understood that the operation of this IGZ4 thin film transistor is similar to that of silicon TFT and dominated by the density of subgap states, that is with a fixed band mobility. So it is always difficult to reproduce the operation because of the density of state of this particular material near the conduction band. So in this particular analysis, we like a new mobility model is being introduced, which can reproduce the temperature property of this IGZ4 transistor. So yeah, so with this, we'll quickly move on to the next. Okay. So this is an simulation with respect to it's a 3D, that is 3-dimensional simulation of dual gate thin film transistor. So dual gate thin film transistor are often preferred in pixel driver and like peripheral circuits for liquid crystal display. So this is because of the reduction of the gate of state leakage current as well as the kink effect. So it is like recently it has been also necessary in order to take the consideration of the problem that is being caused by the 3D effects such as the I can say IV characteristic hump effect and leakage current at the edge of the active region. So this simply means that it requires a 3D simulation of this like a dual gate thin film transistor characteristic in a reasonable time. So also we know that the simulation of this particular device is generally difficult, particularly in 3D, because it has the electrical floating region between the dual DFTs. So this region may lead to convergence when calculating the gate of state characteristic that is including the tidal current. So in this particular example which we have projected, it provides a clear understanding of 3D simulation that is Victory is being used over here, which simulate a normal double gate thin film transistor and also including with the L-shaped dual gate thin film transistor. Like accurately, in order to predict the results accurately, robustly, and in a reasonable simulation time. Okay, so with this, let us quickly have some knowledge about the PIN diode simulation that can be carried out by means of using Silvaco TCAD. And okay, so merged PIN Schottky power diode. So this are the few results with respect to the same. So the device is first constructed using the process simulator, and then we perform any epitaxial growth over it. And once constructed, it will be taken forward the device simulator, where we incorporate various models with respect to the Schottky tunneling model. All these are included with respect to this particular device, and the net doping concentration of the same, along with the electric field distribution, are being provided over here, along with the current characteristics. And then with respect to the radiation and reliability point of view, single event burnout. So I've just projected one small example of single event burnout in a high voltage PIN diode. So here, while considering this particular analysis, so this is a structure of the same PIN diode, and the one feature that we need to, two features, it is two important requirements is for simulating the single event burnout is the device IV characteristic. It should display a snapback characteristic, that is for at least a range of voltage. So there exists two possible corresponding stable current condition, one on a low current off state, and second high current that is on state. So high voltages that is on state dissipates this sufficient power in order to overcome this heat the device. So this is first feature. The second feature is self-heating, which plays a leading role in greatly reducing the current density in a PIN diode, at which this snapback, which we were discussing, the first important feature characteristic occurs, and allowing a significantly linear energy transfer strike in order to transfer the diode from an off to on state. So that is continuous heating. Eventually, it burns the device to destruction. So that's the reason we call this single event burnout over here. So with this simulation results, so let me just give you a quick overview of what are the tools that is available within Silvaco with respect to various analysis, starting from TCAD to EDA to SPICE flow. Okay, so just a snapshot of the same, and then final with the summary of this presentation. So Silvaco is a global EDA leader, driving growth to provide value to our customer in advanced IC, display, and power. And we have physical device simulation, which capture the theoretical knowledge to provide essential insight. They can predict the behavior in the entire design space. So for obtaining a high accuracy simulation to a large area or rapid prototyping, Silvaco is best preferred for it. Along with it supports with the complemented with interactive tools and automation, and it offers an extensive additional resources for the user. And due to time constraint, I have just tried to project few results. But if you are willing and if you want to know more, you can definitely check with the Silvaco website, or either you can contact with the Cognitive Design Technology. So a few words about Cognitive Design Technology, whom we are and what we do. Cognitive Design Technology is a high-tech solution provider with multidisciplinary capabilities ranging from MEMS, IC design, and embedded system development. So we have successfully designed, developed, deployed many solutions for our customer in these areas. So we are the one who supplement our sales activities by providing our customer a next step customized solution for their needs. And we are currently having a highly talented embedded electronics engineer who are continuously executing the projects for our prestigious customers in India. So with this, so now if you have any queries, we can definitely support with the same. But if you want a detailed understanding, and then definitely you can reach us with this ID. And our concerned department will definitely get in touch with you in order to solve all your queries. Yeah.
Thank you, madam,
Yes,
for your
thank you,
enlightened
sir.
talk. Hope actually at the end of this session, participants will be able to find different kind of simulation tools. At least they will be able to identify the different simulation tools available to simulate thin film transistors and PIN diodes. So it is a really enlightened session, and hopefully participants will be highly benefited from this. Thank you, madam. Thank you.
Thank you, sir. Thank you so much. Thank you.
Can I have a quick question?
Yes, please.
Well, I think I just have a few queries. You could clarify it, or if you could showcase something, that will be great.
Yes.
So, I mean, now that, see, because you mentioned PIN, conventional silicon, but I mean, we are more interested in large area and flexible electronics. So if I were to do, say, a PIN heterostructure device and maybe again combine with polycrystalline silicon, so can I do these HIT, say, solar cell type device simulation here effectively?
Definitely, sir. Definitely. We have a specific module for performing all those simulations.
And because you're now mentioning again in case of TFT, so what, I mean, is it the problems with indium gallium zinc oxide and the temperature related effect, is it similar to the threshold shift problems in amorphous silicon, or how are they different? I mean, here with increasing temperature, I mean, of course, also there's both a voltage shift and of course current is increasing. But what are the major instability issues in such devices, if any?
So I think I have projected few with respect to temperature alone. Maybe if you are too much concerned, I can just send you what are the other things, features.
Okay, great if you can send some information.
Yes.
And you're also talking about atomistic model there and saying it's a unique and advanced thing that you're doing with Purdue. I mean, so I just want to know, suppose I'm developing some nanomaterials and I'm creating clusters. So, I mean, if, and I want to do devices both in nano dimension, or I want to look at dielectrics that can go as low K dielectric in conventional ULSI, VLSI, or equally look at the same material for amorphous, or organic material type TFT. So how, I mean, how do we define that, or for each of them, do I need to define something differently based on my material properties? And how do we go about? I mean, does it distinguish between the two, or I simply define a property material and it will give us an output?
Definitely, it is the second category. So you just define these properties and it will provide the simulation. The tool will automatically take the default things as per the user's definition.
Okay. So, but then if I am wrong, my simulation will also be wrong.
Definitely, that is the case. I completely agree with this. So that is the reason I projected that we need to have an in-depth physics college when we are going for all these. So, but one thing is like Silvaco will provide you with a default value. So we need not worry about that.
No. See, for example, you are talking about 10 or 5 nano 6 micron polycrystalline. So is it? So is it that say, I mean, is it amorphous material crystallized with laser process, or was it by default, I mean, my LPCVD polycrystalline silicon grown at 600 degree, or how do I differentiate between the two? Does it give provision for something like that? Because I mean, the defect that will come with amorphous, and because many TFTs are today made with laser-based crystallization after amorphous process, so that localized heating can be done rather than lama. So do you have provision to do things like that, or how do I know what process to use?
Yes, there are like for every category, what you're looking for is available within the tool. And as per, I mean, like I at this stage I couldn't project. If not, I can show you what are the features that has been available for as per the question that you have requested. So everything is involved. But the thing is, like, we need to understand the tool, what are available within the tool, and we need to call for while simulating.
Okay.
So, but that is not an issue. Like when any user procure the software, then with respect to their needs, of a specialized training will be given where we will be projecting them as per their requirements.
So, for example, as I was talking earlier, I want to look at a carbon-based material, which is something between amorphous and cluster, but it's not nanostructured. Okay.
Okay.
And it does. I mean, I don't have any idea of defect density. Its conductivity can be high. I mean, I could change conductivity over 12 orders from -12 to say 10 to the power 1 without even a dopant. So, I mean, how do and if I want to use it as an amorphous device, or if I want to use it as general amorphous or organic type device, or I want to go even into nano electronic and say form. So, I mean, is there something to check and verify and tell me I am doing something right, or it will be simply that depends on my foolishness, it is turning out right or wrong?
Definitely not like that. The tool will let you know whether you are in the right track or not.
No, but I mean, because I'm simply defining some defect density, it is realistic or unrealistic. I mean, how does the band gap calculations understand it?
This is viewable. This is viewable. So just like that, we just don't give any comments and then we plot it or we observe it. But obviously we will be all these are matched with the physical models that is available universally, right? So definitely, if we are implementing the right things, then the result will be much more accurate.
Okay. Anyway, thanks for your input, and we look forward to interacting, learning something more when we are going to use things related to this domain. So thank you very much.
Great. And if any of your persons are looking for a much more detailed understanding of any of the devices they are working with, which is to know the capability of Silvaco TCAD, then please let us know. Our team will get in touch with you. The corresponding team will get in touch with you.
No, I mean, we would appreciate getting information on, amorphous and metal oxide materials based TFTs, and of course amorphous silicon heterostructure. Solar cells are where we could use them as sensors. And so, what is the software you use for MEMS?
MEMS, like if we are not, going in depth about mechanical analysis, then Silvaco TCAD supports the same.
Okay. So if I'm looking at electromagnetic field linked activity, can I use it?
Yes, please. So that is, I can say, like when if you are looking for anything with respect to motion, in that case, then this is not possible with Silvaco.
No, I'm more looking at electromagnetic field, current density changes and things like that.
Yes, so, that is possible. Yes.
Okay. All right. And or similarly, is there something to do with, say, diamond-like carbon? It's an amorphous material, or graphene and all that. How much does it support?
Okay, so actually for graphene and all, it is not available as a default material, but Silvaco supports with the user-defined material, which can be incorporated into the tool. So that the user should contain all the properties of the material, and they can just put it over in the tool for further characterization.
Thank you very much. Thanks for your inputs.
Madam, please. I have a question. Am I audible?
Please. Yes, please.
This is Dr. Ornav from ATC department of CGU. Actually, I'd like to ask one question just in line with the question asked by VC sir. Actually, when in case of the two-dimensional materials, especially like graphene or layered materials, when you incorporate those things in TCAD at last, so in case of that, there are some convergence issue because the TCAD is more inclined towards the conventional materials like silicon, germanium, like that.
yes, it is a fact that user-defined materials are allowed, but in case of that, the incorporation of user-defined material, especially for two-dimensional material, the entire parameter list must be changed. But that is a very hectic process. So, can you?
Okay, let me just quickly give you a few points. So convergence is like we can't say that it's only related to the material what you are incorporating.
It is actually mesh-related issues, some meshing-related issues and other convergence issues due to material parameters.
Yes. So there are so many parameters. So as you rightly mentioned, with respect to mesh, and then if we are setting any wrong process or device parameter setting, that may also lead to convergence. And then we have to be very careful while choosing the numerical solver. And then like these are few things. Then with respect to extended precision, all these have an impact with respect to convergence. It's not only constrained with respect to material properties.
No, the thing I would like to ask is that as the synopsis is incorporating with the quantum wise, which is a atomistic toolkit for simulating especially the two-dimensional or 1D, 2D materials, even for the bulk nanomaterials. So is there any kind of associated tool with, so you can suggest that can be used with Atlas TCAD?
So if you are performing with respect to atomic level simulation, that's what I mentioned. Like there is a separate tool. It doesn't comes with respect to Atlas. It comes as a separate tool. So which is meant purely for performing any like atom level simulation. It could be a quantum dot, whatever it is.
Okay. Thank you, ma'am.
Thank you. So is there any other question?
Thank you, madam. I think there is no more questions. So thank you, madam. Thank you.
Yeah, thank you. Thank you.
All, I welcome all the participants to the last session of today's FDP program. So in this session, our Center of Excellence Coordinator, Mrs. Soumya Mishra will give a demonstration of creating an ecosystem for IoT Industry 4.0 in academic environment. She will show the different facilities available in our university for carrying out research as well as product development. And with this, I welcome Mrs. Soumya Mishra to present its demonstration. Thank you all.
Thank you, sir. Thank you so much. A very good afternoon to my esteemed colleagues, authorities, the organizing committee members, and my dearest participants. This is Soumya Mishra. I'm Assistant Professor in Electronics of Telecommunication Engineer. Additionally, I'm also working as a coordinator for all the centers of excellence which are functional inside our campus. Apart from that, I'm also the institutional coordinator for IQAC. So basically, more or less, I'm into all those disciplines which ensures quality, accreditation norms, regulatory measures, which is carried out time to time and regularly inside the institution for the last couple of years. So once again, I express my gratitude to the organizing committee to allow me to present the state-of-art facilities which are there in the CGO campus. Definitely, I'm sure that this will promote, this might attract and might promote collaborative ideas with our dearest participants, and maybe they can come up with any other projects in association with CGO in the near future. So, hoping for the best, let me start my presentation. So basically, roughly I will be covering on the vision and mission, a brief about our university, the various programs which are floated in our university, in our organization. Most importantly, I will be highlighting the partnerships with the industry academics and the sector skill councils. Ladies and gentlemen, we are among the very few institutions across our nation and in Asia to float the marine engineering programs. So we are really proud of that. So I will be also showcasing the various facilities, the infrastructure which has been very meticulously set up for the marine engineering department. Most importantly, I will be also trying to cover all the centers of excellence, some brief about all the centers of excellence, but I really apologize in advance because currently we have 25 full-fledged functional centers of excellence and another 5 in the pipeline. That means the equipments are purchased, the land has been set up, the rooms are set up, but yes, we are yet to float the programs directly, which we are expecting to do anytime soon, anytime shortly, maybe maybe in the early next year. So I'm not sure whether I can actually cover all the centers of excellence, but I will try my level best to cover the best centers of excellence which have attracted a lot of fortune, a lot of projects, programs, and very valuable collaborations across the nation. Most importantly, CIJU is a markdarshan for its many institutes. So since we are very much in depth in accreditation, and we are really looking forward to many such advanced accreditation programs, and we really give our best and we strive our best for acquiring the world rankings as well. So definitely we have enrolled ourselves for the Margdarshak program, and we really thank AICT for giving us this opportunity in order to take up this initiative to train and mentor 10 institutes under our jurisdiction, and we will ensure that all those 10 mentee institutions will be accredited shortly, maybe in the next 2 or 3 years, and that will basically be the fulfillment of our objective. Apart from that, yes, I will be speaking a little bit on the incubated companies which we have established inside our campus, and more or less on the overall infrastructure. So yes, we do believe in excellence, and we do believe in emergence as a global leader, and that is basically our vision, just like any other institution. But not that, apart from that, also we do believe in establishing a skill army. Now, I'm sure everybody here will be accepting this fact that even the UGC, even the MHRD have expressed their deepest concern in evaluating this percentage of the engineers who are not employable. So this has basically given us a motivation to establish the various skill centers, and most importantly to establish a skill army. So we have stopped calling our students as students, but rather we have started calling them the skill army, because not just the theory, not just the practical, but most importantly the hands-on top tech initiatives and the top tech incubation trainings has been incorporated very meticulously for these students in order to make them a very strong skill army of the nation, and maybe they can become the entrepreneur. They can establish the startups in the future, and maybe they just don't have to depend on the campus programs or the placement recruiters or the employers to get engaged in the future. So regarding the academic establishment, yes, we are very, very focused on not just the core and the electives, but most importantly the internships and the project-based learning. We really promote the startups, the incubation centers, the project initiatives from UGC and AICT. Most importantly, we try to apply many other projects in establishment with the DST. And not just that, we have a couple of project collaborations with the external universities as well. Now, we have made a steady initiative of mapping all our academic course curriculums in establishment, in MOU, in partnership with the sector skill councils. Now, this has been a mandate since the day we have turned into a university, that is in the year 2020. So once, I mean, the very basic fact, the objective of becoming a university was to change the entire curriculum and map every academic activity onto the sector skill council syllabuses and making our students ready for the various skill competitions. Now, we are one of those institutes who have grabbed the first gold medal for the nation in water technology in Kazan, Russia. So, the very elite student, Mr. Ashwath Narayan, he was the first Indian to win the gold medal for India in the World Skills, which was held in the year 2019 in Kazan, Russia. So that, I mean, he was a very big hope for us, and he was basically the motivation for us in order to produce and in order to grab many such awards and accolades for the various subsequent batches, and to map every curriculum onto the sector skill councils in alliance with the world skill curriculum. So basically, in C.V. Raman Global University, we offer the 19 UG programs, 21 PG programs, 15 PG diploma programs, and PhD programs in all engineering disciplines and basic sciences. So we have almost 100 people registered currently since the last year in the PhD program. So we are a budding universities, but yes, we have overcome the benchmark, we have overcome the milestone for the very first year of establishment as a university. Now, as I was just now saying that we have 24 plus almost 25, I can say. I'm not exactly saying 25, but because the 25th Center of Excellence has not been officially inaugurated. So yes, officially it is 24, but functional, yes, it is 25, and another 5 more in the pipeline. So we have established these centers of excellence in association with the global giants in industrial automation, in process automation, in tool room training, in various, in the tool room practices, in the simulation, in the geographic information system and remote sensing, in the AC/DC drives, in the motor drives, in the robotics, in the graphics and simulation, in the tear down and benchmarking for the automation, and in the plumbings. So yes, these are the Center of Excellences and the high-tech laboratories which are very much present in 100 acres of the clean and green and smart campus of CGU. So these are certain accolades and achievements of our university. Yes, we have been awarded as NAC A certified institution, and we have established ourselves as a university in the year 2020. We have been rated as AAA by Careers 360, and we have been awarded the Best Higher Education Institute by Assocham. Not just in the year 2017, but my dear participants, we have been repeatedly awarded as a clean and smart campus by AICT consecutively for 2 years, that is 2017-18 and 2018-19. But yes, the third year, that is 2019-20, the results are yet to be out. So we again expect the best out of it.
ఫోన్ నెంబర్ చెప్పండి ఎన్నిసార్లు తీసుకున్నా కూడా నేను ఫీడ్ చేసుకోవడం మర్చిపోతాను
Can I request the participants to please mute the microphones? Thank you.
ఎప్పుడో ఒకప్పుడు అవసరమైనప్పుడు ఫోన్ నెంబర్ గుర్తొస్తుంది చెప్పండి 9347 291.
So these are the undergraduate programs which we offer, starting from the general engineering subjects up to the marine engineering. Again, these are the postgraduate programs and the PhD programs in exactly all those disciplines. May I request the host to please ensure, okay, let me mute. Okay, thank you. So, ladies and gentlemen, I was just now talking about the marine engineering department. Yes, we are among the very few institutions to have a marine department exclusively in the campus. And we have all the infrastructure and the setup for a fully functional marine department with all the tool rooms, the simulators, the artificial ponds, the life-saving boats, the fire prevention and firefighting kits, and everything. So we actually offer a 4-year BTech Marine Engineering program with 1-year GME course, and all our courses has been approved by the DG Shipping. Yes, so as you see these photos, so this has been a marine parade, And this was basically a very momentous occasion where we had established a collaboration. We had signed an MOU with Cyprus Maritime Academy. And again, this is exactly the engine room replica you can see with the engine and generators. This is the OOW simulator. We have an engine room simulator. We have a seamanship lab. As I was saying, an artificial pond setup with a lifeboat and the electrical workshop. So as I was just now saying that we have established these high-tech labs in association, in collaboration with the major global giants in industrial automation, robotics, and many such other disciplines. So these are exactly the industry giants with whom we have partnered since the last decade. And apart from that, also, we are in collaboration with NAFSA, with EAIE, with FICCI, with CII, and these are basically the governing bodies which have tied us up with various other universities across the globe. So we are also in establishment with ITMOR University, Russia, the National Research Nuclear University, Russia, the Nishantasi University, Turkey, the Cyprus Maritime Academy. Now this particular university has exclusive tie-up for our Marine Department OD. Now, Mingdao University is from China, and EDSIL University, who facilitates the Study in India scholarship programs for our neighboring Asian countries. So we have more than 150 international students residing in our campus. And also we are in setup with Malta College of Art, Science and Technology, that is MCAST. Exclusively for the world skills and for the Odisha skills, and to establish a skill army and aligning all our syllabuses in association with the sector skill councils. So these are the sector skill councils with which we have established an MOU. So basically these are the COEs and the year of establishment. As you can see, the very first COE was the Bosch Rexroth Center of Industrial Automation. So perhaps at that point of time, we were just one of those 2 centers across India to have set up or have a center of excellence in association with Bosch Rexroth. So at that point of time, basically industrial automation was emerging, and that was an emerging field. So we came up with fluid mechanics, with hydraulics, pneumatics, robotics, and many such modular skill courses to be floated externally, as well as given as a mandate to our students who have enrolled in the CGU campus. So should it be as a part of the CDT program, that is the career development program, or an elective, or a major project or a mini project, we ensure that all our students have gone through a minimum of 4 centers of excellence training throughout their 4 years. So as I was saying that, yes, officially we have inaugurated 24 functional centers of excellence, but yes, the 25th center of excellence is a drone center of excellence. So we have very deliberately not noted down here because that has not been inaugurated. Apart from that, yes, we are in a process of setting up another 5 centers of excellence. So a total of 30 centers of excellence, which everybody can witness by the year 2020 in CGO campus. So starting with the Bosch Rexroth Center of Excellence, yes, the year of establishment is 2010, and basically the short modular courses or the training programs which has been offered by Bosch Rexroth is hydraulics, pneumatics, the PLC, the mechatronics, the robotics, and sensor technology in collaboration with Bosch Rexroth Germany. But what these team of very diligent and very dynamic trainers and faculty members of Bosch Rexroth came up with, my dear participants, we are very privileged to reveal that they are a very integral part of an elite Atmanirbhar program in developing right now their own kits for automation and not just depending on Bosch Rexroth or importing these equipments from Germany. So yes, this series of developments came up with our elite respected honorable advisors joining the institutions and giving us awesome guidance for fabricating our own equipments, for establishing our own processes, for developing our own kits, and not just draining the INR or draining the Indian rupees into the foreign dustbin, right? So apart from that, in the recent years, we have been very keen in setting up the Industry 4.0 equipments, and all these automated equipments has been in alignment with IoT. So not just the manual automation, but right now we are very much into the integration of IoT and embedded systems and sensor-based equipments which are aligned with these heavy automation equipments. Apart from that, yes, we also offer courses on the transfer system drives with conveyor belt. Now, ladies and gentlemen, let's witness a short video on the Center of Excellence. Please have a look.
The last 2 decades has witnessed a tremendous surge in the application of automation technology in Indian industries. It has thus become very important for engineering students to have adequate exposure to the field before they embark upon their career. Bosch Rexroth Center of Excellence at C.V. Raman College of Engineering is a step forward to match the time. This center is a joint venture of CVRCE with Bosch Rexroth, a global leader in the domain of automation technology from Germany.
The center was established to spread the awareness of automation, which is now the brave word for manufacturing. Automation has spread in a very big way in India, and the main intention of this center is to make the students trained in areas of automation.
Automation involves knowledge in drives and controls, which in turn require insight into hydraulics, pneumatics, robotics, PLC, sensorics, and mechatronics. C.V. Raman Bosch Rexroth Center of Excellence endeavors its best to impart knowledge in the said fields.
So we have set up 2 labs, one is for drive and another one is for control. In drive, we have setups related to hydraulics, electro-hydraulics, pneumatics, electro-pneumatics, and mobile hydraulics, proportional hydraulics, and including digital hydraulics.
This high-end program provides exposure and hands-on training to the students and makes them familiar with different aspects of industrial automation. This program is extended to the BTech students of CVRCE in the streams of electrical, electronics and telecommunication, applied electronics and instrumentation, and mechanical engineering. The faculty and trainers of CVRCE, skilled by Bosch Rexroth Germany, teach them methodologies of how the fundamentals of engineering are applied in the day-to-day activities in industry.
Here we have 3 levels of training systems. In first level, they are learning the basic pneumatics part, means using by only cylinder, only valve and only the compressed air. The second level, they are covering the electro-pneumatic parts they are covering, like electrically how to control the pneumatic components. So that if they will use the electrical components, so their component will be reduced. Easily they can do the troubleshooting, they can do fault finding, they can take feedback with a long distance. So this is quite now frequently used in industries now. So industrial processes that totally depend upon the electro-pneumatic. This is our second level of pneumatic training. The third level, we have PLC based pneumatic systems where students can write program in computers. They can download the program to PLC. Through PLC they can interface. So they can do a graphical screen, they can operate the systems to computer systems, they can operate with a Android systems, so it is quite flexible, it is quite easier. In the Rexroth products, we cannot see the internal products, but in this kit specifically, so students can see the internal part, how the spool is moving, its movement procedure, its flow amount, cylinder velocity, all these things they can see in the transparent kit.
After getting the basic level of training, the students can practice using the trainer's kit.
Our engineers in mechanical engineering, electrical engineering and most of the manufacturing sectors, they need to be trained in all this technology to be rightly fitted into the industry.
This training activity of over 110 hours covers both classroom and laboratory components in line with those recommended by Bosch Rexroth. Thus, the center offers world-class training opportunity to the students to handle state-of-the-art automation equipments marketed by Bosch Rexroth.
The various applications can be in water filling industries and steel industries. We get familiar with all these equipments, so it is easy for us to get industry ready.
And we are getting a hands-on practice so that we can work efficiently tomorrow if you are joining any industries.
They are given a certificate which is considered very useful during their placement. Our students have an edge over other students in their placement because they are already acquainted with all aspects of automation in our center.
C.V. Raman Bosch Rexroth Center of Excellence adds immense value to the students of engineering. Because of the hands-on skills on automation technology, the pass-outs from the institution get an edge over their peers in the industry.
They get trained in all this technology, and when they go back to the industry, they absolutely fit into the requirement and giving them better opportunity for their professional career.
So that was indeed a very interesting video, and we always show it to our guests whosoever visit our campus, because definitely these centers are our pride, and definitely they give us a motivation, they give us a scope to get forward in the process and in the research with collaborative projects with the industries. Now, going forward with the Siemens Centers of Excellence, which is actually a sister center for the Bosch here. So both the centers are located adjacently, maybe just a couple of feet apart. But the basic setup of the laboratories are very similar to that of the Bosch Rexroth. But we have different programs floating under the Siemens exclusively in the total integrated automation, that is TIA, AC/DC drives, LV and switch gears, and servo motors. So please have a short look at the video.
Today, productivity of the manufacturing industry has reached the peak due to application of integrated systems and solutions in the field of automation. Understanding the trend, CVRCE has entered into an agreement with Siemens, the global leader of the domain, and established the Siemens Center of Excellence.
The Siemens Center of Excellence, we have established 2 labs for research and training, and all these equipments of the electrical equipments which you train in the Siemens, those all are of industry standard.
The program, run at the CVRCE Siemens Center of Excellence, is a combination of hardware and teachware, offering training and research facility in automation and related HMIs, PLC, SCADA, DCS, and related hardware and software. It also deals with variable speed, electronic controlled AC, DC and servo drives, LV switchgear including air circuit breakers and soft starters.
Electrical power is there in escalator, in motor, in conveyor belt, and everywhere the speed control is a primary thing. And our electrical students undergo this training in their Siemens Center. They write the program in SCADA and implement these programs for controlling the speeds in electrical motors.
This training activity of over 110 hours covering classroom and laboratory components includes multimedia presentations, PC animations, sample units and power units, circuit simulation on trainer kit, and circuit simulation on simulation software. The faculty and trainers of CVRCE, scaled by Siemens, teach the students the fundamentals of engineering applied in day-to-day activities in the industry. So this center offers world-class training opportunities to the participants, state-of-the-art automation equipments marketed by Siemens.
The 4-year training course which has been scheduled in a normal engineering course has been a very great help to us, because without any extra pressure and extra time we get to learn so many things here. The real industrial training kit, we'll get to learn the real industrial processes which will be very helpful in the near future. It even increases the weightage of our CV, which will be helpful for our placement. Very few colleges in India are providing such kind of training setup, so it's been a great help to us.
After completing their training, when they appear in their interviews, they are sure to do very well in their interviews. So apart from imparting training in automation, our training here also increases the market value of our students.
Because of the knowledge and hands-on skills on integrated automation technology, the pass-outs from the institution get an edge over the peers in the industry.
We train these students in such a way with the technology which is really adopted by the industry now, so that when they go back and join in the electrical industry and the automation related industry, they by that time they have already the expertise and the knowledge to command those technology. So these trainings will really helping them for getting better job.
Okay, so ladies and gentlemen, coming up with the fact center goal for process automation. So we have completed the industrial automation and the drives aspect of electrical engineering in the Bosch Rexroth as well as the Siemens Center of Excellence. Now, this particular process automation center of excellence, which has been associated with fact center goal, has exclusive training programs for automation vacuum generators, the gantry loader, the electric drive automation, the pneumatic drives, the vacuum generator, the compressed air preparation, the image processing systems, and many such modular courses. Very proudly we can say that within the fact center goal, we have an exclusive equipment for the world scale equipments for water technology as well. So yes, this is the fact center again. So yes, this was the momentous day on 10th March 2014, where our president inaugurated in association with the fact center director. These are certain photographs. So they are our elite world skill trainers. They are world skill certified trainers who have been the part of that proud journey, that gold journey, bagging the first gold medal for the nation. So these are the programs, these are the courses which are floated under the Fact Center Gold. So yes, we all are aware that process industry is a world of various industrial sectors, and basically the process automation exclusively has a big big demand in the water and the wastewater treatment, in the petrochemical industries, in the pharmaceutical industries, in the agro industries, most importantly. So, in liaising with the Process Automation Center here, we do have the paper recycling plants, we have the biogas plants, we have the biodegradable short plants, we have the STPs, and most importantly, we have the treatment plants, which are very much, automated and treated by the Process Automation Fact Center Code in the campus. So this is exclusively the EduKit PA Basic, which is completely sensor enabled, and basically it adds the automation technology with the pressure flow and ultrasound sensors with an input output connecting board for a controller. So this is the trademarked MPS PA compact workstation. And as I was just now saying, that the very coveted water technology equipments which are very much a part of the fact center here. They basically conduct an elaborative, very detailed study of the pH of a water sample. They also analyze the dissolved oxygen of a water sample. They also have various spectrophotometers for analysis of water sample by UV rays. They also go for the analysis of turbidity and various environmental discovery systems. So this is the maintenance test stand for pumps. And this is complete. This is the complete EDS station. This is the wastewater transport session. And yes, in order to, initially train a particular trainee with the wastewater treatment, we have also set up a virtual reality system. So again, we are using here the trademarked EDS WWTP VR simulator, which basically, virtually blurs the line between the virtual world and the real world. And basically, it goes on for a live simulation both for the distributed control system and the primary components of a wastewater treatment plant. So coming now next to the Welding Center of Excellence. So basically, the Welding Center of Excellence is a huge center here, which has been lately, very recently developed and set up much after the Fact Center, the Bosch Rickshaw and the Siemens Center basically.
Dear participant, there is a power failure. Within 2 minutes, we will resume the presentation.
I'm so sorry, there was a network disruption. Prabodh sir, can you please make me the co-host? Okay, thank you, sir. So yes, as we were discussing, basically the welding has a huge market in the industry, basically, and it covers vast applications, so be it the automotive, the aviation, the construction, the railway, defense, ship, and many more. So we in CGU basically we stood up to set up this vast welding center, and most importantly, not just the male students, but we are deeply involved in and encouraging the female students, the girl students to come up with the welding not just as passion, but also targeting as an occupation. So basically, this is the list of the equipments in the welding COE. And this is the MIG and the MAG and the pulse MIG and the MAG welding equipments, the SMA welding, the gas metal arc welding machine and the submerged arc welding machine, the plasma arc, the automatic CMT machines, the workstations and the classrooms, the microscope and the tester. And my dear participants, as you can see here, the girl students are deeply and very, meticulously encouraged to go for various welding championship programs, for the welding championship events. And our girls have made us immensely proud in winning so many welding championship awards across the globe. We are also very grateful to our Honorable President Shri Sanjeev Kumar Raut, who has set up a foundation for the orphan. So he has gone for a SAFAL program, SAFAL. So it is a SAFAL program. It's a successful program, and the name of the program is SAFAL. Basically, this program has adopted many girl students, and they have been completely patronized, and they have been completely sponsored with their entire set of educations, starting from the ITI diploma engineering, as well as the centers for upskilling and up to placing them in different industries. So as a successful outcome of those SAFAL programs, these girl students are right now in Tata, in Deloitte, in many global giants. They are right now working for many global giants in India and abroad. So they are our elite welding trainers, the faculty in charges, and the world skill trainers. So, ladies and gentlemen, these girl students are a part of the SAFAL program. They are coming from the orphanage, the Adruta orphanage, with which we have tied up as an institutional CSR activity. And these students have not just excelled in the welding skill, and they are very, very motivated to take up welding as an occupation in the future, breaking the norm, breaking the patriarchy, and going for the welding industry. So yes, this is a short video clip from the NWL, that is National Welding League 2020, and you can see how these girl students are excelling in welding. I'm sorry, did I just interrupt the video?
पिछले 5 सालों में ऐसा कुछ नहीं था, लेकिन वेल्डिंग ली. So we will participate. We are the student welders from all over India. Some students are giving their interviews on this and are indulging in various activities all over the country. But here students also likewise me, and we are very thankful to this institute that they are giving us the opportunity to bring ourselves confidence and happy International वुमेन्स डे. टेक्नोलॉजी का जमाना आ रहा है, तो जमाना साथ साथ टेक्नोलॉजी के चल रहा है. तो अभी रोबोटिक वेल्डिंग है जो बहुत चल रही है इधर इंडिया में. पहले पिछले 5 सालों में ऐसा कुछ नहीं था, लेकिन 5 सालों ने इंडिया ने बहुत ग्रोथ की है अपनी, और 5th पोजीशन पे है जहाँ सबसे ज़्यादा रोबोटिक्स यूज़ होता है. तो उससे क्या है, टाइम सेविंग है, क्लीन प्रोसेस है, और उससे जो हमें मटीरियल्स अलग अलग मटीरियल्स की ताल हो रही है, तो उन पे हम इजीली वर्क कर सकते हैं.
स्टार्टिंग में ये होता था कि हमें वेल्डिंग हमें कॉलेज में भी नहीं सिखाई जाती थी, हमें सपोर्ट नहीं था वेल्डिंग के लिए, और हम जैसे हमें ट्रेनिंग चलती है हमारी इंडस्ट्रीज़ में, तो हमारे वहाँ पे भी सपोर्ट नहीं था. तो जब हमारे कॉलेज ने ये चीज़ लॉन्च किया तो उन्होंने गर्ल्स को थोड़ा ज़्यादा सपोर्ट किया इस चीज़ के लिए कि अगर लड़कियां बढ़ेंगी तभी तो हमारा देश आगे बढ़ेगा, इस चीज़ के लिए. फिर जब वेल्डिंग का आया तो कॉलेज वालों ने कहा कि अगर तुम जा सकती हो तो जाओ, जाने में क्या है, क्योंकि तुम्हें सीखने को मिलेगा बहुत कुछ. जब हम पिछली बार यहाँ पे आए थे तो हमें बहुत कुछ नया देखने को मिला, बहुत सारे फ्रेंड्स मिले, बहुत अच्छी है. तो इस बार जब हमें मिला मौका यहाँ पे आए कि हमारा स्किल थोड़ा और डेवलप हो सके.
देखिए, ये सारा देश से लगभग 200 वेल्डिंग इंजीनियर्स यहाँ पर आए हुए हैं. तो हमारा दिल्ली से लेकर, पंजाब से लेकर, राजस्थान से लेकर, साउथ इंडिया, कोयम्बटूर, तमिलनाडु, सब जगह से बच्चे आए हैं, पुणे से भी आए हैं. तो ये जो अभी वेल्डिंग कंपटीशन है, ये उसका दूसरा संकलन है. पहले लास्ट टाइम हम लोग किए थे, बट अभी हमारा जो वेल्डिंग कंपटीशन है वो प्राइज़ जो जीतेगा उसको प्राइज़ देने का अलावा हमारा ये मकसद है जे जितने बच्चे इधर आते हैं तो उनका हम एक प्लेटफॉर्म बनाएंगे, उनका एक वेबसाइट बनाएंगे, उसको सारा इंडस्ट्री को लिंक करेंगे जो वेल्डिंग इंजीनियर्स को ढूंढते हैं. बिकॉज वुमेन, महिला लोग के लिए कितना स्कोप है इसमें? देखिए, अभी इसमें महिलाओं के लिए बहुत ज़्यादा स्कोप है, क्योंकि जितने महिला वेल्डिंग इंजीनियर इंडस्ट्री में काम करते हैं उनका परफॉर्मेंस बहुत बढ़िया है. एंड वेल्डिंग इंजीनियरिंग एक ऐसा ही प्रोफेशन है जिसमें एक लड़की 50,000 से उसका सैलरी स्टार्ट करेगा. तो ऐसे कोई ऐसे प्रोफेशन नहीं है जो आपको शुरुआत से 50 से 60,000 का तनख्वाह दे सकता है. तो वेल्डिंग इंजीनियरिंग ऐसा एक स्किल है जिसमें ये संभव है. तो हम चाहते हैं ये बच्चों का अंदर इसको प्रोत्साहन दें, उनको जानकारी दें, तो उनके लिए एक प्लेटफॉर्म में बनाएं, तो उससे मदद मिले उनको, वो आगे जाके. देखिए, आप हमारा वेल्डिंग सेंटर ऑफ एक्सीलेंस में हैं, इसमें यहाँ पर आपको रोबोट्स देखने मिलेगा, सारे ऑटोमेटिक मिलेगा. ये हमारा बेडरूम से भी और अच्छा है. तो वेल्डिंग एक गंदा और ऐसे काम है, ये गलत सोच है. वेल्डिंग इज़ ए वेरी सोफिस्टिकेटेड हाई प्रोफाइल प्रोफेशनल वर्क है. तो इसका जानकारी बच्चों का अंदर नहीं है. विदेश में जैसे चाइना में आप देखेंगे बहुत ज़्यादा महिलाओं ने उन वेल्डिंग इंजीनियरिंग प्रोफेशन को लेके उनको देश को आगे बढ़ाने के लिए मदद किया है.
Okay, so next coming up with the Google Center of Excellence. So this my participant has been recently set up in 2017, and it's a fully-fledged equipped laboratory with the Dell Latitude and the Chromebooks with Chrome OS the operating system laptops, and basically all our trainers have been Google certified, and they are having the professional certification, and they can certify other mentees. They can they can give certificates to anybody who has enrolled in the Google COE once they have completed the prerequisite norms and they have completed the course and they have passed the certification exams. So yes, this is the Associate Android Development Certification course which we impart. And apart from that, we also offer the summer internship courses. All these, the details of these courses you can find in our website in the www.cgu-odisha.ac.in. So you can find the links of all these courses. These are the short-term courses. We have the modular programs, we have PG diploma programs, and you can find all these courses under the section that is COE in the website. So exactly on the front page, on the very opening of the website, you can find a section at the top that is COE, and once you click the COE, you can come across the different COEs which right now I'm briefing you about, and under every COE you can find out the link for registering for these short-term modular courses. So he's our elite Google certified trainer, Professor Subhashish Das Mahapatra. He's a gem of a person, and he has been already certified Google certification professional course, and he is also AWS a cloud architect. He has been cloud certified, and let's hear Mr. Subhashish what he's talking about our Google Center.
Welcome to Google Center of Excellence. This Center of Excellence was established in 2017.
Madam, your slides are not moving.
They aim to provide students training and...
Well, ma'am.
Okay, yeah, thank you.
Welcome to Google Center of Excellence. This Center of Excellence was established in 2017 with the aim to provide students training and expertise them in Google related technologies like Android application development and digital marketing. So far we have trained around 300 students in this center on Android application development. Many of